What do you think about this statement? The ideal process is one without any variation. It probably sounds good in theory, but in practice, a process without variation doesn't exist. All processes are subject to some amount of variation. Even though you can't eliminate all variation, you can take steps to control it. Statistical process control, or SPC, can be used to measure, monitor, and control processes. SPC is a methodology that uses control charts to determine when a process is out of control. Once you've figured out that a process isn't operating as expected, you can find the sources of variation and apply the necessary corrective actions to control the process. How exactly does SPC help you to improve a process? Well, it's grounded in continuous improvement. You examine the inputs and outputs to determine what's really going on. This can apply not only to processes, but also to products and services. Essentially, anything you want to measure, monitor, and control. Let's explore two types of variations. Common causes are those that are inherent to the process and not controllable by process operators. For instance, common cause variation in manufacturing could include variation in raw materials, temperature and humidity, or equipment. Common cause variation can also occur in service processes. Variation in the input data, customer loads, and computer operations are all examples. Special causes of variation are sometimes called assignable causes and include unusual events that the operator can usually remove. These include large changes in raw materials or a mistake made by an operator. In service processes, examples might be sudden changes in service quality, delivery time, or cycle time. It's important to note that the effects of all variation may be similar. For instance, defects, quality loss, rework and scrap, waste, cycle delays, and unpredictability of the process behaviors. The difference is in the underlying causes and the degree of their effects. Special cause variation is usually more severe and visible. But the causes of common and special cause variation may vary. For example, variation in the claim processing time at an insurance company is due to both common and special causes. Some of the common causes may include the inherent variation in claims and customers. On the other hand, a sudden change in the variation, trends, and cycles all indicate the presence of special causes. For instance, a conflict between the existing software and the new process might have slowed the computers down. Or a lack of training and skill gaps among a few agents might be special causes for variation in the process. So why would you use statistical process control? SPC has three key objectives. A key objective of SPC is to monitor process performance to find out if changes occur. Monitoring performance entails determining process capability and the natural range of a process. It also involves assessing how the process measures up to specifications. Six Sigma practitioners use a number of basic quality control tools to monitor processes: control charts, histograms, run charts, and check sheets, to name a few. Another of SPC's objectives is to identify the special cause and common cause variation in a process so that appropriate measures can be taken to eliminate special causes. This involves using statistical analysis to help identify sources of variation. It's crucial to distinguish between the two. Why? Well, suppose you adjusted a process in response to common cause variation. This is known as overcontrol, which could result in more variation, not less. Or what if you failed to respond to special cause variation? This could also result in more process variation, or undercontrol. Six Sigma practitioners distinguish between special and common cause variation by examining runs of data and tracking trends exhibited on control charts. The final SPC objective is to control and improve process performance, which includes reducing variation in the process. Even when processes are within specification, excess variation can translate into extra costs. You might be able to eliminate these costs using process improvement. As a Six Sigma Black Belt, you can use SPC tools, such as control charts, to return visible and dependable results that contribute to overall quality improvement. Quality isn't without cost. It requires investments in both time and money to measure, evaluate, audit, and test processes to ensure the products and services being produced conform with quality standards. But despite the costs, SPC offers great benefits to your organization. At this stage, it's important to differentiate between the concepts of defect and control. A defect is determined by the process violating the specification limits, whereas a process would be called unstable or out of control when it violates the control limits or exhibits an abnormal behavior when plotted on a control chart. Control limits are different from specification limits. They're more inward-looking and are calculated from process data itself. Specification limits, on the other hand, are usually determined by factors external to the process. For instance, customer requirements, industry standards, or the company's strategic goals. However, a process that's within control is likely to have less variation, and most of its data points are expected to be within the specification limit. Such a process will result in products and services that have fewer defects, are of better quality, and require less rework, scrap, and inspection. Now that you understand the objectives and benefits of SPC, how do you actually use it in your company? There are several considerations for implementing SPC at the ground level. The first consideration is that SPC requires buy-in from every member of the team, including operators and management. This means some necessary investment of time and money. Operators and those working closely with the process will do much of the actual work of SPC monitoring and analysis, so their support and understanding of SPC is critical. Management must also sign off on the costs associated with setting up the program and training staff, creating and monitoring charts, and implementing the data collection system. Finally, everyone must recognize the need to investigate and correct indicated process defects. You should also understand that, in order to work, the SPC method must be correctly implemented. This might seem obvious, but you have to be careful not to overanalyze and get nothing accomplished as a result. For instance, over-relying on control charts can be dangerous. Plotting control charts for every aspect of every process is not feasible. Another consideration for implementing the SPC methodology is that SPC focuses on process issues, not human issues. What does this mean? Well, instead of intimidating and reprimanding workers, process owners have control over the process. In other words, they have the ability to record the behavior of the process and the authority to change the process as needed. SPC is a toolkit that provides immediate, quantitative feedback on process behavior. It can be an indicator of total process performance, but it's not a short-term cure-all. It's also not a complete quality control or quality assurance program. There's one final consideration. Although you can use many other graphical tools as part of SPC, control charts are the most common and preferred tool. They'll also be the tool discussed during the remainder of this course. Where other tools are much simpler and generalized and are used ubiquitously in almost every phase of Six Sigma, control charts are the primary control tools and the backbone of SPC. They're perhaps the most important tools used in the control phase of Six Sigma DMAIC. You can use Statistical Process Control, or SPC, to measure, monitor, and control processes. SPC is a methodology that uses control charts to determine when a process is out of control, but it's not a complete improvement program. SPC has three main objectives: to monitor the performance of a process, to identify special and common cause variation, and to control and improve process performance. SPC can offer great benefits to your organization, but it has to be properly implemented, keeping in mind several considerations. It requires buy-in from everyone involved in the process, including management, and you have to be careful not to overanalyze when you're implementing the program. SPC focuses on process issues, not human issues, and it provides immediate quantitative feedback on process behavior. Finally, control charts are preferred over other graphic. When you're using Statistical Process Control, or SPC, you'll find that control charts offer many benefits. In fact, you might be tempted to think that if a control chart can help control a process, charting every characteristic or process variable will allow you to entirely control the process. But it is possible to overchart. And when you chart too many parameters, there's a risk that you'll spend so much time and effort completing the charts, the actual processes you're monitoring will become secondary. When a change actually does happen, you might overlook it. When you use more than a few charts, the benefits can actually decrease while costs increase. So it's vital that you choose the appropriate variables for control charting and monitor only these. So what criteria should guide your choice of variables to monitor with control charts? Typically, this will depend on your own experience and judgment, but you should keep in mind a few considerations when selecting variables for SPC. You can choose variables that are most difficult to hold or variables tied to customer, organizational, or regulatory imperatives. One could also choose variables that represent a critical dimension of the product or process, or you could choose salient or known variables. The first category comprises variables that are most difficult to hold or maintain. An example of this is variables that can be directly associated with high defect rates. Another example is variables that are known to exhibit a lot of variation. The next category of variables you should consider for control encompasses variables tied to customer, organizational, or regulatory imperatives. The first example involves major sources of customer complaints. If customers are unhappy about an aspect of your product or service, that's a variable you should consider for monitoring using a control chart. For instance, customers at a retail store could be unhappy with the service they receive. This would be an area you should focus on. Another variable you should consider for control is any characteristic that key customers request. Obviously, if there's a product characteristic your customers are particularly interested in, that should be your focus. For example, a cellular phone manufacturer might find that customers don't care about having multiple ringtones, but do care about the battery life. The battery life of the handsets may definitely be a variable of interest for the cellular phone manufacturer. You should consider using control charts for items that must adhere to applicable organizational or regulatory standards. For instance, an expanding company might want to build new premises, and making sure the new building meets environmental standards might be important to the company. So, what are some other variables you should consider as good candidates for control? Well, another category includes variables representing a critical dimension of the product or process. For example, you should consider aspects of a product or process that affect human safety, the environment, or the primary use of the product. Key process variables that impact the product are ideal candidates. These include key process input variables, or KPIVs, and key process output variables, or KPOVs. You should analyze KPIVs to figure out how they affect a process. KPOVs can help you determine process capability and use control charts to monitor the process. A few more examples of variables fit into this category, including variables that have caused processing difficulties, variables that help control the process, and items that contribute to high internal costs. When you're using statistical process control, the ideal situation is that you'll have one variable that's so critical there'll be no question about what to chart. But it might not always work out this way. If you don't have a critical variable, or if you have to choose between multiple options, you can rely on other familiar tools. For instance, design of experiments, analysis of variance, and Pareto analysis can all help you identify variables to select for charting if the need arises. The final category of variables you should consider for control involves salient or known variables. For example, you might select variables with special cause variation, the root cause of which is known. Or you can choose variables that can be measured or items that can be counted by the person doing the charting. Another example would be to chart a leading indicator, which is a variable that detects special causes before others do. So how can you use these categories to select variables for your own projects? Reviewing an example will help you translate what you've learned into real life. You're the Six Sigma Black Belt at a toy manufacturer. In the past few weeks, several customers have complained about the brittleness of certain motorized toys and their inability to maintain shape after only a few weeks of use. Management is very concerned about the customer complaints and excessive variation. Cost control and customer satisfaction are both important to your company. You and your Six Sigma team find that the variations mostly occur in the toy's base structure as it goes through the molding and stamping process. And you determine that customer complaints about brittleness and shape also relate to the base structure. You identify as many as 15 probable input and output variables in the process that could be causing the variation. You eliminate 7 of them at the primary stage because they aren't critical to product quality or customer requirements. The remaining 8 are the quantity of the liquid plastic poured in the die temperature, liquid plastic temperature, liquid plastic density, injecting pressure, cooling time, material elasticity, and tensile strength of the base structure. Because monitoring all 8 variables that made it to the next round of analysis is impossible, for process control purposes, you and your team want to narrow down the variables to those most critical to cost, variability, and customer satisfaction. These are the variables you'll monitor using statistical process control methods. Consider the following example. The engineering team determines that brittleness is directly associated with the liquid plastic temperature. The base structure is brittle coming off the mold when standards aren't adhered to. The team then proved that liquid plastic density could be directly attributed to the base structure having low tensile strength. However, considering its significance to customer satisfaction, the team decided to monitor this variable separately. The production manager reported that material is often discarded due to the liquid plastic overheating or the liquid plastic density straying from technical standards. Next, you note that the quantity of liquid plastic poured in the die is controlled manually, causing lots of rework and waste in the process. Finally, you conduct a factor analysis with a large sample. This reveals that other variables, such as cooling time, die temperature, and injecting pressure, aren't major causes of variation. Based on this analysis, you decide to use control charts to monitor 4 out of the final 8 variables. Liquid plastic temperature was chosen because it's a key process variable that impacts the products, and the items must adhere to applicable organizational or regulatory standards. Liquid plastic density was chosen because it's a key process variable that impacts the product, and it's also a major source of customer complaints. The quantity of the liquid plastic poured in the die was chosen because it contributes to high internal costs, and this is a process that runs at a high defective rate. Tensile strength of the base structure was chosen because it's a variable that's known to exhibit a lot of variation. It's also a major source of customer complaints. These considerations can help you select variables for SPC. Even so, it's important to keep in mind that, ultimately, the selection of variables will depend in large part on your own experience and judgment. Control charts can offer many benefits when you're using statistical process control, or SPC. However, it's important to avoid overcharting. When you use more than a few charts, the benefits can actually decrease while costs increase. Therefore, you have to choose the appropriate variables for the control chart and monitor only these. You should consider 4 categories of variables for control: variables that are most difficult to hold, variables tied to customer, organizational, or regulatory imperatives, variables representing a critical dimension of the product or process, and salient or known variables. As a Six Sigma Black Belt, you'll often have to examine processes and find ways to minimize variation among similar items. You can use rational subgrouping to help with this task. What is rational subgrouping? To answer this question, you first need to know what a rational subgroup is. It's a small, homogeneous sample from the process, taken in a short space or time, so that all of the items in the subgroup are produced under similar conditions. Rational subgrouping is the technique used when you're selecting subgroups for creating control charts or for any other analysis and process control purposes. The rational subgrouping is done so that just the normal or random effects are responsible for the observed variation within the subgroup, and that allows you to observe all significant variations, shifts, and trends in the process. There are 2 types of variation, within subgroup and between subgroup. To capture variability within a subgroup, you take samples from one particular source, for instance, 4 samples taken from the output of a single machine. To capture variability between the subgroups, you take samples from a number of sources. For example, you could take a sample from each of 4 machines that produce the same product. It's already been mentioned that control charts rely on rational subgrouping of the process data. For example, when you're dealing with variable data and decide to create an X-bar and R chart, you calculate the average, or X-bar, and range, or R, for each subgroup. Then you plot these on control charts to determine if the variation from subgroup to subgroup is consistent with the average variation within the subgroups. Usually, you need to select subgroups in a way that ensures they're as homogeneous as possible. A relatively lower within-subgroup variation allows for maximum chances to observe subgroup-to-subgroup variations. Why do you need to minimize within-subgroup variations? Because in the X-bar chart, you use the average of subgroup averages to determine control limits for the entire process. The between-subgroup variations are used for plotting data points around the center line and upper and lower control limits. Now, if within-subgroup variations are too high, the resulting control limits will be too far from each other and from the center line. As a result, when you plot the data points around the center line, even a significant variation, shift, or trend between subgroups will still appear within the control limits. This will reduce the sensitivity of the control chart in catching variations, shifts, and trends in the process. However, if the within-subgroup variation is kept low, your control limits will be narrower and closer to each other and the center line. When you plot the data points now, even the slightest variation in the data points will have data points going over the control limits. Those subgroups will be identified as out of control. As part of rational subgrouping, subgroups are selected in a way that minimizes within-subgroup variation and maximizes between-subgroup variation. Another thing to keep in mind, as the project's black belt, you should always select samples in a way that explores the variation of interest to you. The variation of your interest might be shift to shift, day to day, hour to hour, or batch to batch. It's common to explore between-subgroup variation over time, location, customer, or supplier. The main thing to remember is that you should take subgroups from different times, locations, or operators if you're interested in differences between these types of variables. But to create meaningful control charts, you must form subgroups with items that were produced under similar conditions. This will help ensure that variations between the measurements within each subgroup is attributable to background noise only. If you're interested in variation according to time, location, operator, or other variables, you should choose subgroups with the intention of minimizing variation within each subgroup while maximizing the chance that subgroups will be different from each other due to variation in underlying conditions. To organize subgroups so they're internally homogeneous with respect to potential causes of variation, subgroups should have several properties. You should already be familiar with these properties from your prior experience with Six Sigma. Each of the properties you just reviewed are key to rational subgrouping. If you want to reduce variation within subgroups plotted in control charts, rational subgrouping can help do this. You know that in rational subgroups, the observations comprising the subgroup must be independent. This can be challenging for processes that are particularly prone to dependent sampling. For instance, in chemical processes, samples taken close together in time are influenced by one another. Subgroups formed over a short period of time often have observations within the subgroups that are very similar. Or consider a service process variable, such as the wait time at a financial institution. Your wait time will be directly influenced by the wait time of the person in front of you. Another example would be discrete part manufacturing. When you use feedback control to change a process based on your past observations, the observations automatically become dependent. The second property of rational subgroups is that the observations within a subgroup are from a single, stable process. Consider what would happen if they weren't. When subgroups are made up of multiple process streams, the within-subgroup variation would be significant compared to the between-subgroup variation. The last property is that the subgroups are formed from observations taken in a time-ordered sequence. You can't form subgroups from random data. A subgroup has to be a snapshot of the process over a small window of time, the optimum size of which is determined on an individual process basis. Now that you understand the principle behind rational subgrouping, you can move on to its application. Rational subgrouping is used in a variety of situations that involve control charting, but remember, the variation of interest should be the between subgroup variation, with the intention of minimizing within subgroup variation. Consider the following examples of how rational subgroups were selected. A car rental company wants to improve the turnaround time for getting cars ready for the next customer. The Six Sigma team selected 4 samples on a specific day from each of the 3 rental locations in one city. Each rental location was formed into a subgroup. This shows the team its variation of interest, which is between locations. A cereal manufacturer wants to reduce variation in the box filling process. The filling machine has 4 filling heads, and the Six Sigma team formed subgroups by taking a sample from each head. However, the filling heads all have different average values, causing the within subgroup variation to be larger than the variation in the subgroup averages. This demonstrates an important point. Sampling across different streams or machines when you want to compare product variation will sabotage your control chart by introducing too much within subgroup variation. But this study could yield valuable information. It tells you that potentially important variation exists between output streams, different machines, different operators, and different manufacturing lines, for instance. It's often recommended that separate control charts be constructed for each of the different output streams. This shows the team its variation of interest, which is between machines. A manufacturing process involves stamping each piece as it's produced. The machine stamps 30 pieces per minute using 5 pistons on a conveyor belt. The Six Sigma team wants to select subgroups of 5 pieces. What's the best way to do this? Well, the team could select the first 5 pieces in a row, which would have the 5 samples produced by 5 different pistons. But a better choice would be to select the pieces that are formed by the same piston over a period of short time, which would make more sense as a rational subgroup. This shows the team its variation of interest, which is between pistons. You should note that if the samples for each subgroup are collected over a long period of time, for instance, a couple of hours or a day, the time will also act as a key variable apart from the machine. Some unknown or unavoidable conditions, such as humidity or room temperature, might change during this time. To avoid that variable coming into play, the team should collect subgroup samples over a shorter period, such as a few minutes. As a Six Sigma Black Belt, you need to understand how to apply rational subgrouping. This will help you to more effectively organize and chart data so that it answers the right questions about the process you're examining. You need to keep a few final considerations in mind about rational subgrouping. These have to do with subgroup size. The first is that if you have a large subgroup that you've taken over a short period of time, it may contain dependent data. However, if you take the subgroup over a longer period of time, it may contain special cause variation. In other words, larger subgroups taken over too short or long a period of time may contain dependent data or special cause variation. The process will often dictate the size of a subgroup, but you should consider both the pros and cons of having a small subgroup size. For instance, a sample size of 2 or 3 items. One benefit to taking this approach is that small subgroups are more economical and assumed to be rational. However, even though smaller subgroups can easily detect large shifts, 2 to 3 sigma for example, they can't detect smaller shifts as easily. The final consideration about subgroup size is that you need a sufficient history of the process in order to create a control chart that's meaningful. It's important to collect enough data observations so you can calculate reliable estimates of the variation and average. In addition, you can't distinguish between special causes and common causes if you don't have enough subgroups to define the common cause operating level of a process. So you've created your rational subgroups. Now what? The next step is to select the control chart, which you'll learn how to do in the next lesson. Rational subgrouping is a technique used when you're selecting subgroups of data. A subgroup contains all the measurements in one plotted point on a control chart. A rational subgroup is a sample where all the items are produced under conditions in which only random effects are responsible for the observed variation. The main principle behind rational subgrouping is that you should choose subgroups that give the maximum chance for within-group observations to be alike. This maximizes the chance that special cause variation will occur in between-group variation. There are a few considerations involving subgroup size. Large subgroups may contain dependent data or special cause variation, but small subgroups are more economical and are assumed to be rational. The optimum number and size of subgroups is proportional to the size of the process shift you wish to detect. Another consideration is that service processes typically have a sample of 1. And finally, teams need to have a sufficient history of the process to help determine the appropriate size for subgroup. As a Six Sigma Black Belt, you know that in any quality improvement initiative, it's important to rein in out-of-control processes. Control charts are often created as a key step in quality improvement. They help you assess the stability of a process over a period of time. From your Greenbelt training, you'll recall that control charts tell you whether or not a process is in statistical control by graphically showing the upper and lower control limits of a key process characteristic. They also demonstrate how a process changes over time. Control charts are powerful tools. You can use them to analyze variation in almost any process and for several reasons. For example, to control ongoing processes by pinpointing and fixing problems as they occur, to predict the range of outcomes you expect from a process, and to determine whether a process is stable or in statistical control. Other reasons include to analyze process variation patterns from special or common causes, and to determine if the goal of your quality improvement project should be to prevent specific problems by making changes to the process. You'll also recall that a control chart always has a center line that shows the average, an upper line that shows the upper control limit, or UCL, and a lower line that shows the lower control limit, or LCL. Individual data points can be referred to as either measurements or observations. You determine the values for these lines using the same sample data for drawing lines and plotting values. Lines are drawn by considering all values. Then, you plot the subgroups and individual data points considering individual subgroup values. Now you can compare current data to these lines to determine if process variation is consistent. You can access the content on key elements of control charts after this video to review the purpose and main components of control charts. You need to perform 6 steps to create and use a control chart. First, choose the appropriate control chart for your data, then determine the center line, and proceed to determine the upper and lower control limits, the UCL and LCL. Then, draw the center line, UCL and LCL, and plot the data points. Finally, analyze and interpret the chart. Because you should already be very familiar with the process involved in creating and using a control chart, we will instead focus on how to choose the appropriate chart, and also cover the basic background for determining the center line, UCL, and LCL. Even though you'll almost always perform these calculations using software, it's still important to know where the values come from. When you're selecting a control chart, it's important to remember the difference between the types. Control charts for variable data are used when the quality characteristic can be measured and expressed as numerical data, length, volume, temperature, or time. A key characteristic of variable data is that it can be expressed in decimal values. For instance, 1.375 centimeters, 120.78 degrees Celsius, 3.25 hours, or $3.50. Examples include a Six Sigma Black Belt comparing the weight of parts as they are produced, or a quality analyst measuring customer processing time at a ticketing window. Control charts for attribute data, on the other hand, are used for product characteristics that can be evaluated with a discrete response, pass or fail, yes or no, good or bad. They typically plot the number or proportion of defects or defectives. An example is a quality control engineer using specific criteria to classify items coming off the production line as acceptable or unacceptable. There's another difference between the two types. Control charts for variable data is constructed in pairs, whereas control charts for attribute data is used singly. Sometimes you'll have a choice. For instance, when you haven't yet collected the data, and you could choose to collect it as variable or attribute data. In this case, you should keep in mind that variable charts are relatively accurate, but also expensive and effort-intensive. Each chart type is best used in certain situations and has its own unique characteristics. There are control charts for variable data when the subgroup size is greater than 1. Common types of control charts for variables include the X-bar and R chart, which is also known as the R chart or the XR chart. The other type is the X-bar and S chart, which is also known as the X chart or the XS chart. Then there are control charts for variable data when the subgroup size is 1. Control charts for variable data when the subgroup size is 1 are known as individual and moving range charts, or IMR charts. An IMR chart is a pair of control charts for processes with a subgroup size of 1. It creates a picture of how the system changes over time and is used to determine if a process is stable and predictable. Finally, there are control charts for attribute data. Control charts for attributes include C and U charts, which follow the Poisson distribution, as well as NP and P charts, which follow the binomial distribution. You can access the job aid Selecting a Control Chart after this video as a guide for helping you choose the correct control chart in different situations. The first category includes the common control charts for variables data. The X-bar and R chart plots the subgroup mean, X-bar, and range, R, of a process. It's typically used when subgroups contain between 2 and 10 measurements. The sample averages are plotted on the X-bar chart and show any changes in the mean value of the process. The range values are plotted on the R chart and indicate changes in the dispersion of the process. The X-bar and S chart plots the subgroup mean and standard deviation. It's a better choice when you have subgroup sizes greater than 10, because the standard deviation statistic is a better estimate of subgroup variation than range for large subgroups. Instead of using an R chart to plot the range, it uses an S chart to plot variation within subgroups. You can access the content about X-bar and R and X-bar and S control charts after this video to review these charts, as well as the steps for constructing them. The next type of control chart is the individual and moving range chart, otherwise known as an IMR chart. It is used for variable data that uses individual measurements of a quality characteristic. An IMR chart plots both the individual measurements and the moving range between subgroups. Data can be expensive to obtain, or it occurs very slowly and a rational subgroup cannot be formed. IMR charts are used when sample data isn't in subgroups, but rather in individual data observations. In other words, you use an IMR chart when the subgroup size is 1. You can access the content on control charts for individual observations after this video to further review IMR charts and the steps for constructing them. For instance, you're the Six Sigma Black Belt in an electronics manufacturing facility. You've determined that the temperature of the soldering equipment is essential to the product's quality. Due to cost and technical constraints, you can measure the temperature only once every hour in degrees Celsius. Which chart would you choose in this situation to monitor the performance of the process over a period of 12 hours? Well, you know that temperature measurements are continuous data. This tells you that you need a variables chart. You also know the subgroup size for each of the measurements, it's 1. Using the flowchart, you can conclude that an IMR chart is the best option for this scenario. The final category includes common control charts for attributes data. First, recall the C and U charts, which follow the Poisson distribution, where you can count the number of defects instead of categorizing items as defective or non-defective. The C chart plots the number of defects per subgroup or sample. For instance, you could measure defects by day, batch, or machine. You can use this chart when the sample size is constant. The U chart plots the average number of defects per unit because it's generally used when sample size isn't constant. Because the samples aren't constant, it's necessary to create a standardized statistic. You may notice that the UCL or LCL are not straight lines in the U chart, signifying the varying sample sizes. You can access the content about C and U control charts after this video to further review C and U charts and the steps for constructing them. The final two charts are the NP and P charts, which follow the binomial distribution. The NP chart plots the number of defective or non-conforming units, and it's used when the subgroup or sample size is constant. Because the subgroups are equal in size, converting defective counts into proportions isn't necessary. The P-chart plots the proportion or ratio of defective units because it's used when the subgroups aren't of equal size. Similar to the U-chart, the UCL and LCL aren't straight lines. This signifies the varying sample sizes. This chart is most effective when the sample size is 50 or more. You can access the content about NP and P control charts after this video to further review NP and P charts and the steps for constructing them. Suppose you're the black belt at a large retailer, for example, and you're monitoring an invoicing process improvement project. You want to know the stability of the invoicing process by counting the number of errors that occur in it. So you randomly collect subgroups of equal size, 200, from the invoices generated over 15 weeks. Do you know which chart to use in this situation? Since you want to know if the process is in control by counting errors in the invoices, you know you need an attributes chart. You're counting the number of errors in the invoices, which tells you you're monitoring defects. You also know the subgroups are all the same size, 200. All these factors combined tell you that you should use a C chart. To use control charts effectively, you need to understand which control chart to use in a specific situation. When you know the subgroup size and the type of data, whether attribute or variable, you can select the appropriate chart. Once you've selected a control chart, you can move on to calculating control chart values. As you complete steps 2 through 5 of developing a control chart, you'll calculate and draw the center line, UCL, and LCL. The center line is an average of the data points being plotted. These data points can take several forms. It can be seen in the form of individual values, abbreviated as I, subgroup averages, abbreviated as X bar, subgroup ranges, abbreviated as R, proportions or counts per unit, abbreviated as P and U, and numbers or counts, abbreviated as NP and C. Here's an example of an X bar and R chart's center line. To find out the extent of variation in the process that produces glass cylinders, Six Sigma team members pull a sample subgroup of 5 cylinders at 1-hour intervals. Then they measure the diameter of cylinders and chart the average value for each subgroup on the X bar chart and the subgroup range on the R chart. The average of the data points is the center line for each chart. When the subgroup sizes aren't equal for all the points on a control chart, it may be appropriate to set variable or separate control limits for each point, proportional to their subgroup sizes. In these cases, the control limits might not take the form of a straight line. And smaller subgroup sizes mean less certainty, so you'd set control limits further from the center line. Each type of control chart has associated formulas that allow you to calculate the UCL and LCL and the center line. Before moving on to the formulas, you should recall that constants are involved in the formulas for variable charts. An IMR chart uses the UCL of the individual control chart equals X bar plus the outcome of E2 times R bar. The center line equals X bar. The LCL equals X bar minus the outcome of E2 times R bar. E2 represents a constant based on the subgroup size, and R bar represents the average of all subgroup ranges. The UCL of the moving range chart equals D4 times R bar, where D4 represents a constant based on the subgroup size. The center line equals R bar. Finally, the LCL equals D3 times R bar. D3 represents a constant based on the subgroup size. For the X bar and R chart, the UCL of the X bar chart equals X double bar plus the outcome of A2 times R bar. The center line equals X double bar, which represents the grand average of all subgroup averages. The LCL equals X double bar minus the outcome of A2 times R bar. A2 represents a constant based on the subgroup size, and R bar represents the average of all subgroup ranges. The UCL of the range chart equals D4 times R bar. The center line equals R bar. Finally, the LCL of the range chart equals D3 times R bar. D3 represents a constant based on the subgroup size. Looking at the X bar and S chart, the UCL of the X bar chart equals X double bar plus the outcome of A3 times S bar. The center line of the X bar chart equals X double bar, which represents the grand average of all subgroup averages. The LCL equals x double bar minus the outcome of A3 times S bar. A3 represents a constant based on the subgroup size, and S bar represents the average of all subgroup standard deviations. The UCL of the S chart equals B4 times S bar. B4 represents a constant based on the subgroup size. The center line of the S chart equals S bar. Finally, the LCL equals B3 times S bar. B3 represents a constant based on the subgroup size. You can access the job aid control chart formulas after this video as a reference to the formulas used. Consider the example. You're the black belt at a bank and want to find out if the mortgage processing time is in statistical control. Every mortgage case is unique and takes a long time to complete, so it isn't possible to subgroup many cases into one. This is because they won't be homogeneous and might have more variation than what occurs naturally. So, considering each case individually and having a subgroup size of 1 makes more sense. Therefore, you can create an IMR chart and want to calculate the UCL and LCL. First, you calculate the values for the moving range chart. To find the UCL for the moving range chart, you multiply D4, which is a constant value, 3.27, by R bar, which you've already established is 0.68. This gives you a UCL value of 2.22. To find the LCL, you multiply R bar by the constant value D3, which is 0 for n equals 2. Here, that's 0.68 times 0, which is 0. Now that you've reviewed the variable chart formulas, let's review formulas from the chart. To find the UCL for the P chart, you must have both P bar and N bar calculated. P bar is the center line, which is the defective proportions average. N bar is the average number of observations per subgroup. The formula is P bar plus 3 times the square root of the following. The result of P bar multiplied by the result of 1 minus P bar divided by N bar. The formula for the LCL is P bar minus 3 times the square root of the following. The result of P bar multiplied by the result of 1 minus P bar divided by N bar. A negative value for this calculation means the LCL is set to 0 on the control chart. The formula for the UCL of an NP chart requires that you have P bar calculated, which is the defective proportions average. The formula for P bar is NP bar divided by N, the total number of observations in the subgroup. The formula for the UCL is NP bar plus 3 times the square root of the following. NP bar multiplied by the result of 1 minus P bar. The formula for LCL is NP bar minus 3 times the square root of the following. NP bar multiplied by the result of 1 minus P bar. Keep in mind that a negative value for the LCL calculation is equivalent to 0 on the control chart. The C chart UCL formula is C bar plus the result of 3 times the square root of C bar. The LCL formula is C bar minus the result of 3 times the square root of C bar. If the LCL is negative, it is set to 0 on the chart. The U chart UCL formula is U bar plus 3 times the square root of U bar, divided by the square root of N bar, where N bar is the average number of observations per subgroup. The LCL formula is U bar minus 3 times the square root of U bar, divided by the square root of N bar. N bar is the mean number of observations per subgroup. If the LCL is negative, it is set at 0 on the chart. Return to the prior example where you're the black belt at a large retailer and you're monitoring an invoicing process improvement project. You now want to know if the invoicing process is in statistical control by counting the number of errors that occur. You're creating a U chart and want to calculate the UCL and LCL. To calculate the UCL, you must have values for U bar and N bar. U bar is the center line, which is 0.137, and N bar is the total observations, 2,948, divided by the number of subgroups, 15. This equals 196.53. Plugging the numbers into the formula gives 0.137 plus 3 times the square root of the result of 0.137 divided by 196.53. That makes the UCL 0.137 plus 0.079, which is equal to 0.216. Next, you calculate the LCL by plugging your numbers into the formula. This gives you 0.137 minus 3 times the square root of the result of 0.137 divided by 196.53. The LCL is then 0.137 minus 0.079, which is 0.058. Control charts help you assess the variation and stability of a process and help determine whether or not the process is in statistical control. They help you measure a process over time and examine for any special cause variation. You need to perform 6 steps to create and use a control chart. Choose the appropriate control chart for your data, determine the center line, determine the upper and lower control limits, the UCL and LCL, draw the center line, UCL and LCL, plot the data points, and analyze and interpret the chart. Each chart type is best used in certain situations and has its own unique characteristics. There are 2 categories of charts: charts for variables, including individual and moving range charts, and charts for attributes. Each type of control chart has associated formulas that allow you to calculate the UCL and sometimes conventional control charts can't be used for all processes. You're already familiar with the common ones: X bar and R, X bar and S, IMR, P, NP, C, and U. But beyond these, several specialized control charts are available to you and your Six Sigma team when certain situations warrant them. You'll learn about 2 of these in this topic: moving average charts and short-run SPC charts. Both of these charts are used when you collect data infrequently. You can also use them when you don't have enough data to support your statistical conclusions or detect the trends of interest using a conventional chart. The first of these charts, the moving average chart, is often combined with a moving range chart, which you should be familiar with from the IMR chart. The moving average chart is similar to the IMR chart in that it combines a set of adjacent observations to take the average of these, then drops the oldest observation, picks up a new one, and calculates the average again. But instead of doing this with range observations, it does it with means, or X-bar. So to use a moving average or range, take a short run of the individual values and find the average and range of these. Then you move over 1 step in the run and retake the average and range. You continue in this manner, moving over another step and calculating average and range. You then plot the moving averages and moving ranges you find for each run as points on the control chart. The runs are often n equals 2 or n equals 3, and the higher the number of n, the less sensitive the chart is to changes in individual x values. Suppose the first 7 measurements taken in a process are 131, 140, 152, 139, 130, 141, and 129. If you have a moving average run of 3, or n equals 3, and you want to find the moving averages, here are the values you'd get. The moving average for the first set would be 141, for the second set 143.7, for the third set 140.3, for the fourth set 136.7, and for the last set 133.3. Compare the original data set in the previous question to the correct moving average set you calculated. This demonstrates the smoothing effect, which will be discussed later in this topic. So when would you use moving average charts? They actually have several applications. For instance, they're often used when you need to quickly identify small shifts in the process mean that probably would go undetected by a regular control chart. This is also helpful when data is collected periodically or when it takes a lot of time to produce a single item. Even with a small number of individual data points, you can detect changes in the process mean. This is because of the moving average chart's sensitivity to changes in the means of the small runs. Moving average charts can also enable short-term forecasting by smoothing the data. A moving average plot is smoother than a plot of individual points. Short-term fluctuations are smoothed and longer-term cycles are highlighted. Smoothing the data more clearly shows the trajectory the data is on. In other words, if the chart shows points starting to drop, chances are there's a downward trend in the data. This might have been difficult to detect if individual points had been plotted instead of moving averages. Individual points would jump around more randomly. Finally, moving average charts can be used to dampen the effects of overcontrol by smoothing the data. If you set your control limits too tightly, smoothing the data means that fewer points will appear out of control. To demonstrate the smoothing effect, consider this example. A control chart has values that appear out of control, that is, some of the points fall beyond the 3 sigma line. But on a moving average version, these points are smoothed by lumping them in with adjacent points and taking the average. The points no longer exceed the 3 sigma control limit line. This example demonstrates how the moving average chart helps smooth out data and dampen the effects of overcontrol. You can conclude that the process is actually within control limits. Here's a final point to note about using moving average charts. Interpreting these charts is somewhat different from interpreting other types of charts. This is because the subgroups aren't independent, and some of the analysis tests you apply to other control charts may lead to false conclusions on a moving average chart. When interpreting one of these charts, using caution is very important. Like moving average charts, short-run SPC charts are often used when data is collected infrequently. However, unlike moving average charts, which work best with data that is collected periodically, short-run SPC charts are best for data collected aperiodically. A short-run SPC chart is used in 2 situations. First, when the organization produces a low volume of outputs, and second, when the process itself only lasts a short time, providing a small amount of data that's insufficient to ensure a statistically reliable determination of process control. Short-run SPC charts are specifically designed to deal with these limitations and challenges. When you have infrequent or few data points, the short-run SPC chart sometimes omits setting control limits based on the data. Instead, it sets nominal or target values based on historical data. Short-run SPC charts have several other characteristics. You can actually use short-run SPC charts to plot observations of variables or attribute data for multiple parts of the same process stream on the same chart. You have to ensure that the parts are in the same process stream, but they can vary in size, shape, and material. To compare multiple parts with different characteristics, the short-run SPC chart codes or standardizes the data through arithmetical transformation. This involves subtracting the target or nominal value for each part from the observations for that part, which leaves you with a difference for each part that can be compared with the difference for other parts. An important requirement for short-run SPC charts is that variation between different parts included in a chart remains the same. This is called homogeneity of variance. If variance isn't homogeneous, you should further transform or standardize the data. If this doesn't work either, you should use standardized or common control charts. When would you use a short-run SPC chart? Here's an example. A manufacturer produces parts for different airplanes, and the Six Sigma team collects data infrequently and aperiodically. The weight of the different parts can only be meaningfully compared, for determining consistency of part weights, if the mean differences between part weights for different airplanes are first removed. You should also note that when you're creating attributes charts, you can only use standardized short-run charts. This is because the estimate of the variability of the process for attributes charts, proportion or rate for instance, is a function of the process average. Short-run SPC charts are quite often exploratory in purpose, and they can reveal various things about parts and processes. Consider an X-bar chart with 4 variables. What can it tell you? Variable D deviates the most from the center line. Variables B and C have negative deviations and are closer to the center line than variable D. Now, the chart has changed slightly. You can tell that, this time, variable D deviates the most from the center line. Variables B and C have the negative deviations for closer than variable D. The final point to make about short-run SPC charts involves control limits. Various approaches exist for setting control limits for short-run charts, and some of them are controversial. Nomenclatures and approaches differ, but there are sets of formulas available for calculating center lines and limits for short-run SPC charts that mirror each of the common control chart types: X-bar, R, P, NP, C, U, and MR. Sometimes you can't use conventional control charts for all processes, and you'll have to use specialized control charts. Two of these are moving average charts and short-run SPC charts. Moving average charts are often combined with moving range charts. To use one, you take a short run of the individual values and find the average and range of these. You then move over one step in the run and retake the average and range. They're used when you need to quickly identify small shifts in the process mean, to enable short-term forecasting by smoothing the data, and to dampen the effects of over-control by smoothing the data. Short-run SPC charts are best for data collected aperiodically. They're used in two situations: when the organization produces a low volume of outputs, and when the process itself only lasts a short time. Variation between different parts included in a chart remains the same. This is called homogeneity of variance. If variance isn't homogeneous, you should further transform or standardize the data. If this doesn't work either, you should use standardized or common control. You already know that every process has variation, and this variation can be divided into two categories: common cause variation and special cause variation. Common causes are those inherent to the process and not controllable by process operators. On the other hand, special causes of variation, sometimes called assignable causes, include unusual events the operator can remove or reduce, if identified and corrective measures taken. It's special cause variation that's at the root of out-of-control conditions. There are 6 major categories of causes. Choosing the wrong type of materials can have a negative effect on product quality. For instance, what if you purchased the lowest cost materials you could find? They might not be the best quality. Other causes include changes in the materials themselves, changes in suppliers, too much waste lying around your facility, and carelessness about mixing types of materials. To ensure your products are of high quality, you must have machines that are reliable and consistent. A machine that breaks down frequently will have a negative impact on product quality. Other examples of causes in this category include poorly designed equipment, broken or worn tools, and general deterioration. The things employees do can also have an impact on product quality. When operators are sloppy or careless, waste can occur. Other causes in the manpower category could include worker fatigue, poor attitudes toward work, a lack of proper supervision, or ignorance of how to perform tasks. How employees perform their tasks can impact product quality. It's important, for instance, that all operators follow the same standards and guidelines. Production methods, whether they're new or just poor, can also be a cause. The way processes are measured can also impact product quality. For instance, using different or unsuitable testing methods can result in a product that doesn't meet standards. Mother Nature is often used as the 6th M to describe environmental factors. Examples of environmental factors that can have an impact on product quality include the temperature or humidity in a factory, the amount of dust in the air of a warehouse, and even the amount of ambient noise. You can access the job aid Categories of Causes after this video to review these categories and their examples. Ideally, a process will only exhibit common cause variation. In other words, you want a process that only has random variation that's not due to any special causes. This process would be considered in control. Control charts are used to help explain if and where special cause variation exists. The main point of control chart analysis involves interpreting the pattern and location of plotted data on control charts. This will help explain whether or not any special cause variation exists in the process. There are 2 important things to remember when you're analyzing control charts. First, an out-of-control state can be detected in points outside of control limits or in irregular patterns. Second, if you use variable control charts, such as X-bar and R, X-bar and S, and IMR charts, there will be 2 charts involved. An out-of-control state demonstrated in either chart indicates the process is out of control. You'll recall control charts are divided into 6 zones. These zones are the regions formed by plus or minus 1, 2, and 3 standard deviations from the central line. You set control limits at the 2 extremes of this range. Assuming a normal distribution, it's expected an in-control process will have about 68% of points falling within 1 sigma deviation, or SD, of the mean. This is zone C. It's expected that 95% will fall within 2 SDs, which is zone B, and 99.7% within 3 SDs. The 2 sigma lines, beyond which you find zone A, are sometimes referred to as the warning limits. In a natural or in-control pattern, the fluctuations of the data points are consistent and predictable, and all data points fall within the control limits. As you know, control chart analysis involves taking a run, or a length of plotted points, and analyzing these for warning signals or patterns that indicate an out-of-control process. You should be sure to check the range or standard deviation chart first if you're using a 2-part control chart. Certain visual signs should set off alarms about the state of a process because they indicate trends in the data. In this course, the term trend will refer to all visual signals that might indicate a potential problem with the process. Theorists and sources differ on what constitutes an alarm-worthy trend. You can apply several important rules to test for trends. Let's review 6 of them. A control chart with points outside the UCL or LCL fails the test and indicates the presence of special cause variation. This trend is commonly known as freaks. A run of 9 or more data points in a row on the same side of the center line fails the test. When this happens, it's known as a shift in the process mean, where the process moves up or down and stays there for a period. A violation of this rule indicates the presence of special cause variation. This trend is commonly known as process shift up or down. A run of 6 or more data points in a row in steadily increasing or decreasing order fails the test. This trend is commonly known as process drift up or down. Then, a control chart with 14 or more data points in a row alternating up and down fails the test. This trend is commonly known as systematic variation. A control chart that has patterns with 15 or more data points in a row within 1 sigma of the center line clustered around the center line fails the test. This trend is commonly known as stratification. And finally, a control chart demonstrating any other visible recurring patterns or cycles fails the test. Cycles often show up because of the nature of the process and can include hour of the day of the week, or month of the year. They're often caused when you modify the process inputs or methods following a regular schedule. This trend is commonly known as recurring cycles. What can these tests tell you? It's generally safe to assume that the process is out of control when any one of these rules are violated. Or, in other words, when any of these tests fail. In a real-life situation, there may be trends that don't appear to violate the rules discussed earlier in the topic, but they still need to be considered alarm signals. In fact, in many Six Sigma situations, control charts don't map to any of these broad rules, but still indicate visible signs of shift, drift, repetition, patterns, and stratification. Your job as a Six Sigma black belt is to dig deeper to find the possible causes and identify corrective measures. What if one or more of the trends you just learned about are present in the process? If this is the case, the data and control chart indicate that the process is out of control. You'll have to analyze possible causes. It's not enough to identify trends on a control chart. Once you've created the chart, you have to respond to the trends that exist. Each of the patterns can indicate specific problems, and you have to take the proper corrective action. As you're analyzing control charts, keep in mind that the tests for interpreting X-bar and R charts apply equally to attributes charts as well. For instance, P, NP, C, and U charts. You should note that all the trends and rules discussed so far are applicable to all attributes and variables charts. You can access the job aid Causes of Control Chart Trends after this video to review the content about responding to each of the 6 trends. The corrective actions that you apply when you discover trends will be very specific to the business or production context that you're in. Different situations will require different actions, and it's impossible to cover all the possibilities. However, this topic will demonstrate a manufacturing scenario dealing mainly with X-bar and R charts. This will exemplify how a Six Sigma team draws conclusions from a control chart by analyzing the possible causes and taking corrective measures. Imagine that you're the Six Sigma black belt at a company that manufactures cutting tools and machinery. You've come across control charts with specific trends for many of your product's key characteristics. For instance, weight of the blades, diameter of drill heads, thickness of slitting saws, RPM of drills, weight of saws, and the thickness of blades. Keep in mind that this case study is specific to the X-bar and R chart. The first of the control charts pertains to the weight of the blades. You notice that the chart involves changes in data that indicate a process drift up or down. This trend is characterized by the range increasing about 3 times. Even though the points on the range chart go up and down, there's still an apparent overall trend. You might find that there aren't any points that are out of control, and the average chart demonstrates large shifts but remains centered. You need to analyze and respond to this trend. Analysis of the charts may reveal some valuable information. For instance, in an X-bar chart, an upward drift in tool diameter could indicate machine wear or deteriorating maintenance. If it's going down, the operator may have made some over-adjustments to the machine. Ideally, no downward or upward drift in the process characteristic is desirable. The control chart exhibits a violation of Rule 3, that a control chart showing a run of 6 or more data points in a row fails the test. How could you respond to this trend? There are several examples of corrective actions. You could maintain a machine that's wearing down, find out why the operator is having problems, train the operator, or repair a broken tool. The second control chart pertains to the diameter of the drill heads, and the trend you notice is a potential process shift. Both of the charts show a shift over time, and the range chart appears to be in violation of Rule 2. When a shift occurs, the average and range shifts up or down over 9 or more data points. You might not find any points on the chart that are outside the control lines, but the average and range charts demonstrate shifts in the process average and range. This trend can have many causes, including new machinery or operators, and changes in materials or methods. You can take several corrective actions for a shift up or down. You can ensure your material supply is consistent, make sure operators use the same methods and instructions over a reasonable period of time, and check the calibration of the device used for measurements. The third control chart pertains to the thickness of the slitting saws, and the trend you notice involves frequent changes in the data, or systematic variation. The change in range is quick but also unpredictable. It can either be up or down on the control chart. This trend can be hard to detect when you're performing control chart analysis. There might not be any out-of-control points on the chart. Possible causes for this trend include over-control, differences in the methods used for testing, and using materials that are mixed or are of different qualities. You can take several corrective actions to respond to this trend. For instance, you could make sure the control limits are set at the correct levels, check the testing procedures, determine if inspections should be performed differently or occur more frequently, or standardize the materials used. The fourth control chart pertains to the RPM of the drills, and the trend you notice involves points that are too close to the center, or stratification. You might find that there aren't any points out of control. This trend can have many causes, including the control limits being incorrectly calculated, an employee who's not conducting regular checks, and the process improving since the last time the limits were calculated. How could you respond to this trend? There are several examples of corrective actions. You could ensure the checking procedure is being followed. You could also make sure employees are taking measurements properly and following procedures for rational subgrouping. The fifth control chart trend pertains to the weight of the saws, and the trend you notice involves points that are outside the limits. These freaks can occur for several reasons. For example, over-control or the use of a variety of materials of different quality can all contribute to this trend. You can take several corrective actions to respond to this trend. For instance, you could prevent operators from over-adjusting the process. An out-of-control process definitely requires adjustment, but sometimes the process may be adjusted unnecessarily when a false alarm occurs. Other corrective actions include making sure the variability in machines and operators is reduced to the minimum, and checking into any variation in materials. The sixth control chart trend pertains to the thickness of the blades, and the trend you notice involves recurring cycles in the plotted points. This can be caused by physical factors such as humidity or temperature, operator fatigue, their periodic rotation, and seasonal effects of incoming material are other potential causes. How could you respond to this trend? There are several examples of corrective actions. You could adjust the environmental factors if it's possible, regularly maintain your equipment, and change operators when signs of fatigue are evident. You could also regularly inspect the input material to ensure its homogeneity. There are other rules that professional bodies and institutions suggest which haven't been covered here. For instance, early warning signs. This trend involves 2 out of 3 points more than 2 sigma from the center line on the same side, or 4 out of 5 points more than 1 sigma from the center line on the same side. You should be aware of these because both may warn you of a potential process shift. As was previously mentioned, the interpretation and responses discussed in this topic can be applied to other control charts: X-bar, IMR, C, U, NP, and P. The trends can be found in all kinds of control charts, and the corrective actions you take will depend on the situation. You've learned about potential corrective actions in a manufacturing context, but you should also think about what actions you might take to address trends in a different kind of process. You should keep in mind that interpreting moving average charts is slightly different from interpreting other types of charts. This is because the subgroups aren't independent and the moving averages are smoothed. Even though it's important to proceed with caution when interpreting moving average charts, the generally recognized tests are the same as for other charts. These include checking for points outside the UCL and LCL, runs of 9 or more data points in a row on the same side of the center line, runs of 6 or more data points in a row in steadily increasing or decreasing order, and 14 data points in a row alternating up and down. Control chart analysis involves interpreting the pattern and location of plotted data on control charts to explain if and where special cause variation exists. When you're analyzing control charts, you should keep in mind that an out-of-control state can be detected in points outside of control limits or in irregular patterns. Also, if you use variable control charts, an out-of-control state demonstrated in either the X or the R chart indicates that the process is out of control. Certain trends should set off alarms about the state of a process. These include points outside of the UCL or LCL, runs of 9 or more data points in a row on the same side of the center line, runs of 6 or more data points in a row in steadily increasing or decreasing order, 14 data points in a row alternating up and down, patterns with 15 or more data points in a row within 1 sigma of the center line, and repeating patterns or cycles. If these trends are present, you'll have to analyze possible causes. Each of the patterns can indicate specific problems, and you have to take the proper corrective action. The trends can be found in all kinds of control charts, and the corrective actions you take will depend on the... People think of a manufacturing plant as a smooth-flowing entity with complex processes and sub-processes that merge seamlessly to deliver each stage of throughput. But what happens if machines are unpredictable? When one piece of equipment goes down, it can directly affect output. Equipment maintenance ensures that every machine in a production process remains available to perform its required task and production is not interrupted. Clearly, this plays a vital role in the control phase of a Six Sigma project. Wherever mechanical devices are used in service and manufacturing organizations, their working state directly impacts process control. Even subtle deterioration in production equipment performance can affect process output, often in ways you might not suspect. Total Productive Maintenance, also known as TPM, is a proactive equipment maintenance program that has always been a part of lean manufacturing. It is now widely used as a Six Sigma control phase tool. A total or comprehensive approach to maintenance can be used to sustain improvements and control the improved Six Sigma process by removing deficiencies from the machines to minimize or eliminate defects and downtime. Generally, organizations are reluctant to change the way things have always been done. Equipment maintenance and reliability are often viewed with a complacent, fix-it-when-it's-broken attitude. In this mindset, machines are expected to fail, and maintenance is more reactive than proactive. Spare parts are commonly stored in large inventories. The lifespan of parts may be decreased due to poor maintenance, and operators may ignore signs that could warn of potential malfunction. What if every business waited for equipment to falter or fail completely before taking action? In some cases, the impact would be costs to the company due to failure and downtime, as well as additional costs that drive up prices to the consumer. But in the aircraft maintenance industry, there's zero tolerance for failure, since equipment maintenance is a concern to passengers, regulatory agencies, and the airline itself. From those who perform aircraft maintenance to those who supply the parts and materials used on the job, a high degree of discipline and certification is required. Every process and step has documentation, and procedures are extremely specific. There is double and triple verification for each and every critical process, as well as audits by regulatory bodies and third parties to ensure compliance. So, even with tens of thousands of takeoffs and landings every day, this proactive approach to maintenance makes crashes due to equipment failure extremely rare. TPM is a proactive approach with the goal of removing deficiencies from machines to minimize or eliminate defects and downtime. It's a unique concept for maintenance programs that aims to prevent deterioration and reduce maintenance. It's not just about fixing equipment. TPM extends beyond simple preventive maintenance and includes comprehensive management of people, processes, systems, and the environment. TPM promotes coordinated group activities for greater equipment effectiveness. Such activities include operators sharing responsibility for routine equipment inspection, cleaning, maintenance, and minor repairs. The goal of TPM is to increase production while also boosting workers' job satisfaction and morale. Employees are empowered to take ownership and pride in maximizing the life and use of the equipment they operate and reducing costs in the process. They then have end-to-end accountability. TPM focuses on maintenance as a necessary and vital component of the business. No longer seen as an activity that cuts into profits, TPM is used to keep emergency and unscheduled maintenance to a minimum. A TPM program has three major features. The first is a system of productive maintenance to maximize the useful life of equipment. The second is the goal to maximize equipment use and effectiveness. And the third feature is that it works through sharing responsibility for routine inspection, cleaning, maintenance, and minor repairs. The total in total productive maintenance encompasses total efficiency and effective use of equipment. This is a total package for both downtime prevention and maintenance maintainability, and, perhaps most importantly, the total participation of employees. The goal of total efficiency and effectiveness of equipment requires the elimination of failures, defects, rework, waste, and any losses from equipment-related operations. A total package for both downtime prevention and maintainability has a goal of zero breakdowns and zero defects. Some businesses that have instituted TPM have had a 2% reduction in original breakdowns that resulted in a 90% reduction in rework. Total participation of employees means that all employees must be involved in a TPM program, from leaders to operators. Having a TPM program doesn't mean there's no professional maintenance staff. They still perform major maintenance activities and coach operators in the routine and minor activities. A Japanese plant engineering study found that even in clean plants, more than half of machine breakdowns are caused by dirt and looseness. Cleanliness and tightness should be key in any system to reduce breakdowns, but maintenance workers can't be everywhere at all times. Or can they? A TPM program focuses on a guiding principle of shared responsibility for maintenance. Operators are key players, supported technically by skilled maintenance workers, so in effect, maintenance workers can be everywhere at once. In support of this principle of shared responsibility, TPM includes 3 points. The first point addresses the involvement of employees at every level and across departments. The second point integrates autonomous maintenance into the daily routine of operators, and the third point incorporates company-led small group activities to monitor the use of TPM throughout the organization. Without leadership, even the best maintenance operators and reliability engineers can't achieve total plant reliability. TPM requires the involvement of employees at every level and across departments, from top management all the way to frontline employees. Cross-functional teams from all departments are included, from production, product, and process development across the board to marketing and administration. Of course, the professional maintenance staff still has responsibilities, but employee participation in the enterprise is comprehensive. This employee involvement is a key characteristic of TPM that makes it unique. Autonomous maintenance includes any activities operators perform that have maintenance functions and are intended to keep the plant operating efficiently. Operators perform certain equipment maintenance activities which are closely linked to the daily operation of equipment. The focus of the operating team is on cleaning, inspecting, lubricating, monitoring, and other such essential daily tasks traditionally within the domain of the maintenance department. In a TPM system, operators should have a sense of ownership, protecting and caring for their machines. And maintenance personnel can then spend more time on value-added activity and technical repairs, instead of constantly fighting fires. Small groups consist of employees who continually control and improve the quality of their work, products, and services. These small groups operate autonomously, tap members' creativity, and promote mutual development through training. Company-led small group activities set up and monitor the use of TPM within the company. They facilitate a top-down promotion of company TPM activities, as well as the bottom-up ideas for the production floor's activities. The way to achieve zero losses is by overlapping small group activities to identify causes of failure or possible plant and equipment modifications. For example, a manufacturer of plastic injection and rubber moldings for the home appliance industry had neglected preventive maintenance. The company was in the classic maintain it when it fails situation. To improve plant availability, product quality, and resource utilization, management decided to implement TPM. Let's look at examples of how the manufacturing plant featured shared responsibility in its TPM program. The TPM committee emphasized the most important change of all, that the new plan was to be carried out through the positive participation of all concerned across departments at every level. A suggestion from a small group for reducing part replacement time on molding machines was implemented as a joint project by engineers from the parts, maintenance, and production departments. Over a period of 3 years, this effort has reduced the replacement time from 59 minutes to 50 seconds. Operators now carry out mandatory daily and weekly inspections as part of autonomous maintenance. Without interrupting production work, operators can easily prevent breakdowns, predict failures, and prolong equipment life as they become more familiar with the machinery they use. Operators know what to do to keep machines in normal operating condition by lubricating them regularly, monitoring vital signs, and recording abnormalities. They also know what to do to get the machine back online when something goes wrong. The company expended considerable effort into improving the plan for ease of machine condition monitoring, including creating small groups within and between departments. Group activities are overlapped to promote a closer working relationship between maintenance workers and plant operators, encouraging operators to become equipment conscious through focused training. The small groups successfully helped in this training, as operators learned what constituted normal and abnormal operation and what to listen for to detect potential problems before they occurred. TPM is based on a zero-loss concept. This concept will allow you to achieve high reliability and flexibility of equipment. It also helps to reduce costs by minimizing wastage of manpower, raw material, energy, consumables, and so forth. TPM is accomplished through 4 specific objectives. They are zero breakdowns, zero defects, eliminating failures and waste due to equipment-related operations, reducing emergency and unscheduled maintenance events to a minimum. There are 6 big losses that contribute negatively to equipment effectiveness. These are equipment failure, setup and adjustment time, machine idling and minor stoppages, reduced speed, process defects, and reduced yield. Equipment failures result in downtime for repairs. Breakdowns cause a loss of time, resulting in lower productivity. They also cause quality losses from defective products. Costs associated with equipment failure include downtime and its resulting lost production opportunities and yields, as well as straightforward costs for labor and spare parts. Setup and adjustment losses come from equipment changes. They result in lost production yields that occur during product changeovers, shift changes, or other changes in operating conditions. Idling and minor stoppages can be caused by defective sensors, conveyor jamming, and so forth, which can result in slowdowns and losses. Frequent production downtimes can range from 0 to 10 minutes in length, and these are difficult to record manually. As a result, such losses are usually hidden from efficiency reports, but can cause substantial equipment downtime and lost production opportunities. The differences between designed and actual operating speeds result in losses from reduced speed. Productivity losses occur when equipment has to be slowed down to prevent quality defects or minor stoppages. In most cases, these losses aren't recorded since the equipment continues to operate, though they may directly impact overall equipment effectiveness, or OEE. Process defects produce scrap and quality defects. Process defects cause off-spec production and defects due to equipment malfunction or poor performance. This can lead to output that has to be reworked or scrapped as waste. Yield losses reflect wasted raw materials associated with rejects and scrap. Reduced yield losses typically are linked to machine startups, changeovers, equipment limitations, and poor product design. Each of the 6 losses have their respective goals. The goal for equipment failure is 0 breakdown losses. The goal for setup and adjustment losses is to keep such changes under 10 minutes. The goal for idling and minor stoppages is 0 losses. The goal for reduced speed is 0 speed losses. The goal for process defects is 0 quality defect losses. The goal for reduced yield is to minimize yield losses. Eradicating or minimizing the 6 losses can dramatically improve operating conditions in your manufacturing plant. After all, losses such as equipment downtime can bring a lean manufacturing operation to a complete standstill. The failure of equipment at one step of a process can strangle the flow entirely, halting all the steps before and after it as well. When the TPM philosophy is properly integrated in a company, the result is improved equipment reliability, with concurrent increases in productivity, quality, and plant capacity. These changes are aided by improving employee attitudes and providing a supporting work environment. This results in higher skilled workers who feel ownership of their equipment and process throughput. Properly integrating TPM will result in organizational benefits that are comprehensive. These include increased productivity and efficiency through improved worker and equipment utilization, a reduction of costs and inventory, and a reduction of accidents and pollution. It also includes increased employee morale through a sense of ownership, mutual goals, shared knowledge and experience, a collaborative work environment, and an enhancement of employee skills. Unexpected equipment downtime can destroy a business. Total Productive Maintenance, or TPM, is a proactive approach that emphasizes shared responsibility and focuses on preventing losses before they occur. With proper training, autonomous maintenance, which is a key aspect of TPM, empowers workers to take care of the equipment and machines they work with. The goal of TPM is the elimination of losses, including equipment breakdowns, idling and minor stoppages, defects and rework, and reduced speed, and the minimization of setup and yield losses. The implementation of TPM leads to improved utilization of production assets and As firms introduce Total Productive Maintenance, or TPM, into their organizations, it is key to have maintenance and reliability as a core business strategy. Many of them have the ultimate goal of capturing the Japan Institute of Plant Maintenance, or JIPM award. Winners for this annual Preventive Maintenance Award are chosen through preliminary assessments, document assessments, and a final on-site assessment. The prize is so sought after because winning it really reveals something about how successfully a company has implemented TPM. Many factors are considered to determine the winner: cost reduction, inventory reduction, accident reduction or elimination, control of pollution, and the overall work environment. Whether or not your goal is to win the JIPM award, taking steps to prepare and educate everyone in the organization before TPM activities are put into action is crucial. There are 12 recommended steps that form a path toward achieving prize-winning TPM results. Step 1 is to announce the organizational commitment to TPM. The support of management is critical in creating an environment that will support TPM's introduction. Without such support, the initiative can be met with skepticism and resistance. Step 2 includes launching a formal education program. Such a program needs to inform and educate everyone in the organization about TPM activities, its value to the company, and how important each person's contribution is. Operators are educated on a general level about the need for and approach to autonomous maintenance. In Step 3, you create an organizational infrastructure to support TPM. This includes creating a cross-functional team to promote and sustain TPM activities. To promote communication and ensure everyone works toward the same goals, the team should include members from every tier of the organization. A project steering committee, for instance, reports directly to the executive sponsor, through whom all issues facing the project team are resolved. Step 4 involves setting basic TPM policies and quantifiable goals. This includes analyzing the existing conditions and establishing realistic goals. In Step 5, you outline a detailed master deployment plan. This is a plan that identifies what resources will be needed and when. Step 6 is the official TPM kickoff that launches the implementation process. Step 7 is to improve the effectiveness of each piece of equipment. Project teams analyze the equipment and make the necessary improvements. In Step 8, you develop an autonomous maintenance program for operators. Routine cleaning and inspection of equipment by operators will help stabilize conditions and slow deterioration. Step 9 involves developing a planned or preventive maintenance program. A schedule for preventive maintenance is developed for each piece of equipment. In Step 10, training is carried out to improve operation and maintenance skills. This step focuses on the employees directly involved in operating and maintaining specific equipment. Step 11 is to develop an early equipment management program. In this step, you apply preventive maintenance principles during the design process of equipment. Finally, in Step 12, you implement TPM. But things don't end there. Just as in any Six Sigma initiative, an organization has to develop a mindset and a culture that supports continuous improvement. Let's look at an example where a bearing manufacturing company has a problem. Orders are being delayed. Customers want shorter lead times and cost reductions. Emergency work orders take up about 80% of maintenance hours. The first step is implemented using the company newsletter, Bearings Now, to discuss top management's commitment to TPM. Next, in Step 2, the company educates employees through organization-wide communication programs. These programs include detailed and intensive educational sessions about TPM. Then, in Step 3, management organizes every functional level into small groups to promote TPM. In Step 4, the company sets goals using the SMART technique. Management makes sure the goals are specific, measurable, attainable, realistic, and time-based. Next, in Step 5, a master deployment plan is developed that details what resources will be needed for training, equipment restoration and improvements, maintenance management systems, and new technologies. In Step 6, the company is ready to hold the TPM kickoff meeting, which is the start of the serious work. After holding its TPM kickoff meeting, the bearing manufacturing company is ready to tackle the last 6 steps. In Step 7, project teams are formed to analyze every piece of equipment with an eye to improve effectiveness and to prioritize the team's efforts for maximum results. Next, in Step 8, the equipment operators are trained in the daily maintenance requirements of the bearing machinery. In Step 9, the company develops a maintenance program, and the maintenance department starts on these scheduled activities. Members of the maintenance department teach and guide operators by providing training, advice, and equipment information to the project teams in Step 10. As new equipment is designed, early equipment management programs are developed in Step 11 to ensure that the equipment is ready for production through evaluation, validation, and improvement. Last but not least, in Step 12, the company is ready to implement TPM and aims for perfection. Continuous improvement milestones are set up to ensure success. 10 months after implementing TPM, the bearing manufacturing company records a 78% decrease in the number of unplanned maintenance hours. The company's management attributes the remarkable success to a hardworking and dedicated maintenance team, and to the implementation of its TPM program. During and after the implementation phase, TPM is first and foremost a team-based approach. Small groups and the activities they undertake are critical to TPM, since one of the basic principles is that operators and others in daily contact with equipment are the first line of defense against unplanned equipment downtime. Integrated teams of operators and maintainers use their knowledge and familiarity with operating conditions to predict and prevent breakdowns and other equipment-related losses. These small groups are teams that work together, care about their work, and are committed to team success. Having small groups undertake work that involves overlapping functions is at the heart of TPM. A department supervisor often has the role of team leader, and activities such as equipment cleaning, lubrication, bolting, and inspection are performed as small group activities. In fact, the use of small cross-functional groups is a distinct feature of TPM. Operators and maintainers work together toward the same goals with common performance measures and methods. But a team doesn't spring into being fully formed and completely functional. Teams typically progress through 4 stages: member self-development, group improvement, problem-solving, and autonomous management. The self-development stage is one of team member learning. Education and training is a fundamental improvement activity of TPM. Member self-development allows for maximum team member flexibility, efficiency, and job satisfaction, whether team members are managers, maintenance staff, team leaders, or equipment operators. The group improvement stage is when group improvement activities are undertaken and fulfilled. Small groups tackle the job of maintenance prevention when the goal is to minimize the amount of maintenance intervention while supporting overall plant or operational goals. To achieve these ends, teams use standard operating procedures, along with systematic analysis and treatment of equipment failures or other abnormalities. In the problem-solving stage, the team begins to actively select issues to address. The TPM approach of decentralizing decision-making and empowering employees helps small groups to solve problems with knowledge and confidence. It also helps them to be team players who know when and where to ask for help. In the autonomous management stage, the team identifies high-level goals and manages work independently. In TPM, the teams of operators and maintainers are responsible for decisions they make. Self-organized teams bring out the best in people and enhance productivity with superior results. This example illustrates how a solar panel manufacturer handled the development of small groups during its TPM implementation. As part of the new plant-oriented maintenance initiative, the plant operators are now expected to maintain the normal operating conditions of machinery. Small group teams were formed to implement these actions and to promote a closer relationship between maintenance workers and operators. The first stage of small group development is that of member self-development. The challenge was to change operators' attitudes toward the maintenance department from "I break it, you fix it" to "I maintain my own equipment." Because team members put considerable effort into understanding their machines, attitudes changed from operating without thought of maintenance to feelings of ownership and responsibility. The second stage is to carry out group improvement activities. Operators took what they learned about maintaining their own equipment and began to carry out inspection and cleaning routines, perform simple maintenance tasks, and assist maintenance workers. The third stage is the problem-solving stage. Here, the groups started to actively select problems to solve. Using problem definition tools, such as flow charting and Pareto diagrams, teams developed solutions. The teams reached decisions about the problems through consensus and weighted factor evaluations. The fourth and final stage of small group development is that of autonomous management. Now the teams are able to choose what high-level goals to work toward, and they can manage their work independently. Teams have learned to use automated tools, such as computerized maintenance and materials management systems, to help them. Maintenance and reliability as a core business strategy is key to a successful TPM implementation. Implementing TPM using 12 steps will start you on the road to zero breakdowns. But no matter where you are in the implementation process, teams and their small group activities are key to maximizing flexibility and capability. The teams need to develop to the stage of operating autonomously in order to support overall plant or operational goals. If workers don't have clear or detailed instructions, what happens? Targets aren't met, and production results vary by process or operator. Lack of information about process status, performance, targets, or issues can derail improvement initiatives. Everyone on the job, from management to operators, needs clear information about such things as order status, product quality, lead times, customer demand, and costs. Humans receive real-time information from the environment through their sensory systems of vision, hearing, touch, and smell. The majority of people, though, rely on vision the most. Vision affords the greatest capacity for information receiving and processing. Visual controls leverage human sensory systems for ensuring controls or guiding actions. They provide a picture of what's happening in the workplace, allow for immediate feedback, and inform any necessary actions. At a workplace, visual controls and standardized visual communication are used in every part of the facility. Visual communication provides clear and self-explanatory clues to workers about operations, job performance, goal accomplishment, and expectations. Visual controls use signs like cards, labels, color-coded markings, and other tactics to ensure workers have the right information at the right time. In a visual workplace, employees have access to the information they need where and when they need it. A visual workplace is made up of two main areas. Visual displays impart information and data to employees in the area. Such displays make work areas user-friendly by answering questions, identifying equipment, materials, and locations, describing actions and procedures, and providing safety warnings. Labels and signs are displays that communicate needed information at the point where it's needed. Visual controls actually control or guide actions. Visual controls give management and workers a visible manifestation of what's happening at any moment, allowing for immediate feedback about the workplace's condition. Visual controls include production boards, schedule boards, tool boards, Jidoka devices, and Kanban cards. Visual controls can illuminate the condition of workplace safety, production throughput, material flow, quality metrics, or other information. As such, visual controls is used as an umbrella term encompassing visual displays as well. Consider the following example of how a hospital uses visual communication. Visual displays in the hospital include large whiteboard charts that show the operating room schedules and attendance. It's clear at a glance who is on duty, who is incoming, and when a substitute has to be called in. Visual controls include color-coded painted dots and signs on the floors. These dots guide workers and patients to the correct exits and departments in the hospital. Sharing information through visual tools helps keep operations running smoothly and safely, since the tools provide data such as process metrics, work instructions, and general workplace information. Visual controls enable anyone in the environment to accurately and effectively assess at a glance the condition and performance of the process in a workplace. The benefits of visual controls are that they increase employee involvement and motivation, keep communication open, improve quality and productivity, and allow for a faster decision-making process. Some visual control strategies encompass both displays and control actions. For example, when a grocery store turns on the aisle light that indicates an open line for cashiers, it provides information to management, workers, and customers, and also guides and controls the checkout process flow. The same is true of any ticket system where the number being served is displayed on an LED screen, such as in a bank or delicatessen. These are all visual aids that guide activities in the workplace. Visual controls help employees improve processes, understand their roles, and contribute to the success of the corporation as waste is reduced at all levels. The three basic goals fulfilled by visual controls are to make problems visible, help workers and management stay in direct contact with the workplace, and clarify targets for improvement. One visual control tool used to make problems visible is Jidoka. Jidoka is a device that stops a machine or notifies a human to when a defective part is produced. It's a form of automation, which is an automation that has human elements. A Jidoka system has machinery that automatically inspects each produced item. If a defect is detected, production is stopped and a human is notified. The Jidoka system empowers workers as thinkers and gives them the right to stop the production line if necessary. Some shutdown devices used in a Jidoka system include signaling solutions, panel mount alarms, LED round beacons, hazardous location signaling, and safety relays. For example, in a metal manufacturing plant using a Jidoka system, a red light comes on above a machine that heats up aluminum when the temperature drops below acceptable levels. When such equipment malfunction occurs, the light indicates a problem. Then, the operator or maintenance personnel responds to find the source of the problem to resolve it. A machine that is stopped is an indication of a problem that must be fixed, and either the light or the stopped machine makes problems visible at a glance. Another goal of visual controls is to help workers and management stay in direct contact with the workplace. A visual workplace has many ways to do this. Visual information systems provide employees with simple information about the performance of procedures and processes. Signs, labels, painted floor sections indicating specific areas or activities, tool boards, indicator lights, and many more strategies also visually supply information about the workplace. For example, Kanban systems can provide material control cards to control the flow of production and inventory. Audio signals in the factory are another way to help workers maintain contact with what is going on in the workplace, for example. Audio signals can indicate malfunctioning equipment, and sound warnings can alert people prior to the start of a machine operation or transport vehicles backing up, among other things. Let's consider the following example. Before visual controls were implemented at an air compressor company, workspaces were cluttered and disorganized. Nothing on the production floor had a dedicated location. From work in process to tools, everything was placed in any location in the work area. Everyone wasted time verifying and looking for parts. Tools were misplaced or were difficult to find, and supervisors commonly didn't know the operational status of equipment. Now let's look at an additional example. After setting up visual controls, everything changed at the air compressor factory. Tool boards were constructed to hold or mark the place for the tools required at each workstation. Tool boards now visually convey two pieces of information: where the tool belongs and whether the tool is missing. It's now clear that if a tool isn't in its spot, it's either being used or a replacement is needed for the process to keep operating effectively. This simple visual indicator is a significant time saver, eliminating the need to search through toolboxes, other work areas, tool drawers, or cabinets. The part system received the same type of overhaul, and all signage was standardized. Now, everyone at the plant can easily stay in contact with the workplace. Another way to help employees stay in contact with the workplace is through the use of visual production controls. These generally include the posting of daily production data, maintenance items, or quality problems for everyone to see and understand. Before the start of a shift, a department supervisor might use the boards to discuss the daily planned activities and any specific problems. Managers and executives walking through the plant can use visual control boards to estimate progress in the various departments. Various items can be displayed on such boards. For example, quality issues and machine downtime, training records and cost reductions, trend charts including safety trends, total productive maintenance and 5S activities, productivity and delivery information, and checklists and standardized work instructions. A parts manufacturer simplifies its production scheduling with visual indicators. Instead of generating paperwork, supervisors use easy-to-grasp signs to trigger production processes. A scheduling board, also known as a production trigger board, is used as a visual indicator. The simple chart is filled in with X's as a product is consumed. When the filled-in chart areas reach a certain height, operators are authorized to produce more parts. Everyone in the area can quickly visualize part consumption and production status. The third goal of visual controls is to clarify targets for improvement. Measurements track the progress toward planned goals, but if workers don't have access to the information, they can't adjust their behaviors to help reach those goals. A visual workplace excels at providing information that will help workers see where they stand in meeting their targets. Visual performance measurement summarizes the information that keeps operators in touch with their targets. Status boards, indicators, quality control charts, and check sheets can provide the strategy and the means of conveying this type of information. Additional information that can clarify targets for improvement include weekly data, monthly trend lines, and improvement plan information. Visual information can also aid improvement efforts by helping to prevent mistakes. Color coding is often used to prevent errors. Shaded pie slices on a dial gauge tell an operator the instant the needle leaves the safe range. Matching colors on labels or tools is another approach to aiding tool choice or part assembly. The goal of visual control in the control phase of Six Sigma DMAIC is to provide teams with the control tools and techniques that are simple yet effective in maintaining the improved processes and holding the gains that the Six Sigma project delivered in the earlier stages of DMAIC. By establishing a lean management system, visual controls can help enforce discipline among team members necessary in maintaining the quality and level of improved processes consistently and as a way of life. This lean management system can be maintained by using accountability. Processes that are charted should be actioned and misses followed up with the person responsible for them. Charts should be studied on a daily basis, and any hiccups that stall a project should be treated with importance. Examples of simple visual controls include hour-by-hour production tracking charts, late load logs, daily accountability boards, as well as visual control boards located in various areas of operation. While sophisticated information technology, or IT, tools have their benefits, such as computational accuracy and the ability to have information available simultaneously in numerous places, simple visual control tools are favored by the lean management system since they are seen as more beneficial. For instance, by using simple visual controls, current information can be displayed for everyone to see as it's updated on the floor. However, information updated via IT tools will only display the data last entered or when the last reporting was done, and only to the people sitting in front of the screen. The information derived using simple visual controls is more accurate, as it's usually displayed close to the area it relates to and not lost in interpretation. However, information displayed using IT tools may not always be as accurate, because the data isn't located close to the actual area it relates to, and is dependent on human judgment and precision of data entry. Information displayed via simple visual controls prompt inquiry. Any questions can be asked in real time and responded to immediately at the location of the control. If the answers result in the form being modified, this too can be done immediately. In the case of information displayed via IT tools, typically the only questions that can be addressed are those already designed into the report, and any resulting changes would need to be updated by IT, which is time-consuming. Simple visual controls are less intimidating than IT tools, especially if an individual is not well versed in technology. Additionally, simple controls allow individuals to take ownership by manually adding or updating information in their area, while IT tools often take information away from the area. When information is added or updated using simple visual controls, very little overhead is required because the data is updated by individuals already located in the area using inexpensive markers, highlighters, or pens. In contrast, updating information using IT tools is generally more expensive, as it requires specialized departments, software, and experts for managing and troubleshooting. As part of visual controls, the whole workplace has visual elements such as signs, labels, and color-coded markings to ensure that the process stays on track and delivers intended results. The goal is for everyone to be able to know what's going on, understand the process, see what might be out of place, and take corrective measures if required. Visual control tools help to maintain control over processes. Implementing visual controls makes problems visible, helps workers and management stay in direct contact with the workplace, and clarifies targets for improvement. Measures are numerical representations of reality. The more representative they are, the more useful the actions based on them are. Measurement is the cornerstone of Six Sigma improvement. The measure phase of Six Sigma's DMAIC methodology yields data that is used to validate observations and drive process improvement decision-making. Business decisions must be based on data that represents the true value of that which is being measured, so trustworthy measurements are a must. But data itself isn't necessarily information. You must analyze data before it has meaning, so the reliability of the measurement system is vital. The measurement system is the means by which things are measured, validated, and analyzed. After a process improvement is implemented, the control stage of the DMAIC methodology ensures that process and product characteristics are continually monitored. For your Six Sigma team to effectively monitor and control a process and sustain improvements, your measurement system must remain accurate. Various elements make up the measurement system, including people, standards, devices, environments, and methodologies. In a good measurement system, each element contributes to the system through interrelated data gathering activities while adding only minimally to the overall variation. A poor measurement system produces inaccurate, biased, or just plain irrelevant results. As you recall, measurement system analysis, or MSA, assesses whether a measurement system is measuring what it's supposed to and how well it's doing so. MSA determines how much of the total variation in a process is a result of measurement system error. Measurement system analysis qualifies a measurement system for use. MSA assesses three properties: accuracy, precision, and stability. In terms of measurement, accuracy is the degree of actuality. You determine a gauge, measurement tool, or measurement system's accuracy by determining how closely the results you get align with true or standard values. Precision is the degree of repeatability and reproducibility of the measurements. It describes the ability of a measurement system to show repeatable and reproducible results. Precision can be described by the standard error, standard deviation, or confidence interval. Stability is the measurement system's ability to be precise and accurate over time. Accuracy, precision, and stability of a measurement process are all established the same way, by repeatedly measuring and obtaining a specified standard value. You can access the MSA glossary after this video for a brief review of key MSA concepts. MSA measures the reliability of the measurement system by identifying what percentage of total variation results from the measurement system itself. An MSA during the measure phase can qualify the measurement system for use in an improvement initiative. But changes in the process, changes in customer specifications, or the development and use of new measuring devices may be reason enough to re-examine the way you measure. Measurement system reanalysis is an important component of the control phase of DMAIC. In addition to the more obvious reasons why a reanalysis of the measurement system might be required, a less obvious one is a successful improvement effort. If the improve phase of DMAIC has resulted in significant change to the process, the same measurement system may no longer be adequate, depending on the initial amount of variation in the measurement system and how much reduction in variation has occurred. Improved processes may require improved measurement systems to properly monitor and control them. If you fail to reassess your measurement system, it may indicate that your process is less capable than it really is. The total observed variation in a process is made up of process variation and measurement variation. Significantly reducing process variation through an improvement effort reduces the total observed variation. The measurement variation isn't affected, so the error from measurement becomes more significant. It represents a greater proportion of the total variation. Improving the resolution of a measurement system can reduce the proportion of total variation accounted for by measurement variation. The development of new measuring devices may be reason enough to re-examine your measurement system. Years ago, micrometers that measured to 1/1000th of an inch were the standard. Improvements in micrometer technology, combined with the need to tighten specifications, led to the development and use of more precise devices. As machining capability improved, micrometers with the ability to measure to within 1/10,000th of an inch were developed. Even more accurate instruments called supermicrometers have since been invented that measure to within 1/1,000,000th of an inch. By keeping up with customer demands and continually improving measurement systems, measurement variation can be kept under control. Different guidelines or rules of thumb have been developed over time as to how accurate a measurement system needs to be. The 1/10th or 10-to-1 rule is a common standard. It states that the measurement instrument needs an accuracy of 1/10th or 10% of the specification tolerance. Based on the 10-to-1 rule, given a part with a specification of 1 ± 0.5 centimeters, the measurement instrument must measure to within 0.05 centimeters. Other measurement standards use a 4-to-1 or 25% rule relative to the specification tolerance. Both rules have been subject to variations and different interpretations. Important factors in choosing the appropriate measurement rule are the cost and effort required to measure to the higher level. In some applications, achieving a 10-to-1 ratio is easily done. In others, though, achieving that level may require purchasing expensive equipment or may be entirely impossible. In those cases, the 4-to-1 rule may be the more practical choice. These rules of thumb have formed the basis of the standards and guidelines, such as those published by the International Standards Organization, or ISO, and in the Measurement Standards Analysis Reference Manual. These offer guidance on factors such as bias and reproducibility that indicate system accuracy and precision. Guidelines suggest that in an acceptable system, variation in measurement should account for no more than 25% of tolerance. This approach aligns nicely with the 4-to-1 rule. In a good system, variation in these factors accounts for no more than 10% of tolerance, as proposed by the 10-to-1 rule. Variation beyond 25% indicates a measurement system that is unacceptable and needs improvement. Some organizations consider 30% to be the upper limit. Comparing the measurement precision to the specification tolerance indicates how much of the total tolerance spread is accounted for by measurement error. But that doesn't indicate the amount of the total variation that is caused by measurement system variation. That requires a precision to total ratio. Let's explore how reducing process variation through process improvement affects the precision to total ratio. When the percentage accounted for by process variation is 85%, measurement variation makes up 15% of the total variation. When the amount accounted for by process variation is reduced to 75%, measurement variation makes up 25% of the total variation. When process variation's contribution is reduced to 35%, measurement variation makes up 65% of the total variation. The success of the improvement results in the measurement system being responsible for more of the variation than the process itself. When process variation is reduced and the measurement system remains the same, the measurement system may still be acceptable from a precision to tolerance point of view because tolerance doesn't change. But from a precision to total point of view, the measurement system's performance is diminished because the measurement error now accounts for a higher percentage of the total variation. At this point, the organization faces a business decision. It may decide that the measurement system requires improvement because it won't adequately detect further improvement. This may impact subsequent process improvement decisions. Measurement tools are also referred to as gauges. The term can refer to an actual physical tool, a standard, or a scale of measure. To assess the precision of a gauge or a measurement system, you can use a gauge repeatability and reproducibility study, or GR&R study. You will recall from your earlier Six Sigma experience that a GR&R study is used to initially qualify a measurement system for its intended use. In measurement system reanalysis, a GR&R study is used to ensure the measurement system used as a basis for improvement is still adequate for controlling the improved process. Measurement error, or gauge error, has two components, repeatability and reproducibility. Together, these two sources of variation should make up no more than 30% of the total variation. The calculations of a GR&R study are beyond the scope of this course and were covered earlier in the measure phase of the Black Belt curriculum. Repeatability is the variability that occurs when measurements are collected under identical conditions. Also known as equipment variation, or EV, repeatability is the inherent variation of the measurement instrument. Reproducibility is also known as appraiser variation. It describes whether two different operators can get the same measurement using the same gauge on the same part over a number of trials. Other studies can shed light on the effectiveness of a measurement system or tool. These include bias and linearity studies. Bias involves issues that are not directly related to the system being evaluated, but which cause misleading or inaccurate results. A measurement system's bias can be determined statistically by using the system to take a set of measurements, averaging the measurements, and subtracting the average from a reference value or standard. Linearity describes statistical consistency. It provides an indication of whether the bias associated with a measurement system is constant throughout the measurement range. You test a measurement system's linearity by plotting measurements taken against reference values or standards. You determine the best fit line and calculate the slope, intercept, and correlation values. You can access the content on measurement system studies after this video for a brief review about the different types of studies you should be familiar with from your previous Six Sigma experience. A third measurement system property to be reanalyzed is stability. Stability is the measurement instrument's capability to produce values within an acceptable range over time. Both short-term and long-term measurements are taken. X-bar and R control charts are then used to assess the gauge's statistical stability. When a measurement system is stable and in control, data values fall between the control limits. When performing stability studies, remember that correctly interpreting control charts is an art and requires study and experience. Although bias, linearity, and stability studies are important elements of measurement system analysis, the rest of the topic will focus on results from reproducibility and repeatability studies. GR&R results may change after process improvement. For example, say your Six Sigma team has implemented a process improvement for a machining process. A GR&R study was used to qualify the measurement system in the measure stage. System repeatability at the time was 0.0002 and reproducibility was 0.0006, so the system was considered to be excellent. Its precision to total ratio was 2.9%. Since that time, your team achieved a significant reduction in variation. Follow along to learn how things have changed. Now that the project has reached its goal, your team is reanalyzing the measurement system to find out if it's adequate for keeping the process in control. Due to the greatly reduced total variation resulting from the improvement effort, the precision to total ratio is found to be 31.8%, which is unacceptably high. The general rule of thumb to follow for the GR&R results is, if the precision to total ratio is less than or equal to 10%, the system is excellent. If it's less than or equal to 30%, it's acceptable. And if it's greater than 30%, the measurement system is unacceptable and needs improvement. If measurement system reanalysis results in precision to total or precision to tolerance values that are unacceptable, your team must decide whether to improve the system's measurement capability. Deciding the future of the measurement system is a business decision, where the team must weigh a number of factors. The team and the organization must assess the effects of factors such as implementation costs, further improvement plans, changing customer specifications, and altered use of the product. The team must consider cost as a factor when deciding whether to implement improvement to the measurement system. A one-time purchase of more sensitive gauges might argue for change, whereas a situation requiring extensive retraining might not. If further process improvements are planned, your team must consider whether the measurement system will be capable of detecting the ever finer measurements that may be required to maintain the process closer to target. As products are used, customer expectations may change. Consider the size and range of features originally offered for cell phones. Years after their introduction, smaller phones with audio, video, and internet performance that rival a computer's have become standard. Changing specifications alter the precision to tolerance ratio, which may put the current measurement system's performance beyond the acceptable range. Sometimes product uses change. For instance, high-resolution flat-screen televisions might come to be used as computer monitors. Due to this new use, higher resolution could be required. The measurement system might have to be improved to accommodate the higher DPI requirement. Regardless of how the various factors measure up, if the measurement system still performs well according to the precision to tolerance and precision to total ratios, then measurement system improvement is unnecessary. Improving the system may become necessary if further process improvements take place, at which point another reanalysis should be performed. Accurate measurements and meaningful data are the basis of Six Sigma improvement. Measurement system analysis, or MSA, is used to qualify a measurement system for initial use. In the control phase, a measurement system reanalysis is necessary to ensure the measurement system remains adequate for controlling the improved process. Changes to a measurement system's effectiveness may be due to several factors, including the successful completion of an improvement effort itself. Reducing the overall variation in a process makes the measurement system error's contribution to overall error relatively greater. Performing a measurement system reanalysis means taking a close look at the system's bias, linearity, stability, reproducibility, and repeatability to determine if improvement is needed. Teams also assess the effects of implementation costs, future improvement plans, changing customer specifications, and altered use of the product when deciding whether or not to improve. The purpose of a control plan is to provide a single, accessible, relevant, and timely written description of the data and mechanisms needed for process control. An inexperienced project manager at a manufacturing firm tried to monitor an electroplating process without a comprehensive control plan. There was confusion over how often to measure input and output results. Most departments took readings weekly, while one group thought monthly was the rule. As a result, the process drifted from target specifications, and the variation went undetected for almost 3 weeks. Control plans are so-called because they are used to carefully monitor key inputs and outputs of a process to ensure stability and maintain control. Control plans are one of the most important tools in Six Sigma, providing an organized approach to the design, selection, and implementation of quality control methods. A control plan organizes relevant information about a process or product in a meaningful and usable format by clearly outlining methods, actions, responsibilities, and expected outcomes. A control plan serves as a written summary of the actions required at each step of the control process. The plan documents and identifies variation in products and processes, and works to focus resources on customer requirements. A control plan is a central repository of relevant and timely data available to anyone involved in monitoring a process. The control plan improves communication and also acts as an historical document for the process. A control plan is a living document that reflects the current methods of control and measurement systems to be used. To stay current, it must be updated and maintained over time as designs, processes, measurement systems, and control methodologies are evaluated and improved. An effective control plan requires the use of valid measures. It details how, when, and from where the data will be gathered using those measures. The control plan must summarize the important information the Six Sigma team requires for making confident, data-driven improvement decisions, including critical characteristics of the process, process history and process improvements, prevention and reaction plans, frequency and method of measurement and evaluation to be used, roles and responsibilities of team members, and key indicators that will be used to monitor control of the process. The formatting and complexity of control plans vary greatly and depend on a variety of factors. The type of business determines in large part how a control plan is designed. Controlling a tangible manufactured product will involve entirely different measuring tools and techniques than measuring customer service results at a call center, or determining the speed of transactions for a retail provider at point of sale. Simple processes may require fewer control elements than more complex operations. Controlling the final measurement for a single part, for example, would probably require a different level of complexity than controlling a fully assembled jet engine. Even with the same product or process, different customers may have different needs and expectations that will require divergent control plans. Wholesale customers may place different emphasis on shipping and packing materials than retail customers of the same product. Some situations require hard, quantitative data, rigid controls, and highly detailed documentation. Others may rely on more subjective evaluations. Process scope and the financial and physical resources available to the Six Sigma team also affect how the plan is structured. There may not be time and money available for complex, detailed measurements to be taken frequently. Control plans are used and maintained throughout the product lifecycle, and each phase of production demands a different control plan to meet its unique challenges. For this reason, control plans are typically categorized into the following types: prototype, pre-launch, and production. The purpose, types, and basic elements of control plans should be familiar to you from your earlier Six Sigma experience. You can access the content on Control Plan Basics after this video to further review the characteristics of control plans. The control plan is a single comprehensive document that is readily accessible by all impacted groups. It's created jointly by the team under the leadership and guidance of the Six Sigma Black Belt, whose knowledge and expertise provide insight and value in developing a cohesive and executable plan. Once the plan is created, responsibility for implementing and maintaining it is passed to the process owner. A control plan may be created for a single part, a single process, or a family of processes. The process family or group may produce the same output or may have a varied output. While control plans vary greatly, 6 sections are particularly important to include. Process customers receive the output of the process. As their satisfaction is the goal of the process, it's especially important to include information on who they are. Different customers of the same process may have different requirements and expectations. Critical customer requirements, or CCRs, are the specific needs and expectations of the customer. These are the measurable requirements that determine the process specifications. Control plans detail the important indicators and metrics that will be used for comparing relative performance of the process. The various types of indicators predict whether the process is on track. Outcome indicators often involve qualitative data regarding the impact of the process and degree to which it meets critical customer requirements. Key Process Input Variables, or KPIVs, refer to the time, financial, and physical resources put into the process. In a similar way, Key Process Output Variables, also known as KPOVs, refer to important attributes of the goods or services produced by the process. Specifications are the specific measurable standards or targets required of each indicator. Key Process Input and Output Variables are selected for monitoring and control and documented in this part of the control plan. This section often contains the written technical requirements for the process. The current control plan section details the activities associated with continuous review. It includes the responsibilities and action items related to checking and responding, as well as details regarding the frequency and method of measurement and evaluation. The Notes and Miscellaneous section includes meeting minutes, procedures, comments, and any other relevant and potentially useful information not covered in the other sections of the control plan. Control plans summarize what's required to keep an improved process at its current level. They also ensure smooth transfer of responsibility from the project team to the process owner and help the team maintain performance. Another fundamental goal is to enable continuous improvement. There are 3 key improvement-related goals of a control plan: validating improvement, providing a knowledge repository, and finding new improvement opportunities. Validating improvement in Lean Six Sigma involves confirming that the recommended actions have improved the process. It's not good enough to just accept that the process is better. Measuring both process performance metrics and the measurement system itself before and after the solutions have been implemented and validating resulting improvements is paramount. For example, following implementation of solutions proposed by a Lean Six Sigma team at a technical support help desk, the variation in the resolution time was reduced from 3.2 minutes to 1.4 minutes, an improvement of over 56%. However, a measurement system reanalysis revealed that about 50% of this improvement was attributed to the improved measurement system and not the process. This led the Six Sigma team to believe that more process improvement opportunities still needed to be explored. You need to isolate the variation and resulting wastes in the process from those of the measurement system itself. There are various ways to carry out a validation. Basically, it's a case of assessing the process before and after. Sometimes presenting the positive results of the new process in comparison to the negative results of the old process can be used. Improvements should be tangible, quantifiable, and validated by the financial organization. Capturing learning, experience, and key outcomes from a Lean Six Sigma deployment is an essential endeavor for any organization to succeed in the long term. Typically, organizations collect, store, and access this wealth of information using a knowledge management software and a knowledge repository. A Lean Six Sigma knowledge repository may include areas such as deployment planning, project prioritization, resource deployment, team leadership activities, training, lessons learned, analyses, and improvement activities from the past and current projects and experts. Lean Six Sigma teams on future projects are encouraged to use this resource. This provides them a unique opportunity to tap the knowledge and experience from others directly or digitally and improve the efficiency of current improvement. Teams can use the Lean Six Sigma Knowledge Repository to access related ideas, analytical examples, templates, technological advice, and subject matter guidance by using keyword searches. Finding new improvement opportunities related directly or indirectly to the current improvement projects can be facilitated using control plans. There are a number of factors that contribute to teams' ability to find new improvement opportunities. Teams learn a lot during a project, not just regarding their own processes, but unrelated processes as well. A focused approach to look into and analyze a small part of business allows new insights and ideas to flow. Other factors include renewed process and business knowledge, new priorities, and a holistic view of organizational processes and their value to customers. Ideas that are suitable for quick strike improvement are usually sent directly to a supervisor or manager to be actioned. Ideas that require further research are logged in the macro charter and are prioritized against other planned improvement projects, including the current project. Another part of finding new improvement opportunities involves team members using the knowledge and methodology they attained in their project to kick off an improvement activity in their department. Control plans are one of the most important tools in Six Sigma. They provide a single, accessible, relevant, and timely written description of the data and mechanisms needed for process control. Control plans clearly outline methods, actions, and responsibilities. They describe expected outcomes and serve to focus resources on customer requirements. Anyone involved in monitoring the project can use the plan to carefully monitor key inputs and outputs of the process. Control plans can outline the checking, monitoring, and response plan for a single part or process, or a group of common processes. Control plans include a number of categories of information, such as who the customers are and what their critical requirements are, and have details about specifications, targets, responsibilities, and action items. They also set out which indicators will be monitored and the method and frequency of measurement to be used. A well-executed control plan is critical to ensuring the ongoing success of an improved process. The three key improvement-related goals of a control plan are validating improvements, providing a knowledge repository, and finding new improvement opportunities. Validating improvements involves confirming that the recommended actions have served the purpose of improving the process. It relies on effective measurement analysis and that no waste or variation has been produced by inaccuracy or inconsistent measurement reporting. Providing a knowledge repository involves two steps. The first step uses a formal team meeting to finalize an improvement project and integrating the lessons learned during the project into the deployment. The second step is where the executive deployment team finalizes a formal process to store the relevant information for future improvement initiatives. Finding new improvement opportunities involves defining directly or indirectly related improvement opportunities in the current improvement project in order to assist with the current project as well as future. A Six Sigma Black Belt needed a control plan for a hotel check-in process. She decided to use a modified version of a control plan from a previous project involving a maintenance process. The check-in process began to go out of control, and this wasn't detected quickly enough because the control plan called for measurements to be taken weekly. The maintenance project plan wasn't designed for the rapidly changing conditions and customer-facing nature of the check-in process. A control plan must be specific to the process being monitored, and all necessary elements must be included for it to act as the central data source for keeping the process in control. As you recall from your previous Six Sigma experience, the process of creating a control plan includes 3 phases. Phase 1 covers identifying the process scope. In Phase 2, you're determining indicators and responsibilities, and in Phase 3, the control plan is completed and reviewed. During Phase 1, you define the purpose of the process, its boundaries, and its intended use, translating the voice of the customer into quantifiable, measurable objectives. The second phase of a control plan creation is concerned with determining indicators and responsibilities. It involves designing the control process to meet the critical customer requirements, or CCRs. Control plan creation begins with establishing scope, customer requirements, and indicators in Phase 1. Then, in Phase 2, The detailed specifications and criteria that will meet the CCRs are determined. In Phase 3, the control plan is actually created and evaluated. You will recall that Phase 3 is when you define the rest of the elements that will be included in the control plan, keeping in mind that each control plan will have its own particular needs. You evaluate the finished control plan, perform a potential problem analysis, and document lessons learned. The sources of information for the 3 phases are many and varied, including, among others, process flow diagrams, system FMEAs, DFMEAs, and PFMEAs, historical data, team process knowledge, designed experiments, and many more. Design reviews, multivariate studies, and lessons learned are other common contributors to the central data repository that is the control plan. Control plans are specific to monitoring and controlling activities and aren't concerned with process improvement initiatives. While they record the process's capability and key variables, they don't record the process's specific operational, budget, or training details if these don't have a direct bearing on the current control method. The elements necessary to include in a control plan and the layout of these elements will vary greatly from project to project. In spite of this, control plans do have standard elements. The example control plan provided is a generic template that includes all of the specific elements that belong in most control plans. The following administrative data fields often head up the control plan. A Six Sigma team is crafting a control plan. The control plan name, Operational Policy Manual, or OPM, publishing in this case, must be included so that the plan can be distinguished when placed into other documents, such as operating instructions or a Six Sigma database. You should also indicate whether this is a prototype, pre-launch, or production plan. You should provide a unique reference number for the plan, such as 6N-725. This reference number, sometimes called a control number, may be supplied by the responsible department. The core team members, which for this process is Lisa, Eddie, Karen, Tim, and Rudy, refers to the individuals creating the plan and controlling the process, not the Six Sigma improvement team. Particularly if a cross-functional team is involved, you should provide the members' names and contact information for users who have any questions. If revisions are made by different team members from those who created the original plan, note them as well. The current process owner, which for the OPM publishing process is Jerry, should be assigned to the control plan, as that person will ultimately be responsible for its monitoring and execution. The process owner is a better contact person than the project black belt would be. You should indicate the page number for each page of the control plan. Although the examples of control plans in this lesson are single-page plans, some control plans span multiple pages. This control plan indicates this is page 1 of 4. The original date the control plan was created should be noted. It can be listed as the first date in the revision section, or it can be noted as the creation date under the revision details, as was done here. Whenever the control plan is revised, that fact should be noted. For each revision date, it may be useful to note the team members and a revision number as well. Noting the details of the types of changes that were made helps the reader focus attention on the specific area, such as revised targets, versus reading the entire document. You should note the process customers. They are the recipients of the process output, and the objective of the process is to meet their input requirements. This plan is aimed at the Quality Control Department. The process description identifies and describes the product or process, or the component of the process to which the control plan applies. Updating, developing, printing, and distributing the operational policy manual among all employees describes the process and avoids confusion. Other elements that should be included in a control plan deal with the more specific control indicators that will be monitored. The Six Sigma team continues to fill out the OPM publishing process control plan. Critical Customer Requirements, or CCRs, are validated, measurable obligations that outline what the customer needs and expects from the process. These requirements determine the specifications of the process, which in turn influence how the process operates. The customer for this process requires less than 0.04% defects. Outcome indicators assess the effect and impact of the process. They demonstrate the degree to which process improvements have resulted in lasting change. They are key to evaluating how well the process meets critical customer requirements. Unlike key process output variables, outcome indicators often deal with qualitative data, such as the customer being satisfied with quality. When a control plan covers a process step rather than a complete process, you must identify which step the plan covers. Details of any sub-process steps should be noted as well. Here, the process step is the manual compilation. You indicate which item is being monitored and controlled by filling out either the KPIV or the KPOV information, but not both. The higher-level outcome indicators, which are noted elsewhere in the plan, are used to identify which variables are key process input variables, or KPIVs. KPIVs, such as the ring metal noted here, are direct measures of the time and the financial and physical resources put into the process to produce the output. Key process output variables, or KPOVs, are also determined using the outcome indicators. KPOVs are direct measures of the goods or services produced by the process through the use of inputs. KPOVs are not monitored in this plan. The process specification section contains information on the specification limits. For manufacturing applications, the engineering specifications should be used. For other applications, such as the binder width and binder height in this plan, you would provide the upper and lower specification limits, the USL and LSL, and the target value. Being within control limits does not necessarily mean being within specification limits. Process capability studies distinguish between conformance to specification limits and control limits. The initial CPK value of 1.7 for the width and height of the binder indicates the process capability. You must also indicate the sample size for each capability rating and the date it was taken. The measurement system section is used to enter information on the measurement tool or technique and the measurement system's capability. In the technique column, you indicate the measurement gauge, tool, or test device used for data collection. The gauge's ability to produce the required information should be evaluated using measurement system analysis, MSA. Here, the reproducibility and repeatability, RR, of the steel ruler is entered as 6%. Precision to tolerance, PT figures, may be recorded in the PT column. Other important elements included in a control plan fall under the current control plan area of the template. Here, the methods, procedures, and responsibilities for actually monitoring and maintaining control are documented. The user knows what to do to detect and react to problems because of these fields describing the current control plan. These are the elements that fall under the current control plan area of the OPM publishing control. The when frequency column is where you indicate the sampling frequency. This indicates how often the process control measurement takes place. All of the samples in this plan were taken per lot. The where what column is a place to note where in the process you're going to measure and is the place to provide a high-level view of what you're measuring. The plan shows the ring metal in this project is measured at the edge. The who column is used to indicate the person responsible for taking and recording the measurements. Operators took the measurements in this case. The method section is used to note the way the variables will be controlled. Typical methods include control charts, as in this case, or checklists, visual inspections, and automated measurements. Reaction plans are instructions for the action to be taken if problems occur or problems appear imminent. The plan must clearly direct what the responsible person should do if the variable begins to go out of control or products begin to fail inspections. For this project, the OPM user is instructed to contact Rudy at the supplier. The Notes Miscellaneous column is available for entering special considerations and particular characteristics of the process that should be monitored. It can be used to provide a legend of the graphical elements used to represent aspects of the process. You can use it to clarify procedures, write out abbreviations, or include other information vital to supporting the control activities outlined in the plan. This plan has information from two documents, the kickoff meeting minutes and the Measurement System Analysis MSA report. The exact line items in a control plan differ based on the requirements of the process, the team, the organization, the project, and the customers involved. For some processes, additional documents and images may need to be included, either embedded in the main table of the control plan or attached to it. Two key categories of additional information are graphical elements and lessons learned. Control charts and other graphical elements will often be included to provide more detail for the specification limit and capability figures that are recorded in the control plan. Providing these images can give a more in-depth visual performance history of the process than summary statistics can provide. To ensure the quality improvement gains aren't lost, the control plan should document what went right and what went wrong during process improvement. This is known as lessons learned. A Six Sigma team brought in to improve the order fulfillment process at an electronics retailer has improved the process and carefully designed a control plan to substantiate results. Once this is established, the process is ready for handoff back to operations. The team passes ownership to the process owner, the fulfillment department manager. After handoff, she will own the improved process and be responsible for control plan implementation. After completion, a control plan is handed off to the process owner for monitoring and execution. But process owner is an organizational position, and as such, the person fulfilling the role will change from time to time. Even if the process owner, who is often the department or operations manager, remains the same, other projects may demand her attention. Conflicting priorities can easily lead to neglected or poorly executed control plans. If the control plan isn't adequately maintained after handoff, the improvement benefits could deteriorate or gradually be lost. So it's important to hand over control plans in such a manner that current as well as future process owners can maintain controls. After the control plan is complete, the transfer of responsibility for control from the Six Sigma team to the process owner relies on several actions like transitioning and integrating the control process into operations, for example. Your Six Sigma team must re-examine the control plan in light of its integration with other related processes. An order fulfillment process, for example, must interface with the order-taking process on one hand and the shipping department on the other. The control plan must allow smooth interaction between both of these processes. The process owner and his employees must understand what's involved and accept accountability for controlling the process. Most likely, these people will have been consulted and involved in the improvement process, as well as in the development of the control plan. The Six Sigma team will need to train all involved personnel in their responsibilities, verify that the training is effective, and get the team members and process owner on board with the program. The documentation methods involved in the control plan must be well designed, clear, and easy to use. This will allow the people doing the monitoring to effectively document the control process in both written and graphic forms. The team should ensure that all work instructions, including documents that are outside the department or area, have been updated with reaction plan instructions. This will ensure that everyone is on the same page as to what to do when nonconformance or instability is identified. When the OPM publishing control plan is finished, your Six Sigma team successfully passes ownership of the control plan to the operational managers and workers. Your careful consideration of the plan's interaction with the real world ensures successful execution of the plan and keeps the improved process under control. Control plans must contain all the specific information needed to keep the process in control. As the central source of information for all those involved in controlling the process, control plans must include a wide variety of information, including indicators, customer requirements, control limits, specifications, and targets. Control plans also contain responsibilities and actions to be taken in the event that the process begins drifting out of control. 3 broad phases are involved in creating a control plan. Phase 1 is identifying process scope and CCRs. Phase 2 is determining critical performance indicators and responsibilities. And Phase 3 is completing and reviewing the control plan document itself. The final activity associated with creating a control plan is the successful handoff of responsibility to the process owner. You can access the job aid about control plan development after this video to review a helpful checklist for developing and implementing. Some people have a knack for giving fabulous parties. It doesn't happen by accident, and they're not born with this ability. In addition to good planning, one thing that all successful party planners do is post-mortem their social events. Over coffee or while cleaning up after the party, they'll think about what went well and what fell flat. Sometimes they phone trusted friends to get their feedback as well. Over time, the party giver's body of knowledge grows and the parties get better and better. For a project post-mortem to be successful, it must include activities that benefit the organization, such as discussing what went right and what went wrong in the project, emphasize the lessons learned and best practices that must be sustained, and how effective the project was in delivering results. Post-event analysis is useful in the business world as well. Consider this example. Jeremy, a black belt at an investment firm, is accustomed to managing mid-sized projects with medium-level risks. He is confident in his ability to learn as he goes and doesn't put much effort into analyzing finished projects. As a result, Jeremy tends to make the same kinds of mistakes again and again. Risks that could be prevented with a bit of foresight continue to plague him, and he develops a reputation as a poor planner. Then there's Marie, a black belt at the same investment firm as Jeremy. She takes the time to analyze each one of her completed projects. She calls her team together to discuss things that went wrong and things that went well. They discuss the lessons learned and brainstorm better ways to prevent risks and resolve situations that could occur again. Marie documents her findings in reports that she distributes to team members and her superiors. Everyone learns as a result of Marie's experiences. What's the moral of these stories? History repeats itself, and unless you learn from the past, you'll keep making the same mistakes again and again. The post-project analysis goes by many names: lessons learned, autopsy, post-project appraisal, and post-project review, just to name a few. This course will use the term post-mortem analysis. The term post-mortem means after death, and generally refers to examining a body to determine the cause of death. The purpose of a project post-mortem is to brainstorm a project after its completion to find out what worked well for the project, what didn't work, and why. A post-mortem analysis for a Six Sigma initiative is a formal critique that covers all phases of a project. Project post-mortems are organization-specific. Many organizations have their own methods and list of topics that must be analyzed. There are several topics you can consider if your organization doesn't have such a list. One topic is project effectiveness. How effective was the project as a whole? What successes occurred and why? What failures occurred and why? Another topic is resources. Were personnel, time, equipment, and funding adequate? What could you have done to obtain other needed resources? Project tracking is another topic. How well was the project tracked and progress documented? What could you have done differently? Then there's status reporting. How effective was status reporting to top management and the project sponsor? The next topic is the cohesiveness of project team. How well did the project team gel and work as a whole? Which members did not communicate or get along well? What was the effect on the project? How could relationships have been improved? Another topic is recognition. Do team members feel they were adequately recognized for their efforts? The effectiveness of the team is another topic. How effective were the team's actions? Brainstorm specific examples of what worked well and what didn't work very well. And a final topic is quality. What is the true quality level of the delivered product or service? Where and when are problems likely to occur? A post-mortem analysis helps to build an organizational memory and a set of best practices that's tailored to the organization. These elements are key to your organization's ability to produce higher quality goods at lower costs and, in turn, achieve competitive advantage. A post-mortem analysis requires a commitment of resources, both time and money. Managers need to understand the value of post-mortems so they can authorize resources for them. Without management support, a culture of continuous improvement cannot exist. The benefits of a post-mortem analysis are significant. When presenting the benefits to management, there are a number of points to keep in mind. First of all, they make development and improvement a smooth, repeatable process when conducted on a consistent basis. Another point to keep in mind is that they document and preserve information that would otherwise disappear when project members move on to new projects. They also spread important learning throughout the organization. When teams are disbanded, employees take the lessons learned to their new projects. And finally, they support an organization's continuous improvement efforts by ensuring you keep what works and reject what doesn't. In Six Sigma, post-mortems are also an important tool for project control. Data from post-mortems is included in Six Sigma control plans and then used during the control phase to ensure best practices are followed and process changes are maintained. Without this documentation, future project teams could find themselves reinventing the wheel with each new project. The steps in conducting a post-mortem often differ from one organization to the next. The participants can also vary depending on the kind of review being done. Some organizations have a black belt conduct the post-mortem. Others contract with an outside facilitator who has no connection with the project. It's not recommended to have the project manager conduct the post-mortem. The project manager has a vested interest in the results, which could taint the process. During a post-mortem, everything is open for discussion, including failures. It's very important that nothing gets swept under the rug. Regardless of the differences among organizations, two of the first things to do when planning a post-mortem are to declare the intent by selecting the time and choosing the participants. The post-mortem should be part of the project plan, and it should be scheduled to follow closely after the project's completion. Participants must have the issues and events of the project fresh in their minds. If the review is left too long, people forget the details of topics that must be discussed. Consider this example. Ron and Sue are black belts at an aircraft company. They have finished projects within a few days of each other and are planning their post-mortem analyses. Let's take a look at the results of each post-mortem. Ron's team has been disbanded and members have moved on to new projects. He wants to give them time to settle into their new assignments, so Ron schedules his post-mortem for a month after the project. When the time comes, Ron finds that his former team members have forgotten many details, and they aren't eager to revisit their former project. Ron's post-mortem is not very successful. Sue's team has also been disbanded. However, she schedules her post-mortem for a week after the project is completed. She also asks her team members to bring their notes on lessons learned that they'd been asked to keep during the project. Sue finds that people are eager to revisit project details, and they have valuable contributions to make about what worked and what didn't work. In addition to scheduling the date of the post-mortem, you must also choose the participants. If your project team is a manageable size, you may include everyone. This prevents scapegoating of individuals who aren't at the meeting. If you can't include everyone, you should try to include a representative sampling of your team members. It's a best practice to include the core people who are involved in all of your project tracking meetings. These people have a great depth of experience and knowledge of the project. You should also include people who can give you different perspectives. A diverse group with a wide range of views will help you cover all of the issues effectively. Let's consider an example of how two black belts chose the participants for their postmortems. Carrie recently finished a Six Sigma project. His team had 25 people: engineers, operations specialists, suppliers, sales reps, and marketing analysts. To his postmortem, Carrie invited everyone except sales reps. Because he was the only person who dealt with sales reps, Carrie felt he could speak directly with them to get their perspectives on the project. And Katie is planning a postmortem for a Six Sigma project on improving the software development process at an IT company. The project was staged, and in all, 97 people were involved from start to finish. Katie begins by inviting the 8 people who participated in her regular project tracking meetings. Then, she chooses the remaining participants to achieve a representative sample of each area of expertise for each project phase. Now, let's analyze Carrie's and Katie's choices. Carrie's team was small, so he included everyone in his postmortem. This is always a good practice, when doing so is practical. Katie's team was enormous. She invited the core group who had been on the project since the beginning, as well as representatives from each group that participated in each project phase. Whenever people with diverse points of view get together, there can be misunderstandings. Communication barriers naturally exist among people with different perspectives or understandings, as well as between people who have different values or priorities correspondent with their different roles in a project. A good facilitator can enhance understanding among these groups. A good start is to provide a list of common terminology for everyone to use. You can also create a feedback communication plan to tailor specific kinds of communication to particular people. For example, you may want to have follow-up discussions with certain groups or individuals after a group discussion. This can be especially useful when technical issues are being discussed and not everyone in the group is able to understand them. Another way to deal with communication barriers is to break into smaller groups. If the issues to be discussed are particularly sensitive or private, discussing them with a small group of people rather than the entire post-mortem team is a good idea. For example, difficulties with the client might not be a suitable topic for a general meeting. You should probably convene a small group of people for this discussion. Consider a case study. Phil, a black belt for a financial investment firm, is planning a post-mortem for a project that's just now wrapping up. Phil's team consists of financial analysts, actuaries, members of the IT department, and QA specialists. The first planning criteria he follows is to set the time. He schedules the meeting for the same week as the project will complete. Since he isn't the project leader, Phil decides to facilitate the post-mortem himself. Then he chooses the participants for the post-mortem. His team is small, so Phil invites everyone. He wants to obtain the widest possible range of thinking. As a final step, Phil plans how to overcome communication barriers. He suspects there may be some communication gaps between the financial analysts and IT analysts, but he's confident that he can bridge the gap during the meeting. Unfortunately, Phil's post-mortem didn't go as well as he'd hoped. Because he didn't plan in advance how to bridge communication gaps, the IT people and financial analysts weren't able to discuss their differences in a meaningful way. This factor had caused problems during the project as well. If Phil had created a feedback communication plan, he could have developed strategies for helping the two groups to understand each other, and his post-mortem would have been more successful. A post-mortem analysis is held to determine what went right and what went wrong during a project. A post-mortem benefits an organization by building organizational memory and best practices that foster continuous improvement. Topics discussed in a post-mortem include the effectiveness of the project and of the team, the adequacy of resources, the thoroughness of project tracking and status reporting, and the quality of the finished project. A post-mortem should be conducted close to the end of the project. It can be led by a black belt, a project team member, or an outside facilitator. The project manager should not conduct the post-mortem. If the project is small, everyone from the project team can be invited to participate. For larger projects, you must select your participants, including the people who have a depth of experience and knowledge, as well as people with a broad range of knowledge of the issues. A feedback communication plan can help to level the communication barriers that exist among people. Common terminology should be provided to ensure that everyone shares the same understanding of terms and concepts. The objective of a post-mortem analysis is to enable organizations to improve by building on, rather than relearning, lessons from completed projects. Now you prepare for the post-mortem review. All organizations have their own processes for managing reviews. However, some general guidelines do apply to all post-mortem analyses. As you prepare points to cover in your post-mortem, there are 3 tasks that must always be done. First, establish guidelines for the post-mortem meeting. Another task is to develop a high-level view of the project lifecycle processes and activities. And finally, devise conversation starters that will prompt participants to dig deeply into the project lifecycle activities and processes. When preparations are complete, the facilitator conducts the post-mortem. Your organization's policies determine the kind of post-mortem you must perform. The duration of a review and the number of pages in the post-mortem report vary widely, depending on the type, length, and complexity of the project. A review can take from a few hours to a few weeks, and a report can be anywhere from a few pages to a few hundred pages. Regardless of the method used for the post-mortem, though, the primary objective is to identify the top 3 to 5 areas of praise and the top 3 to 5 areas for improvement. The discussion points that are introduced should be geared to elicit this information. Consider an example. To conduct her review meeting, Sarah creates 2 lists, one for areas of praise and the other for opportunities for improvement. After establishing meeting guidelines, Sarah presents her overview of the major activities and processes in the project's life cycle. She uses conversation starters to take participants through each process. As areas of praise or opportunities for improvement are identified, Sarah notes them on the whiteboard. At the end of the meeting, Sarah and the group prioritize items on the whiteboard. In this way, the team identifies the top 4 areas of praise and the top 3 opportunities for improvement. After the meeting, the facilitator presents the findings. Some organizations break this step into 2 parts, giving a presentation and writing a report. The face-to-face presentation can be short and simple, perhaps covering only the basic areas of praise and opportunities for improvement. As a matter of professional courtesy, results are sometimes presented according to a hierarchy: the project manager first, followed by the project sponsor, resource managers, senior management, and the client. Audiences can be separate or combined, depending on how sensitive the information is. In addition to the presentation, findings are documented in a report. The report describes the key 3 to 5 areas of praise and the 3 to 5 opportunities for improvement. It isn't recommended to document any more information than that, as additional detail can water down the important lessons learned. The areas of praise, the good news, should be presented first. An action plan may also be part of the report. The action plan gives follow-up recommendations on how to continue the things that did work and avoid repeating things that didn't work. The point of the action plan is to ensure other people can learn from a project's successes and failures and apply these lessons to different projects in the organization. For example, one of the actions that Sarah notes in her action plan is to follow up with the finance department. Finance agreed to appoint a liaison with the programming department to alleviate the kind of communication problems that plagued Bob's project. Sarah used a section in her report to suggest ways in which this liaison would benefit upcoming projects in other departments. Post-mortem reports are archived, but before that, copies are made available so that everyone can access them. Some organizations maintain a location on the company intranet or website for all post-mortem documents. When a new post-mortem report is available, a general email is sent out to everyone involved in project work. The email summarizes the report and announces its location. The summary is important. People may not have the time to look up a document, but they will scan an email for information that can help them to perform better. 3 tasks are done to prepare for a post-mortem: prepare meeting guidelines, create a high-level view of activities and processes, and devise conversation starters. An action plan may be part of the post-mortem report, listing any follow-up items, including what is to be done and by when. Also included are suggestions for exploring the way that lessons learned can be applied to other projects. In addition to learning how change helps them, process owners and staff members can derive other benefits from training. One benefit is a clear understanding of new expectations. Another benefit is knowledge of how to do a task properly and consistently. The next benefit is knowledge of how to adjust a process for improved performance. And a final benefit is knowledge of where to get help in controlling a process. At this stage, the Lean Six Sigma team and Black Belts transfer the reign of the improved processes, methods, and systems to the process team, which is usually led by the process owner. As a leader of the Six Sigma team, you need to ensure that skill building and transition training for process owners and staff is developed and implemented. The purpose of the training is to ensure that the process team possesses all skills and information required for consistent execution of revised processes, methods, and standards to sustain current improvements. It will likely be very different in terms of content and goals from training they received at the beginning of the project. Training also provides a better understanding of how upstream and downstream processes affect or are affected by each process owner's role in the overall end-to-end process. When you understand your customers and others who supply information to your processes, you can better assess and anticipate the impacts of change on your processes. One critical element in providing training is support from upper management. Without management support, training won't happen, no matter how much employees need or want it. Why would management oppose training? Because it's expensive. Buying or developing training materials costs money. During training, employees aren't working, so there's lost productivity to account for as well. It can also be difficult to cost-justify training because training objectives are sometimes difficult to quantify. For example, an objective like, understand how new accounting processes benefit your department, is important, but how do you measure it or link it to bottom-line profitability? Despite these perceived negatives, it's critically important for management to understand the benefits that come from training. Let's consider some of the numerous benefits training brings to the organization as a whole. First of all, training propagates Six Sigma thinking and promotes buy-in among employees and managers alike. Everyone is able to be on the lookout for opportunities for improving processes. Another benefit is that training disseminates common sets of core knowledge and skills, competencies, throughout the organization. Core competencies are essential for accomplishing organizational objectives. A third benefit to the organization is that training creates a flexible workforce. Grounding in the core skills and knowledge creates a workforce of cross-functionally trained employees. Cross-training ensures that managers always have the human resources needed to perform a variety of tasks. And finally, training brings a competitive advantage. When employees' knowledge and skills keep pace with the organization's evolving processes, the entire organization is on track to achieve its mission, goals, and objectives. In a competitive marketplace, the organization that optimizes its human resources best achieves competitive advantage over other organizations that may not have optimized this resource. For an organization to thrive, upper management must overcome its resistance and understand that continuous process improvement can only be sustained through continuous employee training. When upper managers get behind a coordinated training effort, the entire organization benefits. In many Six Sigma organizations, black belts do double or triple duty as trainers. They know the improved processes and have an enterprise point of view that helps them put the new processes into perspective. However, not all black belts feel comfortable in the role of trainer. If you are called upon to assume this role, there are some guidelines that will help. Training is partly art and partly science. The best trainers begin with basic guidelines, which they modify to suit the nature of the project, individual team requirements, and organizational needs. As a trainer, you must touch on all of the guidelines, but remember, they're guidelines, not rules. There's no cookie-cutter approach to training. You'll always tailor your training to individual circumstances. In most organizations, people are under time pressure to produce results. This pressure may lead you to want to spend less time on planning your training. But remember, training could affect hundreds of employees in diverse locations. Failure to properly plan would be wasteful and ineffective, and even worse, it would jeopardize any expected benefits the project would yield. Preparing for training involves 3 steps: identifying your audience, assessing their training needs, and preparing the activities, resources, and materials that will help meet those needs. Identifying your audience is a critical first step. For a Six Sigma project that is in the final stages of DMAIC, the audience usually consists of employees and managers responsible for managing and maintaining improved processes in various departments. When process changes affect more than one group, you might need to develop separate training activities to meet the needs of each group. After defining the audience, you assess training needs. There will be a gap between what employees are able to do now and what they'll need to be able to do to sustain the process changes. You need to define the scope and the depth of the performance gap in order to determine what to teach. When you define the scope of training, you define the knowledge and skills that will enable employees to bridge the gap and reach the higher performance level. Substantial process changes may require more in-depth training than smaller changes do. Depth is often addressed with a staged approach. Training begins with introductory material and proceeds to specific information and real-world examples. The third task in preparing for training is to prepare the goals, activities, resources, and materials that will help meet the needs of your audience. This task includes several subtasks. One subtask is developing learning goals. A learning goal identifies the purpose of a training program or activity. Goals are general statements that can focus on content, skills, or attitudes. Examples of learning goals are to become an effective communicator and to be able to run a milling process with greater efficiency. Another subtask is design learning objectives. Learning objectives are similar to goals, only more specific. Objectives specify what learners will be able to do after completing the learning activity that they couldn't do before. Examples of learning objectives for the learning goal of achieving near total perfection in the milling process might be to correctly perform the new operating procedures for the milling process and to be able to use appropriate tools for troubleshooting problems. A third subtask is to design learning activities. Learning activities contain the content needed to teach the objectives, designed for the delivery methods you'll use. The medium must suit the message. That is, the delivery method must be appropriate for the content. Delivery methods include computer-based education, classroom training, hands-on workshops, video, and coaching, among others. For example, a learning activity for listening skills might be a workshop with role-playing exercises, where learners practice specific listening skills. The next subtask is designing evidence of learning, which refers to assessments that show whether learners have achieved the objectives. In this course, for example, practice and test questions are evidence of learning. They enable you to assess your own acquisition of knowledge. Evidence of learning for a skills-based activity might be a hands-on demonstration, where the learner demonstrates new behavior learned in the training. And finally, in addition to assessing learners, you must evaluate the learning activities themselves. This can be done both as the activity progresses and after the activity is completed. For example, by questioning learners during the activity, you can assess whether they're on the right road to achieving the objectives. To test an activity after learners complete it, you can ask for supervisor and learner feedback as to whether the activity met its objectives. Be sure to spend the time you need to analyze your audience and assess their needs. Defining your learning goals and objectives, as well as planning for resources and materials, will make training responsibilities much easier. When planning the elements of your training program, don't worry if the program isn't perfect. Be realistic. Make a start, and you can refine it later in the development process. Start by establishing the learning goals. Ask yourself what you want learners to be able to do when they finish the training. You should keep a number of considerations in mind to help you create realistic goals. One key consideration is the content. What is the content or subject matter you need to cover? If your audiences need to master a particular concept, understanding, or subject matter, you need to devise a learning goal for it. Next, consider your time frame. The need to deliver training by a particular time will affect your learning goals, objectives, and activities. Also, a time frame is important for scheduling training. When training is given too early, people forget important information by the time they need to use it. Training given too late is a waste of time and money. When establishing learning goals, also consider the performance gap. Are you training to bridge a performance gap? A performance gap is the difference between what employees are doing now and what they'll be expected to do after the project's deployment. To identify a performance gap, start by finding out which knowledge and skills employees currently have and compare that with the knowledge and skills they'll need in the future. Next, consider whether you are training to bridge a growth or opportunity gap. A growth or opportunity gap occurs when people change responsibilities. For instance, some people may be changing roles after the deployment. If this is the case, training will need to address the new skills. Feedback is another consideration when establishing learning goals. What do supervisors and others have to say about what learners need to know? Supervisors and managers can tell you about strengths and weaknesses in your learner population, as well as potential threats or stumbling blocks to your training. And a final consideration is sources. What kind of documentation is available to help you identify learning goals and objectives? For example, competency lists, job descriptions, and job analyses can help you identify what employees already know. Consider this example. Jan, a black belt, manages a Six Sigma team at a machine tool manufacturer. The team is working on a Lean Six Sigma project to reduce cycle time and work-in-progress inventory. The proposed solution requires implementing a new method, the pull system. Unlike the current system, the new one is highly integrative. Nearly everyone in the company must undergo training to ensure a successful implementation. Jan analyzes the audience's and training needs and follows guidelines to plan her learning objectives. Let's take a look at how she plans her learning goals. Jan defines her audience: managers and process owners, engineers, QA and production team members, and people in various departments who will be affected by the change. Then she defines her content: orientation information about Lean Six Sigma and information about the project that's currently wrapping up, technical skills for operating the new machines and new software, and various soft skills such as how to work with cross-functional teams. She enlists the aid of the corporate training department to provide her with job descriptions and competency lists. And now let's consider how she establishes her goals. Jan comes up with her learning goals, which are that people must be able to understand the work of all departments in the new processes. People need to be able to communicate well and work within cross-functional teams. Engineers need technical skills training to master the skills and knowledge required to operate new machines and software. And managers and process owners need to understand the foundations of Lean Six Sigma and the parameters of the project. With learning goals in place and content roughly defined, you can define learning objectives for each goal. Objectives are the specific skills or knowledge that learners must acquire in order to reach their goals. An objective answers the question, what will the learner be able to do as a result of the learning experience? When you create learning objectives, remember the acronym SMART. Learning objectives should be specific, measurable, acceptable to the learners, realistic to achieve, and time-bound. Time-bound means there's a date or time frame in which the learner achieves and is able to demonstrate an objective. Without a time frame, someone may argue that an objective is to be met sometime in the future. Others may expect the objective to be met sooner than is realistic. A date or time frame eliminates uncertainties. Returning to the example, with her learning goals and audiences in mind, Jan groups her audiences according to common needs. She creates a training matrix and works on some preliminary learning objectives. One learning objective she works on is cross-functional training. Everyone involved must understand the work of all departments that interact with the new process. The objective is for everyone to be able to fill in a flow chart of new processes with names of departments and units that interact. Another objective is technical training. Engineers, production team members, and QA team members need technical training. One of the detail objectives is to be able to operate the new SoftWing inventory control software. Soft skills training is the next objective. Engineers, production team members, QA, and all staff members affected by the changes need training in soft skills. Objectives for this group include be able to deliver a short presentation and be able to demonstrate active listening principles. And a final objective is Lean Six Sigma orientation. Managers and process owners require orientation in Lean Six Sigma. The objectives for this audience include being able to articulate the seminal principles of Lean Six Sigma, being able to identify the inputs, processes, and outputs of the new pull system, and being able to read and understand the Six Sigma project documents. With learning goals and objectives defined, you begin to plan the activities that will enable your learners to meet the objectives. This involves choosing the delivery methods or learning techniques that best suit the objectives and content. As you plan, there are a few considerations to keep in mind. One is learning styles. Do learners have a primary learning style, visual, auditory, or tactile? Plan your learning activities to take advantage of these learning styles. Use graphics, pictures, sound, and hands-on practice as appropriate. Another consideration is environment and facilities. What kinds of facilities do you need? Classrooms, video conferencing, computers? What training facilities are already available to you? Take advantage of the facilities you already have. A third consideration to keep in mind when planning the activities is integration with real-world experiences. Can you incorporate real-life work experiences into the training? The closer your training mirrors the situations that learners will encounter on the job, the more effective the training will be. It's important that your learning activities match the learning objectives. All objectives need to be addressed. Designing activities that are lean and mean is also important. You don't want to waste learners' time. Remember to build in sufficient interactivity. Learners benefit from sharing their experiences with each other. You should balance a bare-bones approach to content with frequent interactivity so that learners can discuss and share their experiences. Returning to the example, Jan is fortunate. Her company has an in-house training department. Jan works with trainers to define the kinds of activities that will help learners achieve the objectives. To meet learners' varied learning styles, Jan will use combinations of audio, visual, and kinesthetic activities. For example, managers are accustomed to presentations with written executive summaries. Production team members will require kinesthetic, hands-on exercises to learn to operate machinery. As far as environment and facilities are concerned, classrooms and a variety of media are available through the training department. Jan will have the capacity to hold large group presentations and take portable media into the production site for interactive demonstrations and hands-on practice. And as far as integration with real-world experiences are concerned, some of the training for production team members and QA will take place on the job. Supervisors will be provided with exercises that learners are to complete within the first 2 weeks of the system going live. Also, Jan would like individuals from involved departments to conduct part of the cross-functional training for each other. This way, they can all share real-world experiences in discussing how they currently do their tasks. At some point in the planning process, you will begin to design or collect the actual training materials that are to be used. Training materials, that is, hard copy course outlines, syllabi, job aids, and learning aids, are important for learning. No one can remember everything, and handouts provide refreshers of important information for learners to take away with them. To identify whether training materials are needed, ask yourself, what takeaways will help the learner perform better on the job? While planning your learning activities, you must define evidence of learning or assessments. Assessments can be used to show upper management that the training is effective and worth their investment. Self-assessments are also important during training. They show learners how well they're doing in mastering the material. You can use several questions to help you define your evidence of learning. One question is, what results are produced? Asking this question will help define criteria for measuring whether learners achieve the objectives. For example, you could use scores from written exams, or you could observe whether learners are able to assemble a part correctly. In any case, the criteria should be measurable or observable. Another question is, who will verify that objectives have been achieved? Asking this question will help define who will verify the results of learners' assessments. For self-assessments, learners verify their own learning. For other kinds of assessments, such as hands-on learning, supervisors may be the ones to verify learning. In designing assessments, test at the same level you teach. If you're teaching concepts, written questions are appropriate. If you're teaching a hands-on technique, try to design a hands-on exercise where learners can show they have mastered the technique. In addition to learner assessment, you must decide how to evaluate the training itself to ensure your approach is practical and effective in reaching learning goals. Prior to delivering the training, you'll want to get all content signed off by a subject matter expert to be sure it's accurate. You'll also want a trainer, if available, to review your activities to ensure they're instructionally sound. Many trainers use questionnaires to obtain feedback from learners and supervisors on the training's effectiveness. Another way to find out about an activity's effectiveness is to ask supervisors for feedback on employees who completed the training. Supervisors can tell you whether learners are performing at the levels you outlined in your objectives. Returning to the example, Jan has defined her learning goals and learning objectives, and she's worked with the training department to define the learning activities. Now, she must plan the learning materials, evidence of learning, and evaluation of the training. To plan the learning materials, Jan asks, what takeaways will help the learner retain information and perform better on the job? For the Lean Six Sigma overview, She will write summaries and copy project documents like the project plan and budget to create packets for managers and process owners. For technical training and soft skills training, the training department will create course syllabi and outlines, plus a variety of supportive visual job aids as needed. For cross-functional training, the learners will be provided with workflows and departmental organization charts. And to plan the evidence of learning, Jan asks, what results will the learning activities produce to serve as verification of learning? Managers and process owners will use self-assessment questions. Supervisors will fill out questionnaires to assess on-the-job performance after technical training. Soft skills learning will be assessed in class as the trainer observes how well learners are able to present and listen to each other. Cross-functional training will be assessed by having learners match the blocks on a process flowchart with names of departments and functions. And finally, to plan for the evaluation of training, she asks, how will the training be evaluated to ensure it's effective? Jan will solicit feedback from managers and process owners as to the effectiveness of her Lean Six Sigma training. She'll use questionnaires and call selected supervisors to learn whether performance has improved after technical and soft skills training. She'll also use a learner questionnaire to evaluate how learners feel about their training. Training, the process of imparting skills and knowledge to employees, is essential in a Six Sigma organization. Continual process improvement can only be achieved when continual employee development takes place. Black belts are sometimes called upon to plan and deliver training. Following certain guidelines can help in planning the training. The guidelines are to define learning goals and learning objectives, define learning activities, gather learning materials, determine evidence of learning, and decide how to evaluate the learning. Plan your work, then work your plan. After creating a training plan, you must determine how best to deliver the training. Some lucky people are born performers, but most people have to work hard to learn presentation techniques. While you may never be a fabulous performer, you can certainly learn to be a confident one and deliver high-quality, engaging training experiences to your learners. Training is a heightened form of communication. Many of the techniques for communicating effectively work equally well for training. There are several techniques that are useful for regular face-to-face or face-to-group communication. For instance, use varied presentation styles, modes, and media. In addition, use appropriate humor and current and relevant examples to illustrate concepts. It's also useful to show enthusiasm and commitment as an agent for change, and to tell stories from your experiences as a black belt. Have you ever attended a training session where the presenter was expressionless and delivered his presentation in a monotone voice? Most people have, and it's not fun. To avoid this, vary your presentation style. Vary the tone and speed of your speech to create interest and emphasize your key points. Use pauses and silence strategically. Pauses give learners a chance to collect their thoughts, reflect on the subject matter, and relate it to their own experience. It's also important to vary communication modes. Communication modes refer to how you give information to and receive information from others. For example, presentations depend on speech as the primary communication mode. But alternate speaking with asking questions and listening carefully to the answers. Active listening is an important part of communication. Try to use writing too. Writing key words on a whiteboard while you're speaking reinforces learners' understanding. And finally, don't neglect body language as a powerful mode of communication. People often reveal a great deal about themselves through their facial expressions, postures, and movement. Another important technique for engaging learners is to vary the media. Different media appeal to different learning styles, visual, audio, and kinesthetic. So try to incorporate combinations of media into your training. For example, lecture, flip charts, transparencies, printed materials, video, and technology-based delivery methods such as e-learning. Consider this example. Frank, a black belt in an insurance company, is delivering a training session for experienced insurance underwriters on process changes that have been made as a result of recent legislation. Frank knows the content is dull, so he uses a variety of techniques to spice up his training session. To vary the presentation style, he makes a conscious effort to modulate his voice so he doesn't speak in a monotone. Whenever he makes a key point, he emphasizes it and pauses to give learners time to process the information. To vary communication modes, Frank practices active listening. He asks questions and assesses learner understanding from their answers and body language. Several times, he picks up on confused looks and paraphrases information before he moves on. And to vary the media, Frank's company created a marketing video to inform customers of the changes that affect them. Frank starts his class with this video to engage the learners. He hands out copies of the legislation, as well as flowcharts of new processes, and he writes important points on a whiteboard as he presents them. Humor is a great icebreaker, but use it appropriately. Stay away from anything related to the isms, racism, sexism, or ageism, and be aware that humor is culture-specific. An innocent story or joke in one culture could be offensive in another. Include relevant examples. Concepts and theory are essential, but good examples show how concepts and theories are successfully and unsuccessfully applied. Telling stories about your own experiences as a black belt gives your presentation authenticity and a real-world perspective. Keep a file of stories so you don't forget them. And finally, believe in yourself and your message. Be enthusiastic and confident. You are the face of change for your audiences, and you are preparing them to accept the change and benefit from it. Returning to the example, throughout his training session, Frank is upbeat and enthusiastic. He doesn't tell jokes well, so he stays away from that form of humor. But Frank has some interesting and humorous stories from his own experience that he shares with his audience. He also asks learners for examples of how they operated within the old process. He uses their relevant examples to illustrate how the new process is an improvement over the old. Frank's session is highly interactive and very engaging. Engaging learners is important, but there's more to effective training than being a good presenter. You must be effective in delivering content. There are several guidelines that can help you be an effective trainer. First, build and maintain credibility. Another guideline is to conduct training in a collaborative and facilitative way. The next guideline is to create a comfortable environment that is conducive to learning. Providing opportunities for learners to apply their knowledge and skills is another guideline to being effective in delivering content. And a final guideline is to provide supporting feedback. Let's consider each guideline in more detail. A good trainer owns the room, sets the tone, and inspires learners to achieve. You must build and maintain credibility by showing respect for your learners and earning their respect in return. Be on time, present your credentials, and dress appropriately. Introduce yourself and clearly explain the expectations and objectives of the training. Learn participants' names and encourage learners to ask questions. In all your interactions, be sure to model the behavior and attitudes reflected in the course goals and objectives. Remember that you're training adult learners. Adults learn best when they're partners in learning. Work toward adopting a collaborative and facilitative approach. Learners bring a lifetime of knowledge and experiences with them, and they want to be able to share with and learn from each other. Provide opportunities for learners to answer questions raised by others and to relate examples from their own experiences. The more learners share their experiences, the more authentic your class will be. Another guideline for being an effective trainer is to provide a comfortable learning environment that is conducive to learning. This has two aspects: the physical environment and the atmosphere. As far as the physical environment is concerned, be sure the facility is equipped with the media you plan to use and that the room is spacious and has lots of light. Provide frequent breaks so learners can decompress from learning mode and are able to attend to physical needs. Provide snacks or lunch as appropriate. Above all, provide a safe atmosphere. Learners must feel safe before they can share their thoughts and experiences, explore new viewpoints, and change their attitudes and behaviors. Be sensitive to cultural differences. Respect differing viewpoints and make sure learners show respect for each other. Don't be afraid to make mistakes. Show that you're human, and you'll be an example for your learners to follow. You'll also want to provide opportunities for learners to apply their knowledge and skills. Whenever possible, provide hands-on practice and assessment so that learners can apply what they've learned in a simulated or real-world context. Timely and supportive feedback is a critical part of learning. Feedback lets learners know how they're doing in the training session, encourages them when they're not doing well, and motivates them to keep going. To provide feedback, you need to monitor your learners' progress during the learning activities. When giving feedback, it's very important to respond according to learners' needs. Nobody likes to make mistakes, so share your observations in a way that doesn't threaten your learners' dignity or self-esteem. Consider this example. Mike is a black belt who has spent a year and a half developing new computerized inventory control processes. Let's consider how Mike trains people on the new processes. Before training begins, Mike sets up his room. At each desk, he places a tent card with a learner's name on it, a manual containing the handouts, a course outline, and a schematic that shows the locations of bathrooms, the break room, and emergency exits for the floor. He cleans the computers that learners will use so monitors are free from fingerprints. On the first day of training, Mike starts the class on time and closes the door. He then introduces himself and summarizes his experience and the course objectives. Generally, as stragglers arrive during the first 5 or 10 minutes of class, Mike nods to them, but he keeps speaking. Mike makes eye contact and watches faces as he speaks. If anyone starts to look lost or confused, he stops to clarify the content. Every 30 minutes or so, Mike summarizes the material and answers questions. The class breaks every 90 minutes. During breaks, Mike talks to people about their projects. Sometimes learners ask him to be a resource for them, and he agrees wherever possible. Mike uses information that he gains from these chats, and he often calls on learners to volunteer their experiences. This way, learners become resources for each other. A big part of the training class is computer exercises that simulate what learners will be doing on the job. Mike walks around the room while learners tackle these exercises so that he can check how they're doing and give supportive feedback. Mike is an effective trainer. He sets up a comfortable learning environment. He establishes credibility by presenting his experience as a knowledgeable black belt and by starting the class on time. Mike also fosters a collaborative atmosphere for learning by encouraging learners to share their experiences with each other. Hands-on workshops provide opportunities for learners to apply their knowledge and skills, and Mike provides supportive feedback while learners do their exercises. Both during and after training, you must gather information that enables you to evaluate whether the training meets its objectives. Let's consider some of the ways you can gather this information. Learners can tell you how effective the training is, so ask them for feedback throughout. Find out whether the content is in line with what they expected to learn. Ask whether learners feel like they've achieved the objectives. Also, during class, you can use question and answer exercises to evaluate how learners are progressing toward their goals. If you find that objectives aren't being met, make adjustments as you go along. Another way to gather information that enables you to evaluate whether the training meets its objectives is to observe learners' behavior and attitudes. If learners look confused, you need to find out why. Watch for eye rolls and mutters of, "What a waste of time." These are direct indications that learners aren't getting what they need, or that training techniques aren't effective. It's also common practice to ask learners to complete evaluation questionnaires when a training session is complete. Questionnaires capture learners' impressions of the training, as well as their thoughts on how to improve a training experience. You can access the job aid sample evaluation questions after this video for assistance when developing your own questionnaires. Don't forget to follow up with the learner's supervisors. Training is a path to improved performance, and supervisors are the best source of information about this. You may decide to create another questionnaire, or you might want to phone individual supervisors to get their feedback. Relationships created during the training experience shouldn't be abandoned once training is over. So be sure to follow up by getting in touch with learners after the training. Ask how team meetings, data collection, and other aspects of the project are going to determine whether trainees have the time, resources, and mentoring support they require to put the training into practice. If you promised answers to questions, provide the answers. If you agreed to serve as a resource, make yourself available. Training is a critical aspect of a Six Sigma project. A good training program prepares people for coming change and gives them the knowledge and skills they need to work effectively with improved processes. Training maximizes the organization's most important resource, its people, and ensures that their skills and knowledge keep pace with the organization's ever-improving processes. You can access the job aid Tips for Presenting and Evaluating Training after this video for some guidelines on how to prepare and evaluate your training programs. Before you can train people, you must engage their interest. Techniques for doing this include varying your presentation styles, modes, and media, using appropriate humor, including good examples, showing enthusiasm, and telling stories from your black belt experiences. Once you've engaged the learners, you can train. Tips for effective training include establishing and maintaining credibility, conducting training in a collaborative and facilitative way, creating a comfortable learning environment, providing opportunities for learners to apply knowledge and skills, and providing supportive feedback. It's also very important to evaluate the training. You do this by asking learners for feedback throughout the training, observing their attitudes and behaviors, using evaluation questionnaires, and getting in touch with learners after their training. People don't want documentation, they want answers. But without documentation, no reliable answers would be available. Information would be passed on by word of mouth, getting more garbled and confusing as it passes from one person to the next. In describing how processes work, how employees perform when interacting with processes, and what the performance standards are, documentation is an essential control element that provides continuity throughout the Six Sigma organization. A thorough documentation system adds value to an organization. Documentation provides many benefits. Let's consider a few. One benefit is that it clearly describes management's views on quality and how the organization's quality goals can be fulfilled. In addition, it records lessons learned during project development, ensuring that Six Sigma teams don't have to relearn the same lessons again and again. It also provides a record of agreed-upon best practices, and so helps to eliminate variation and undesirable changes in the way people work. Another benefit is that it is a basis for training new personnel. It also provides a baseline for process improvement and is dynamic and can be continually adjusted as processes and conditions change. Documentation is useless unless it's up to date. So at the end of a Six Sigma initiative that has produced process changes, you must develop new or update your existing documentation. This is why your deliverables for the control phase should include a monitoring plan, a response plan, and new procedures. Your organization may also have additional documentation requirements. There are some guidelines to follow when writing documentation. For instance, you'll always want to write for your audience. Don't include technical information or use technical jargon if the audience can't understand it. By the same token, include schematics and technical diagrams, and use appropriate technical terminology when writing for technical personnel. Another guideline is to keep it simple. Picture your audience, think about what the people need to know, and keep your instructions simple, brief, and easy to understand. Use diagrams and pictures whenever possible to clarify written instructions. In addition, plan how you will keep the documentation up to date. Establish procedures for issuing periodic updates. Use revision control sheets with your updates to notify users what changes are being made and why. Also, make sure everyone who needs the documentation can access it quickly and easily. If people can't find the documentation, or worse, don't even know it exists, you've wasted a lot of time and effort creating it. And as a final guideline, when applicable, always include directions for what to do and who to contact in case things go wrong with a process. Consider this example. Tim is an operator with a printing company. 2 weeks ago, he was sent for training on how to operate the new high-speed printer. Today is the first chance Tim has had to put the training to use, and he can't remember how to fine-tune the forms loading process. Somebody told Tim there's a procedures manual around somewhere. Tim finally found the manual on his supervisor's desk, but it didn't help. Whoever wrote the procedures didn't know much about what Tim and his colleagues do in printing services. The manual has way too much detail and not enough graphics and schematics. Tim was only one of many operators to report problems with this documentation. Eventually, the manual was rewritten to make it simpler and tailor it to the right audience. Also, an adequate number of copies was distributed and placed in prominent locations throughout the department. Consider another example. Marcy is a technician for a company that produces large glass panes for industrial construction. The workflow on her floor has been reorganized as a result of a recent Six Sigma initiative. As Marcy steps through the new process, a glass pane becomes misaligned at her workstation. Marcy hits the emergency stop button and looks around for help. Marcy spots a schematic on top of the machine and grabs it, hoping for realignment instructions. The schematic is for the wrong machine, so it doesn't help at all. It takes 15 minutes for someone to come and help Marcy, by which time the workflow has stopped and there are significant downstream delays. Marcy relied on documentation to help her resolve a potentially dangerous situation. Unfortunately for her, the correct documentation wasn't available. After a Six Sigma initiative, people are getting used to new ways of doing their jobs, and they need the support that up-to-date documentation can give. Documentation is an essential undertaking and an asset for an organization that seeks to thrive. The four main types of documentation are the manual, procedures, work instructions, and records. These are often depicted as a hierarchy in a pyramid shape. The manual is at the top of the documentation pyramid. Manuals contain the organization's policies on the quality of products and materials, the objectives of the policies, and approaches for ensuring quality is maintained. Procedures are at the second level of the hierarchy. Procedures describe the responsibilities of various personnel in getting the work done. They describe what people do and when they do it. Standard operating procedures, or SOPs, are often included at this level. Work instructions are below procedures, at the third level of the hierarchy. Work instructions specify how to perform the tasks. Work instructions are step-by-step directions for how to perform a task or part of work. And finally, records are at the bottom of the hierarchy. They provide evidence that work has been completed. Records are the documents that provide evidence you are following your processes. Consider this example. Bill is in training to be a purchasing agent for his organization. Bill's supervisor gives him an assignment to locate all of the documentation associated with his job. Bill starts online with the manual. The manual is available on the intranet. After accessing it from a menu, Bill selects the purchasing link. A page opens that gives him an overview of the purchasing function, his company's philosophy with regard to purchasing, a list of the people responsible for purchasing, samples of records, and instructions on how to complete purchase orders. Bill also finds a list of procedures associated with purchasing. He clicks one of the SOPs and finds that it specifies how to work with the company's suppliers. In addition to listing the SOPs, the manual includes the names of work instructions describing specific tasks that purchasing agents are required to perform. Bill locates the instructions for all the tasks he will perform on the job. From the intranet site, Bill is also able to access records that are kept online, and in doing this, he becomes more familiar with how the purchasing process has performed in the past. Bill has followed a chain of documentation from the top to the bottom. The manual provides an overview of his department's mission and an overview of the purchasing function. The manual points to the SOPs and work instructions that purchasing agents use. And the work instructions refer to the records that will be generated as a result of the procedures and work instructions. Documentation is an important control element for a Six Sigma organization. It serves as a record of best practices, as well as a baseline for assessing current performance and practices. Good documentation must be brief, clear, and up-to-date. It should be written for the audience who will use it. That is, if the audience is technical, use the appropriate technical terms. If the audience is non-technical, be careful not to use technical jargon. There are four main types of documentation: the manual, procedures, work instructions, and records. These are often depicted as a hierarchy in a pyramid shape. The manual contains the organization's policies on the quality of products and materials, the objectives of the policies, and approaches for ensuring quality is maintained. Procedures describe what people do and when they do it. Work instructions are step-by-step directions for how to perform a task or part of work. Records are the documents that show that you follow your processes. Documentation is an important element for sustaining Six Sigma improvements. An organization generally requires 4 types of documentation, which can be depicted as a pyramid. At the top of the documentation pyramid is the manual. The manual provides or points to all of the information that users need to effectively use a process or system. Manuals are unique and are developed according to an organization's policies and needs. However, the categories of information tend to be standard, with some variations. Many templates are available for putting a manual together. The template you'll use in this course is a well-constructed general template that companies in any industry can use. Section 1.0 of the template is called Management Certification and Project Team Authorization. This section contains the signatures of top managers and the project's leadership team. Signatures certify that the information in the manual is accurate and approved by upper management. They also certify the legitimacy of the project team and give authority to its work and recommendations. Section 2.0 of the template contains the table of contents and orientation information. This section lists the major sections of the manual along with a brief description of the contents of each section. It may also contain definitions of acronyms, terminology, and abbreviations that are used in the manual. A third section is the General Information section. This part of the manual describes the system and processes in clear, plain language. General information begins with a system or process overview, and this section may contain a number of elements. For instance, it may contain a list and flowchart of the major functions performed by the system, as well as the titles or names of people responsible for the system. In addition, it may contain the system's operational status, such as operational, not operational, or undergoing modification. Another element it may contain is a list of support functions. Another element contained in the General Information section is project references. Project references are simply a list of source documents that were used to prepare the manual. These should be listed in the order of their importance to the manual's users. The next element is contact information. Contact information lists individuals who can provide additional process information and help with troubleshooting. For example, contacts may include the help desk, development, and security personnel. Contact information describes the type of help the contact can provide and gives each contact's name, department, telephone number, and email address. And a final element in the General Information section is the Authority and Permission Statement, which is a warning statement about unauthorized use of the system, data, software, reports, and documents. The next section in the template is a high-level summary of the process or system. This is the meat of the manual. In plain and simple language, the system summary describes the functions and architecture of the system. Let's consider each subsection in the system summary. First, configuration, inputs, and outputs describe the specific processes, their configuration, communications, and the networks they use, including the key process input and output factors. The second subsection is information and workflows, which briefly describe and illustrate the overall flow of data in the system. Next, system accessibility describes which user groups have access to the system and the levels of restrictions placed on each group. And the fourth subsection, contingency plans, describes how operations will continue in the event of an emergency, disaster, or accident. These types of plans include the names and phone numbers of people to notify and explain the effects of degraded performance on user groups. Note that this section relates to catastrophic emergencies that affect the entire system or process. Emergency procedures for chemical spills or glass breakage are covered elsewhere in departmental procedures. The next section of the template is Use of the System. This section contains high-level procedural descriptions divided by function and subfunction. Each function and subfunction is described in detail, which should include narratives and screen captures. In addition, this section provides detailed instructions for accessing the system, including how to obtain a user ID and password and how to log on to the system. The manual should also contain detailed reporting instructions. The reporting section contains copies of each kind of report produced by the system. Each report is accompanied by field-by-field descriptions and screen captures, along with complete instructions on how to request or generate the report. Sometimes the actual reports are placed in an appendix to the manual. The second level of the documentation pyramid is procedures, which identify the what, where, when, and who of a process. Procedures differ from work instructions in that procedures describe processes and interactions, while work instructions describe how to perform tasks or small discrete pieces of work. Procedures often consist of multiple tasks, so procedures documentation should contain lists of the associated work instructions. Standard operating procedures, or SOPs, document important operations that must be performed the same way across an organization. For example, the way in which people contract with external vendors is probably standardized, as is the way people interact with the payroll department. These processes would likely be documented as SOPs. Some organizations include their standard operating procedures in the procedures category, others include SOPs under work instructions. In this course, SOPs will be included with procedures. Procedures documentation, especially SOPs, serves as an important control element over how processes are communicated and performed throughout the organization. Procedures help to enforce standard behaviors, and they ensure that everyone has a common information source for important organizational processes. Typically, procedures are written for processes that meet all or some criteria. Let's consider some processes that require written procedures. First is processes that are routine, but everyone must strictly follow them, such as working with payroll. Next is processes that are lengthy and complex, such as conducting year-end inventory. Then there are processes that require consistency, such as steps in hiring a vendor. Processes that involve documentation, such as disciplining a worker, and those processes that produce serious consequences if done wrong, such as steps to guarantee safety, also require written procedures. And finally, there should be written procedures for processes that involve significant change, such as installing a new computer system. When documenting procedures, a template is often used. A basic template format would require documenting certain elements. Let's take a look at the different sections of the template format. First, the purpose section describes the intended use of the procedure. It may also define the audience and the scope of the procedure and the objective. Then there's the policy section, which is a statement that gives weight to following the procedure as written. It also describes any rules that must be followed to ensure the procedure is carried out properly and in accordance with regulatory requirements. Next, the responsibility section lists the titles of people who are in charge of administering the procedure, along with their roles. It may also describe the approvals that are needed before the procedure is performed. And the materials section describes the minimum equipment and materials needed to make a decision or carry out the procedure. It also provides the locations of the materials. For example, for a decision, the materials section would explain the criteria used to make the decision. For a procedure, this section might list forms, materials, and safety equipment. And finally, the procedure section lists the ordered steps required to carry out the procedure. The format can vary. For instance, procedures may contain narratives, visual flowcharts, process maps, or some combination. The procedure section may also list or point to associated work instructions needed to correctly perform the procedure. Procedures are an important part of documentation because they help you to establish control over your processes. By specifying the what, where, when, and who of a process, procedures help to ensure that everyone in the organization has a common understanding of how work is to be performed. Work instructions are at the third level of the documentation pyramid. Work instructions are step-by-step directions for how to perform specific tasks. They typically aren't used to document tasks that require interaction between or among workers. Each task is usually done by a single worker. Work instructions can be formatted as a written description, a visual flowchart, or some combination of these. And, to make it easy to understand the information, they should be written to suit the needs of the specific audiences. As much as possible, You must eliminate any need to interpret work instructions. Different interpretations lead to variations in performance. Here is an example of how work instructions are used to resolve problems. An aircraft parts manufacturer relies on the packaging department to deliver undamaged parts to customers. One of the needs in this department is a set of work instructions for assembling the complicated boxes the company uses. The documentation department creates poster-sized visual instructions that clearly document best assembly practices. The posters are hung at each workstation on the assembly line. As a result, waste and damage are greatly reduced. Level 4 of the documentation pyramid consists of records, data collected on the operation of processes and products. Records can show that authorized processes and regulations are being adhered to. Also, records serve as an audit trail, as evidence that a procedure or task was performed. In addition to the records an organization chooses to keep, some records must be kept as evidence of compliance with regulatory requirements. If an organization kept every record, it would be drowning in paper. Careful consideration must be given to what records to keep, where to store them, and when, if ever, to purge them. Examples of the kinds of records an organization may choose to retain include customer reviews of products and management reviews of products and systems. Organizations may also choose to retain documents used in design and development activities, such as inputs, reviews, verification, validation, and changes. Other kinds of records are calibration requirements and results, evidence of processes and products meeting requirements or failing to meet requirements, and materials generated during internal audits. Organizations may also choose to retain results from product testing, evidence of preventive and corrective action, and test data used in systems testing. Distinguishing between work instructions and records is simple. Work instructions tell or show how to perform an action. Records are tangible evidence that the action was performed and may also preserve information about the success or failure of the action. The 4 levels of documentation are the manual, procedures, work instructions, and records. Common categories of information in manuals include management certification and project team authorization, table of contents and orientation information, a general information section, a summary of the process or system, a description of how to use the system, and reporting requirements. Procedures identify the what, where, when, and who of a process. Procedures contain multiple tasks and may document an entire function. Standard operating procedures document operations that lend themselves to a standardized procedure across an organization. Work instructions document how to perform specific tasks. They must be clear, unambiguous, and written for the audience that will use them. Records are evidence that work has been done and that regulations are being followed. A Six Sigma initiative by itself doesn't guarantee long-term improvement. Processes degrade over time, customer requirements change, and employees tend to drift back into old habits. To maintain improvements, new processes must be continually evaluated. Consider this example. Toward the end of a Six Sigma project, the team is busy identifying and documenting lessons learned and completing all of the documentation. At this point, the Six Sigma team, along with process owners and others from within the organization, must identify and apply some tools and measures for ongoing evaluation of the improved processes over the short term, the next few months, and the long term, the next few years. The tools should be of 2 types: tools that have the capability of monitoring the issues, limitations, and constraints that get in the way of the improved process, and tools that can help to identify opportunities for further improvement as they become available in the future. Evaluation is part of a continuous improvement loop. Improved processes are continuously evaluated, further improvements are identified and made, documentation is updated to establish and communicate new baselines, and new processes are implemented. Then the loop begins again. At the heart of an evaluation process is measurement. A balanced mix of measurements must be achieved in order to monitor overall process performance and maintain gains. Customers' requirements must also be assessed in order to respond quickly to any changes. 2 types of measurements are commonly used to evaluate ongoing performance: performance measurements and opportunities analysis. Performance measurements provide status information on where a process is relative to its goals and performance objectives. And opportunities analysis is a process of finding potential risks and opportunities for improvement. Six Sigma provides many tools for measuring performance, but not all of them are appropriate for ongoing evaluation of the improved processes. You must carefully choose which tools or metrics to use. The big question is, what do you measure? At a minimum, you must measure performance, quality, and financial results of the products and services produced using the improved processes, and also the current capability and stability of these processes. Let's consider each performance measure in more detail. Six Sigma metrics that are useful for ongoing evaluation of performance results include rolled throughput yield, RTY, defects per unit, DPU, and Sigma levels. Some of the other metrics that are used to measure quality and process behavior on an ongoing basis in Six Sigma are defects per million opportunities, DPMO, cost of poor quality, COPQ, and control charts. And financial results are measured by such statistics as sales figures, market share, return on investment, ROI, net margin, and cost of poor quality, COPQ. It's imperative that Six Sigma process improvement also improve the bottom line. Increasing costs or decreasing ROI likely indicates a need for further improvements. And finally, capability indices CP, CPK, and CPM, and performance indices PP, PPK, and PPM are highly useful in combination to determine whether performance continues to meet specifications or if more adjustments are required. In addition to measuring performance, you must be on the lookout to find improvement opportunities and to identify risks and nonconformities based on a big-picture review of the department, organization, and business environment. Let's consider some common tools for opportunities analysis. One tool is audit results. Audit results reveal the effectiveness and efficiency of operations, reliability of financial reporting, compliance with regulations, and alignment of processes with documentation. Another tool is SWOT analysis, which you can use to identify the organization's strengths and weaknesses and any opportunities and threats present in the business environment that directly or indirectly affect the processes. Benchmarking results is a third tool for opportunities analysis. Benchmarking results indicate how a product and its performance characteristics compare with those of best-in-class products in the marketplace. There are other measures commonly collected or used on Six Sigma projects that aren't useful for ongoing evaluation. You need to carefully strip away any tool that doesn't directly measure the process being evaluated, caters to an early analysis of the process, or aims at investigating the process problems. Then use the right tools to measure what you need. To evaluate a new pull system process, you wouldn't use a stakeholder analysis or the 5 whys, as these are early analysis tools that would have been used in earlier phases of DMAIC. You wouldn't consider tools that have no bearing on the improved process. Say your company recently implemented Six Sigma to improve cycle time in the order fulfillment process. Someone suggests using defects per unit, or DPU, to measure the new process's performance on an ongoing basis. You realize DPU measures the performance of the production process, so it's not the best tool for monitoring cycle time. In deciding what to measure and what to ignore, a good rule of thumb is to ask yourself, does this measure help us gauge the overall performance of our process in the future and provide indicators for reevaluation for further improvement? If the answer is yes, the measure should be included in your evaluation. The measurements you collect in your evaluation should be documented in a quick, easy-to-read format and sent to management and the executive committee. The executive committee, or an oversight committee, must decide how to respond to ongoing process improvement issues. Consider this example. Dana is a black belt at an electronics firm. Her company has been working for a year to develop a product that recently took the market by storm, a fast wireless modem that supports a broadband connection. A month after the product launch, Dana begins to gather data to evaluate the improved processes that helped lead to the breakthrough product. Let's consider how Dana will assess performance by analyzing some categories of results. One category of results is performance results. She collects data on the sigma level of the modem manufacturing process. The results tell her that production is holding steady at the desired performance level for all shifts. Another category is quality results. A government regulatory agency has mandated more stringent cost management standards to decrease quality-related costs. The current quality cost levels of Dana's process are high, but the process will need further improvement to meet the requirements. The next category is financial results. Dana finds that since the product produced by the improved assembly process was introduced, the company's market share has increased, and sales figures and net margin are climbing. And a final category is process capability. A capability study indicates that the process capability index has not gone below 2.0 since the launch of the improved process. This means that the capability of the process to meet its specifications hasn't degraded. Dana also talks to salespeople to find out about new customer requests and changes to requirements. The sales department has been getting inquiries about whether the product will interface with new gaming technology on the internet. Because the product doesn't support the software, savvy customers are purchasing technology from a competitor in order to patch Dana's product and run their games. The sales department is recommending a product upgrade so customers won't have to patch the product to run gaming applications. Dana agrees to follow up with the executive committee about the need for an update. Dana has gathered a great deal of data, but she also wants to do an opportunities analysis. For this, Dana analyzes audit results. An audit reveals that one step of the process is at risk for failure. Dana notes that there should be a formal sign-off at this step to mitigate the risk. Next, Dana analyzes benchmarking results. The benchmarking results reveals that the company's strongest competitor has launched a new process that enables it to cut costs by as much as 12% without sacrificing quality. Dana's company will have to respond to this challenge by setting its cost reduction targets to remain competitive in the long run. Dana also performs a SWOT analysis. The SWOT analysis indicates that customers are demanding greater evidence of green thinking and cleaner technology throughout the electronics industry. Dana recommends immediately looking into disposability issues, recycling options, and greener manufacturing. Using a variety of analysis tools and methods to attain a holistic perspective, Dana has determined that her organization is sustaining controls and maintaining improvements. However, she has also learned that market forces are rapidly evolving. Further improvements will be needed very soon to meet demands from customers and challenges from the competition. Control charts, control plans, and lagging and leading indicators can be used on an ongoing basis for two purposes. One purpose is evaluating the improved process, product, or service. Another purpose is monitoring key organizational metrics to ensure that improvement gains are maintained and the process is delivering the expected organizational value. Once improvements are implemented by the Lean Six Sigma or LSS team, you need to determine with certainty if a process is in control or requires further adjustment. It's crucial to maintain the improvements made to that process. Although all processes are subject to some variation, you can take steps to control excessive variation by using a tool called Statistical Process Control, or SPC. SPC primarily uses control charts to determine if a process is out of control. Control charts are excellent tools for monitoring processes over time. A control chart is used for consistently evaluating processes to determine whether or not the process is on track. Once you've determined that a process isn't operating as expected, the goal is to find the sources of variation and apply the necessary corrective actions to control the process. Control charts have three key objectives. A key objective of control charts is to monitor process performance to find out if changes occur. Monitoring performance entails determining the natural range of a process. It also involves assessing how the process measures up to certain rules. Apart from control charts, Six Sigma practitioners use a number of other basic quality control tools, histograms, run charts, and check sheets to monitor processes. A second key objective is to identify causes of variation so that appropriate measures can be taken to eliminate special causes. This involves using statistical analysis to help identify sources of variation. It's crucial to distinguish between the two. If you adjust a process in response to common cause variation, known as overcontrol, it could result in more variation, not less. On the other hand, if you fail to respond to special cause variation, it could also result in more process variation, known as under-control. Six Sigma practitioners distinguish between special and common cause variation by examining runs of data and tracking trends exhibited on control charts. Controlling and improving process performance is the third key objective. This includes reducing variation in the process. Even when processes are within specification, excess variation can translate into extra costs. You might be able to eliminate these costs using process improvement. In evaluating a process, control charts are divided into zones or regions formed by plus or minus 1, 2, and 3 standard deviations from the center line. You set control limits at the two extremes of this range. In a natural or in-control pattern, the fluctuations of the data points are consistent and predictable, and all data points fall within the upper and lower control limits, UCL and LCL. Certain visual signs should set off alarms about the state of a process because they may indicate trends in the data. Trends are visual indicators that indicate a potential problem with a process. A control chart is divided into 3 zones. The zones are the regions formed by plus or minus 1, 2, and 3 standard deviations from the central line. Control limits are set at the two extremes of the range. Zone C has a normal distribution in an in-control process, displaying 68% of points falling within 1 standard deviation, or SD, of the mean. Zone B displays 95% of points within 2 SDs, and Zone A displays 99.7% of points within 3 SDs. There are rules you can apply to test for trends like process shift, freaks, process drift, recurring cycles, systematic variation, and stratification. However, in some Six Sigma situations, control charts won't always map to any of the broad rules to indicate visible trends. Your job as an LSS black belt is to dig deeper to find the possible causes of a problem and identify corrective measures. You can use control charts to do this. You need to know how control limits differ from specification limits. Control limits are calculated from process data and represent the voice of the process. And specification limits are usually determined by the voice of the customer and other factors external to the process. For instance, the voice of the business and its strategic goals, industry standards, or regulatory requirements. You also need to differentiate between defect and control. A defect is determined by the process violating the specification limits, whereas a process would be called unstable or out of control when it violates the control limits or exhibits an abnormal behavior when plotted on a control chart. A process that's within control is likely to have less variation, and most of its data points are expected to be within the specification limit. Such a process will result in products and services that have fewer defects, are of better quality, and require less rework, scrap, and inspection. Control plans are living documents used to carefully monitor key inputs and outputs of a process to ensure stability and maintain control. They help to organize relevant information about a process or product by clearly outlining methods, actions, responsibilities, and expected outcomes. Although control plans may vary, there are 9 elements that are considered standard. First of all, a control plan name must be included so that the plan can be distinguished when placed into other documents, such as operating instructions or a Six Sigma database. You should also include whether this is a prototype, pre-launch, or production plan. And you should provide a unique reference number for the plan, such as 6N-725. This reference number, sometimes called a control number, may be supplied by the responsible department. A third element, the team members. The core team refers to the individuals creating the plan and controlling the process, not the Six Sigma improvement team. Particularly if a cross-functional team is involved, you should provide the members' names and contact information for users who have any questions. If revisions are made by different team members from those who created the original plan, note them as well. Next, the current process owner should be assigned to the control plan, as that person will ultimately be responsible for its monitoring and execution. The process owner is a better contact person than the project black belt would be. You should also indicate the page number for each page of the control plan. Some control plans span multiple pages. Also, the date the control plan was created should be noted. It can be listed as the first date in the revision section, or it can be noted as the creation date under the revision details. The revision date is another element that must be included in the control plan. Whenever the control plan is revised, that fact should be noted. For each revision date, it may be useful to note the team members and a revision number as well. Noting the details of the types of changes that were made helps the reader focus attention on the specific area, such as revised targets, versus reading the entire document. You should also note the process customers. They are the recipients of the process output, and the objective of the process is to meet their input requirements. And finally, include a process description. The process description identifies and describes the product or process, or the component of the process to which the control plan applies. For example, updating, developing, printing, and distributing the operational policy manual among all employees describes the process and avoids confusion. Control plans are used for a transfer of responsibility, to hand off responsibility of the improved process to the process owners and their team members. Once the Six Sigma team designed a control plan based on the process that needs improvement, the control plan is handed off to the process owner for monitoring and execution. The Six Sigma team is responsible for passing ownership of the control plan to the operational managers and workers. The control plan must be updated and maintained over time as elements of the process are evaluated and improved. If the control plan isn't adequately maintained after handoff, the improvement benefits could deteriorate or gradually be lost. Careful consideration of the plan's interaction with the real world ensures successful execution of the plan and helps to keep the improved process under control. Performance improvement efforts such as Six Sigma rely on achievable business objectives and measures to be effective. Strategic goals and objectives set the course for the organization and determine the performance measures that need to be implemented. Leading and lagging indicators can collectively be useful during the strategic planning process. Lagging and leading indicators help gauge how a business is performing compared to the expected level of success the business wishes to achieve. Lagging indicators are reactive. They measure and identify results after the fact based on past events rather than current activities. And leading indicators are predictive. They focus on measuring short-term performance activities that can improve a company's chances of achieving performance goals and strategic objectives. When developing performance management systems, it is best to use a combination of leading and lagging indicators. Lagging indicators without leading indicators don't indicate how outcomes are achieved. Leading indicators without lagging indicators are equally ineffective. They fail to provide measurable performance data. When deciding on indicators to use, consider your organization's strategic objectives. You should use key objectives as the basis for identifying indicators that can uniquely integrate with each other, in addition to the functional elements of the organization. When conducting strategic planning, lagging indicators can be used to reflect on whether business goals and objectives are obtainable and realistic, because they focus on past results. Additionally, lagging indicators are vital to ensure strategic business activities are meeting the desired goals. Should an investment in an organization's capabilities not lead to increased profit, the organization may need a different perspective. However, without leading indicators, results will not help an organization achieve its business objectives. Leading indicators, such as customer satisfaction and investing in organizational capability, will drive the organization toward attaining its objectives, for example, to increase sales and profit. As a black belt, aligning strategic objectives with the organization's mission and vision and performance goals will help you ensure that lagging and leading indicators drive your business toward its specific goals. Therefore, Six Sigma projects should focus on achieving organizational goals across the organizational level, departmental level, down to the process level to ensure any deviation of processes is controlled in the long run. This is known as creating a line of sight from performance measures to organizational strategies and goals. A Six Sigma initiative doesn't guarantee sustained improvement. You must perform ongoing evaluation to ensure people don't backslide into the old ways of doing work. You must evaluate using a balance of measurements to obtain a holistic perspective on the improved processes. Processes may differ, But for any process, you should measure performance results, financial results, quality results, and process capability. You'll also want to take advantage of opportunities analysis and examine benchmarking results and audit results, and conduct a SWOT analysis to identify strengths, weaknesses, opportunities, and threats. Finally, keep an eye on customer requirements. Changing requirements should signal an immediate need to evaluate your processes and products. You can use control charts, control plans, and lagging and leading indicators on an ongoing basis for evaluating the improved process, product, or service, and for monitoring key organizational metrics to ensure that improvement gains are maintained and the process is delivering the expected organizational value. Statistical Process Control, SPC, is a methodology that uses control charts to determine if a process is out of control, since control charts are excellent tools for monitoring processes over time. Control plans are summarized documents used to carefully monitor historical and current key inputs and outputs of a process, while lagging and leading indicators help gauge how a business is performing compared to the expected level of success. It's best to use a combination of lagging and leading indicators when developing performance management systems. You can access the job aid Ongoing Evaluation Measures after this video to help you achieve a balanced approach to ongoing performance management. Analysts have identified that 70 to 80% of all quality problems are design-related. As a result, many organizations are rethinking their approach to process improvement. Tackling problems on the downstream end makes sense in some cases, but fixing problems at the source during design saves time and is more cost-effective. Typically, return on investment, or ROI, for a business is measured by dividing net income, the numerator, by total investment including costs, the denominator. ROI can be increased by decreasing the denominator or growing the numerator, or both. Many organizations emphasize more on growing the numerator, organizations' revenues, and net income. New products often make up a large portion of a company's revenue. Spending extra time and effort to design them well can help grow the numerator in two ways: more viable new products and increased revenues. C. Merle Crawford and Robert Cooper, experts in the field of product innovation and new product management, put forth 6 terms that have become commonly accepted to describe new products. The first term is new-to-the-world products. These are inventions and discoveries. They are also known as discontinuous innovations because they begin entirely new markets. When first introduced, portable media players, paper disposable diapers, laser printers, and in-vehicle security systems all began new markets. Then there are new category products which are not new to the world but are new to the company. When a photocopier company branches out into the digital camera market, it's more than just an extension of the current product. Digital cameras require new knowledge, methods, and equipment to produce. Next are additions to product lines, which are extensions to what the company currently produces. These additions may include new sizes or other variations on existing products. A soft drink company may introduce new flavors or produce diet, caffeine-free, or even vitamin-enhanced versions of the same basic product. Another term is product improvements. Examples of improvements to existing products include the added features and improvements available with each successive year's new automobiles or computers. The products are essentially the same, but better. Repositionings is another term Crawford and Cooper put forth. Repositioning takes existing products and targets new markets and new uses. Promoting aspirin as good for heart conditions and antacids as calcium supplements are repositionings. And finally, there's cost reductions, which occur when lower-cost new products replace existing ones. Consider the initial cost of portable CD or DVD players. Upon entering the market, these items cost hundreds of dollars. Prices steadily declined, and recent models can be found for a fraction of that cost. In the development of new processes, products, and services, design for Six Sigma, DFSS, is the preferred method for ensuring Six Sigma level quality and process performance right from the start. When people refer to Six Sigma, they are usually talking about Six Sigma DMAIC, The DMAIC process targets sources of variation in existing processes and then tries to reduce defects to near zero. DFSS is a closely linked strategy with many of the same characteristics. DFSS works on the same key principle, reducing defects, costs, and cycle time by reducing rework and the need for inspections. The difference is that DFSS focuses on future development and is proactive in nature. DFSS is used to design or redesign a product or service from the ground up to ensure that the product or service and its associated processes are virtually error-free from the start. DFSS lets you consider customer expectations and needs before the design is completed and implemented. It aims to create products, services, and processes that are robust, attractive to customers, and that inspire confidence in a company's ability to deliver value and excellence. As you will recall from your Greenbelt training, DMAIC and DFSS are similar in some ways and different in others. Unlike DMAIC, DFSS is not a single methodology, but rather a flexible overall approach. It encompasses several methods, such as IDOV, DMADV, and DMADOV. Access the job aid Six Sigma versus DFSS after the video to review the similarities and differences between the two approaches. DFSS provides tremendous benefit but is complex to implement and has high startup costs. Organizations must consider 4 other factors when deciding whether it's appropriate to deploy DFSS. One consideration is the Six Sigma levels of the organization's current development. You should also consider the amount of change in the business environment, the organization's prioritized project schedule, and the organization's capacity to roll out DFSS. Access the content designed for Six Sigma after the video to review this information. Consider an automobile manufacturer that has seen the defect rates in its drive shafts steadily drop over the previous 15 months since implementing a DMAIC improvement plan. In this case, sticking with Six Sigma DMAIC is preferable to DFSS. If the current process is heading toward maximum efficiency, DMAIC is working well and there is little reason to consider redesigning. Look at another example. A mobile phone manufacturer, after much research, has decided to go ahead and launch a new line of products, video phones. The company is losing market share in the current mobile phone market. Defect rates are not dropping, and Sigma levels are not increasing. All possible efforts, including several DMAIC projects, have been made to meet customer specifications, but customer satisfaction is still very low. This situation calls for DFSS because it is a new process, and all possible efforts for improvement have been made, but the output is still not reaching the desired Sigma level. DFSS works better as a strategy for designing new products or processes, or for redesigning existing products and processes that are optimized enough using DMAIC or other improvement methodologies. Next, consider this example. If a new soft drink company entering the market wants to develop a tastier and more consistent cola than is currently on the market, DFSS is the right choice. Because the product and the business in this case do not yet exist, the additional costs and problems associated with redesigning, retooling, and reallocating resources are not a limiting factor. Let's examine a final example. When a bulletproof surveillance device manufacturer started using the Six Sigma methodology 3 years ago, it yielded great returns. Various projects resulted in a smoother, quieter rotating device, increased pixel quality, and a more resilient armor coating to protect the device. But recently, the projects have been yielding smaller and smaller gains. The rate of improvement has flattened out. If, after many Six Sigma projects, the rate of improvement has slowed or stops, and you and your customers feel that the process and its outputs are still not at the desired quality level, then it may be time to redesign the process or product from the ground up using DFSS. New products are vital contributors to company revenues. DFSS is the preferred method for ensuring Six Sigma level quality and process performance when designing new products or redesigning old ones. To decide if the situation calls for employing DFSS methodologies, you must take into consideration the organization's current success with DMAIC methods, as well as its capacity, project scheduling, and Unlike the well-established and refined DMAIC method, no single methodology has emerged for Design for Six Sigma, DFSS. Essentially, all of the different methodologies encompassed by DFSS follow the general form of the New Product Development, or NPD, process defined by Milton D. Rosenau, Jr. Research shows that only a small number of new product ideas typically reach product launch, and an even smaller percentage are actually successful. Fewer ideas survive design, development, and launch stages to become winning products. No single comprehensive methodology for creating winning products has emerged, but various theorists and companies have put forth standardized approaches. For example, product innovation expert Robert Cooper offers what he calls a winning product list of 13 points. These include a unique, superior product, a strong market and customer orientation, pre-development work, good product definition, quality of execution, team effort, proper project selection, and top management leadership. There are 5 remaining points outlined by Cooper. These are prepare for the launch, speed to market, a new product process, an attractive market, and strength of company abilities. Access the job aid Winning Products after the video for a convenient list and explanation of Cooper's winning product points. One company that has formalized its product design development is Indiana-based GE Plastics. The company designs and produces engineered plastics through a series of distinct stages. GE Plastics provides a list of some of the best practices and tools to be used for each design stage. This list is not all-inclusive. One best practice is understanding critical characteristics for both external and internal customers. These CTX items, or customers' critical twos, are those aspects critical to time or delivery, critical to quality, and critical to cost. Another best practice is conducting failure modes and effects analysis, FMEA, to identify possible failures of the product or service and their potential impact. GE Plastics also recommends performing design of experiments, DOE, to identify key variables, their interrelationships, and their effect on the output of the process. Another best practice is benchmarking competitors or other facilities using competitive analysis and surveys. This will determine what the best performance being achieved is. The many variations on DFSS methodologies share 2 prevailing processes: a multifunctional methodology and a stage gate or toll gate process. One type of process is a multifunctional methodology. Traditionally, a new product moved from marketing to engineering to manufacturing, or whatever pattern the organization had established. If issues were found, the product moved back through the loop as needed until the design was complete. This relay method is now considered obsolete, and cross-functional teams have become the standard. Using a stage gate process or toll gate process has become the norm. Stage gating helps keep a new product process in control. Only when the product has satisfactorily completed the previous phase may it pass the gate and move to the next stage. Stages are usually based on the steps in the NPD process or smaller increments of the steps, varying significantly from organization to organization. The 2 core methodologies employed in DFSS are IDOV and DMADV. Both have their foundations in the NPD methodology, and they encompass the same overall processes of identification, design, and verification. IDOV stands for Identify, Design, Optimize, and Validate. DMADV stands for Define, Measure, Analyze, Design, and Verify. A third commonly used design methodology, DMADOV, adds an additional step of optimizing to the DMADV process. Under the IDOV methodology, you first identify and incorporate customer requirements into a formal product design. Then, in the design stage, you develop various concept designs, evaluate them, and select the best. The raw materials, process or service scope, procurement, and development plans are also developed. The optimize step includes establishing the product specifications, service parameters, or process settings. It also entails using process capability information to predict performance and optimize designs where possible. The final step is to validate results by test runs, verifying the design and quality control systems. The DMADV methodology is similar to IDOV, except the process is divided into 5 steps, with the first 3 steps being roughly analogous to the identify stage of IDOV. In DMADV, the process of identifying is parsed into define, measure, and analyze stages. In the define stage, the project goals and customer needs are taken into account. Then in the second stage, you measure customer needs and specifications. In the third stage, you analyze the process options against customer needs. The final 2 stages of DMADV are where you design the product and verify the results. You should be familiar with the DMADV and IDOV methods from your Greenbelt studies. Access the content DFSS Methodologies after the video to review this information. The define, measure, analyze, design, and verify stages of DMADV can also be recognized by the various tools in use at each stage. In the define stage, to establish project goals and find out who the customers are and what they want, the team may use a team charter, quality function deployment, failure modes and effects analysis, and benchmarking to identify CTQ factors. To determine customer specifications, benchmark competitors, and gather industry data during the measure stage, the team employs quality function deployment, failure modes and effects analysis, measurement system analysis, and other statistical tools. Next, to analyze the process options and their effectiveness at meeting customer needs, teams use many tools, including decision matrices and design capability and risk analyses. Then, to develop a detailed process and design that meets customer needs, the team uses tools like quality function deployment, failure modes and effects analysis, weighted criterion matrices, and design of experiments. Finally, to verify performance and deploy the design, teams conduct a measurement system analysis and implement statistical process control using flowcharts, run charts, Pareto charts, control charts, and process capability studies. The DMADOV process is another methodology commonly used to build new products to high-quality levels. DMADOV has 6 stages or process steps: define, measure, analyze, design, optimize, and verify. All the stages of DMADOV are similar to DMADV, except that DMADOV integrates an optimize stage before the final verify stage. DMADOV also follows the IDOV methodology closely. The difference is the DMA in DMADOV takes the place of the I in IDOV, and the V represents verify rather than validate. As with IDOV, the initial actions in DMADOV are concerned with defining the project. Team members ask, what are the project's goals? Who are our customers? And what are the things they want in the product? The define stage may ask, do customers want a more compact and lightweight digital camera, for example? After some sense of the project's goals and an understanding of customers is achieved, the second stage measures the opportunity in terms of precise specifications. The measure stage would, for example, determine that the weight of a digital camera must be less than 5 ounces to impress customers. Benchmarking competitors at this point is useful to determine what levels of service or features are being otherwise offered. In the analyze stage, the team determines creative solutions that may meet customer requirements. The options are evaluated to determine which best fits customer requirements. Several different designs for new digital cameras may emerge, for example. At this stage, some may be eliminated for being too small or prone to damage. In the fourth stage, the team develops a detailed process using tools such as DOE to verify the design meets customer needs. The fifth stage of the DMADOV method is to optimize the process. The new product or process gets tested to evaluate performance levels and impacts. If the product doesn't reach the desired levels, it is redesigned as needed. The DMADOV process ends with verifying that the performance of the finished product or process meets the desired customer needs. At this point, the product or process is deployed. There is no one standardized process for Design for Six Sigma. All of the various methods related to DFSS focus on customer needs and specifications and on early detection and correction of errors. Using cross-functional teams and stage-gate processes has become the standard to ensure more efficient design development. There are two similar core methodologies you can adopt to roll out DFSS, IDOF and DMADV. Both are based on the New Product Development (NPD) process. A third option, DMADOF, is a variation on DMADV. It adds an optimized stage and is another good option for designing a very high quality. Many people cook by intuition, adding items to the pot on a whim. Sometimes the results are spectacular, but more often, the concoctions are edible but less than noteworthy. Have you ever bought a product or used a service that seemed to have been designed the same way? It's astonishing how many products or services come all the way through the design process only to incur incredible expense downstream because the designers neglected an important characteristic. It's even worse when design anomalies aren't found until customers notice them. Analysts at AT&T Bell Labs understood these design issues and studied them extensively. In the 1980s, they came up with the term Design for X, DFX. Design for X is an umbrella term that describes methods for designing products and services that include all the important characteristics represented by variable X. A knowledge-based approach for designing products, Design for X, or DFX, focuses on a desirable characteristic or design constraint. These characteristics, or X's, put constraint on the design process. These can include cost, manufacturability, testability, and maintainability, as well as safety, user-friendliness, and concern for the environment. And the list of potential X's continues to grow. Design for cost requires you to find alternative materials, processes, and methods to achieve your cost goals for the product while still meeting your other design criteria. Introduced in the 1960s, the term manufacturability, also called producibility, means simplifying the manufacture of a product by reducing its number of parts and the number of manufacturing operations required to make the product. Testability, another characteristic, means that a product's performance characteristics are easy to measure. This often requires that the features of the product that are to be measured can be quickly and easily accessed. The next characteristic, designing for maintainability, means that the product performs satisfactorily over its lifespan with minimal downtime and expense. Generally, you achieve maintainability by using reliable components. Designing for safety means that you ensure the product won't cause harm to anyone during its manufacture, use, or disposal. Products must also be user-friendly. Their functions and controls should be intuitive and easy to use, and instructions should be clear, concise, and easy to understand. Finally, design for the environment requires you to think green and minimize any pollution that could result from manufacturing, using, and disposing of the materials associated with your product. To meet the design objectives for DFX, you need a vast and varied toolkit. Fortunately, DFX provides one. Unfortunately, the toolkit is so large that it's overwhelming. So you need to learn and use only those tools that are specific to the X's that are the focal points of your DFX effort. To achieve success with DFX, your organization must have 3 critical factors that establish a foundation for informed decision-making. The first is a full understanding of customer and industry requirements. To create products that have benefits and value for your customers, you must know their needs and requirements, in addition to your industry's requirements for the products or services you create. Next, you need access to data about the development process. To make the right decisions, full and detailed information must be available to the right people about the development process, including time, costs, and the processes themselves. And to control costs, you need to be able to break down your processes and understand the requirements and outputs of each sub-process and component. And finally, buy-in from managers, marketing, and development teams is critical. Product development is a team effort. When you have full buy-in, you have everyone's commitment to the process and the product. Commitment is essential to achieving an efficient and effective design process. To achieve understanding of requirements, access to data, and buy-in from teams, DFX users create multifunctional teams, drawing on the various disciplines involved in product development. By sharing viewpoints, team members learn to think about what's best for the organization, instead of making decisions from their own perspectives, which could affect the big picture in positive or negative ways. Consider the way in which an air conditioner manufacturer uses multifunctional teams. Product managers, vendors, and design engineers work together to balance marketing decisions, client requirements, and technical constraints. Designers work with the quality control engineers and drafters so that quality and functionality issues can be resolved during the design phase. And as issues get resolved, data is fed to the technicians so they can prepare to build the new products. Organizations can maximize their use of multifunctional teams by adopting an appropriate development methodology that will also help them achieve design effectiveness and speed to market. A product development methodology that is used successfully with multifunctional teams has two parts: a front end in which teams brainstorm and sort their ideas, and a back end that has a more structured series of new product development activities. The front end, or fuzzy front end, FFE, is the time before structured product development begins. Team members brainstorm new product ideas, perform research, negotiate features, and prioritize their ideas. Often messy and chaotic, the FFE is also a source of product innovation. The back end is called New Product Development, or NPD. NPD consists of 5 structured activities that build on the best ideas identified during FFE. Team members undertake a concept study to identify the unknowns associated with the product. For example, unknowns regarding the market for the new product, new technology required to produce the product, and potential new manufacturing requirements. Another activity is a feasibility study. Research is conducted to answer 3 basic questions. Is there a real market for the new product? Can the organization be successful in this market with this product? What are the real costs involved and the potential return on investment, ROI? Often, a formal business case is prepared to document the results of the study. Product development, the next activity, is when the product is created. It involves the identification of product specifications, customer requirements, and target markets. Multifunctional team members are identified for remaining development stages, and key phase gates, go, no-go decision points, are defined. After the product has been developed and shipped, maintenance tasks are performed to keep the product functional over its lifespan at minimal expense to customers and the organization. Continuous learning is the final activity. Data is collected about the process and the product and fed back to quality analysts, engineers, and designers, so they can incorporate it into their knowledge about the product. Conflicts are inherent in a process as complex as product development. Process constraints often clash with the wish lists of functional areas. Consider the conflicts during the development of a new electric drill. The engineers are concerned with functionality. They don't care about how the product looks. The marketing department is most concerned with aesthetics. Assembly wants more time than allowed by the schedule and budget constraints, and manufacturing's wish list conflicts with everyone. One tool for managing conflict is known as process-specific diagnosis. By making sure that each member of the team has access to information on requirements of the other disciplines, you can keep conflicts to a minimum. One technique to accomplish this is to have each discipline identify its most important preferences as process constraints, and then make everyone else aware of them. Making team members aware of everyone's constraints can prevent people from making unilateral decisions that cause downstream problems. For instance, imagine what might happen if a designer decided to increase the size of the logo on a luxury brand handbag without researching the effects the change would have on marketing and production processes. Put yourself in this situation. You're a designer working on an update to your company's best-selling word processing system. You want to make the system as robust as possible, and as a power user, you like features. The more bells and whistles, the better. You decide to beef up the product's functionality by adding drop-down menus offering extra features that you and other power users enjoy using. When the director of marketing receives your design, she is not happy. Her survey data shows that most customers don't like feature-rich drop-down menus. Her intention for this update is to streamline the product by stripping out less popular features and making remaining features easier to use. The programmers aren't happy either. They had wanted to beef up data security rather than spend their time and budget on adding functionality. The director of quality assurance is also concerned. The feature-rich design will force him to commit more of his staff to your project than planned, and possibly hire temporary workers to help complete the work. As it turns out, the project is chaotic, rife with conflict, and fails to meet its critical release date. Imagine the difference if you'd worked as a multifunctional team with marketing, programming, and quality assurance. Everyone would have had a voice in the final design and committed to it up front. You'd have avoided most of the conflicts. A DFX process involves creative exploration of different design approaches. The guidelines presented in Design for X are rules of thumb that can help you focus on desired characteristics and strategies, but they shouldn't be used to constrain creative exploration. DFX tools are designed to be used one at a time. Anything else can cause confusion and be very costly. When you select the tools for your project, be sure to keep these considerations in mind. You need performance metrics to assess the DFX tools you use, and you also need to understand the structure and use of the chosen DFX tools and techniques. Finally, you must know how the DFX tools affect each other in design and development contexts. Design for X, or DFX, is a knowledge-based approach for designing products to maximize as many desirable characteristics as possible, such as low cost, manufacturability, testability, maintainability, safety, user-friendliness, concern for the environment, and many others. DFX provides a vast and varied toolkit to help you achieve all of its objectives. To succeed with a DFX approach, you need an understanding of customer and industry requirements, access to data about the development process, an ability to break down processes into sub-processes and components, and a full understanding and buy-in from managers, marketing, and development teams. DFX tools and techniques are guidelines that are meant to spur creative solutions by suggesting broad strategies. They aren't intended to constrain creativity. They are used one at a time. In selecting a tool, you must know its appropriate use and how it interacts with other DFX tools and techniques, and you must have a way to assess the tool's performance. Preparing for a dinner party and cooking a meal for guests isn't easy. Before you start, you have to consider your budget, your guests' food requirements and constraints, and the proposed meal time. Then you think through your production capabilities, oven, knives, and pans, for example, and adjust the menu. You may need to make compromises, replacing items that cost too much or take too long with foods that are cheaper or faster to make. Product creation isn't as flexible as meal preparation, but the principles are the same. You must consider customer requirements, your budget, and the target date. Then you take careful stock of your manufacturing and production capabilities, available technology, machines, tools, processes, workers, and work environment. There's no point designing a product that your organization can't produce, although it's astonishing how often this actually happens. The Design for X dimension, called Design for Manufacturability and Producibility, or DFMP, addresses the issues involved in making, assembling, and testing a product. DFMP is defined as making products easier and less costly to manufacture or produce, thereby increasing profit margin and competitive advantage. In use since the 1960s, the terms manufacturability and producibility mean essentially the same thing. However, some analysts think of producibility as a subset of manufacturability and include design, assembly, and testing in the mix. Consider the design for an innovative new lamp. On paper, the design seems elegant and concise. Prototypes are built, they look beautiful and work flawlessly. But the design isn't created with manufacturing and production in mind, so the lamp can't be produced within reasonable, profitable parameters. Incompatibilities aren't discovered until the beginning stages of manufacturing. By this time, a lot of money has already been spent, with more waste to come due to rework and excess scrap. To avoid scenarios like this one, DFMP brings design, manufacturing, and production together early in the design process through the use of multifunctional teams. This aims to better meet customer needs, a faster and smoother handover to manufacturing, and a lower total product cost. The earlier these teams form, the more manufacturable and producible the resulting products will be. This holds true whether you're dealing with manufacturing, service, or transaction processes. DFMP has an enormous effect on costs and schedules, and there is a larger body of information available for it than for any other DFX dimension. In addition, DFMP activities are associated with and influence a large number of other dimensions. These include the design for several key characteristics, such as cost and profitability, disassembly and recycling, service and maintenance, and quality, reliability, and robustness. When you adopt a DFMP approach, you can realize many benefits for your project and organization. For example, lower production costs, simpler processes, increased productivity, and increased customer satisfaction. These benefits of using DFMP result from pursuing three main goals: design simplification, part standardization, and improved product quality. When designs are simplified, there is less risk of downstream rework and re-engineering, and costs decrease. With part standardization, manufacturing and production costs go down because there are fewer steps and considerations involved in manufacturing and producing a product, and costs decrease. And when product quality goes up, customer satisfaction also increases, customers buy more, and your profits increase. There is no simple recipe for making DFMP work in a particular organization, but there are several ways you can help to make DFMP successful. You can simplify your designs. You can also standardize components and processes and use the same components for more than one product. Furthermore, you can optimize the arrangement of the workplace, equipment design, and the use of the human body. Decisions made during the design period determine 70 to 80% of the product's costs. Simplifying the design can produce a high return on investment, ROI. You can often achieve this simplification through a rigorous evaluation of each part of a proposed design. This evaluation can take the form of questions about each part of the component. Three basic questions can be asked. First, is there an easier way to accomplish the function of this part? If a function can be simplified or a part eliminated, you can reduce overall manufacturing and production costs. Next, ask, is this part a custom part or can it be replaced by a standard part? Standardization can eliminate the need to change manufacturing and assembly processes that often accompany customization. It also reduces inventory. The final question is, can the overall number of parts be reduced? If you can reduce the number of parts, you can reduce the number of steps in the manufacturing and production processes. You can also minimize the opportunity for defective parts and assembly errors. Both of these strategies can create significant cost savings. When you are able to simplify a design by standardizing or eliminating parts, it's sometimes possible to computerize the manufacture or adopt a modular building block approach to assembling the product. Then you can save even more money by consolidating the number of steps required for assembly. Another strategy for applying DFMP is to standardize components and processes so that the same components can be used for more than one step, product, or part of product. When components are standardized, the manufacturer can place large orders for each part to obtain bulk discounts. To assist in the standardization effort, your organization may create a classification structure or database to store information about designs, materials, and parts. Design engineers will consult the stored information to learn how design problems have been handled in the past, as well as to determine if needed parts and materials already exist in inventory. By adjusting their designs to use existing parts and materials, designers can reduce costs and standardize handling and assembly operations. Another DFMP strategy is to optimize the arrangement of the workplace. Tools and materials can be kept in specified areas to save time, stored close to workers to eliminate unnecessary motion, and positioned to facilitate a logical and efficient sequence of motions. For example, a factory that makes bunk beds is equipped with saws, bins, conveyor belts, and chutes. Bins are located beside each saw to give operators access to the lumber they need. After they're sawn, raw pieces are placed on conveyor belts and sent for sanding, gluing, and staining operations. Scrap is tossed into chutes that are located beside each saw and removed from the cutting area immediately. Optimizing equipment design is another important DFMP strategy. Many businesses use computer-aided design, CAD software, to improve the design of tools and equipment. Equipment must be easy to use, and it must be adapted to the human body. For example, the saws that operators use to cut the lumber for bunk beds are equipped with both hand controls and foot pedals for ease of use. They have large vacuums to remove sawdust as it's generated, and they're equipped with safety features. When the forward motion of a piece of lumber stops for 5 seconds, the saw switches off. Of all the resources used to create products, none is more valuable than the human body. In addition to optimizing designs, tools, and equipment, DFMP also seeks to optimize the use of the human body. Each part of the body should be used in such a way as to elicit maximum efficiency with minimum effort. For instance, an operator whose job is to feed blanks onto a thread rolling machine should feed the blank between the two dies and remove the completed screw from the exit in one fluid motion. This eliminates excess motion and minimizes fatigue. Design for Manufacturability and Producibility, or DFMP, addresses issues involved in making, assembling, and testing a product. DFMP is defined as activities and tools for making products easier and less costly to manufacture or produce, thereby increasing profit margin and competitive advantage. The 3 goals of DFMP are to simplify designs, standardize parts, and improve product quality. In realizing these goals, substantial cost savings and ROIs are attained. There is no simple formula for attaining design for manufacturability and producibility. However, there are some strategies that can help in the effort. These include simplifying designs, optimizing equipment design, optimizing the arrangement of the workplace, optimizing the use of the human body, and standardizing components and processes so that the same components can be used for more than one product. Fast food was once a novelty, but now it's available on nearly every corner. With products that are familiar to everyone, fast food restaurants compete on the basis of taste and serving size, but their fierce competitive focus is on price. Price becomes especially important in the marketplace as the competitive playing fields level when products mature. When this happens, the market can become saturated with similar products, like fast food, and competition becomes increasingly based on price. Price also plays a critical role when affordability is your customer's primary buying criterion. For example, many elementary schools and most high schools require students to have calculators, but they don't want parents to have to spend much money. There are companies that target the affordability requirement and produce inexpensive calculators to meet the need. On another level, some manufacturing companies control costs by establishing in advance the prices they will pay for parts, making price their top priority. Suppliers that want to do business with these companies must meet their prices while still meeting all their other quality specifications. There is a basic difference between price and cost. Price is set by the marketplace. Cost is what you have to pay to create and sell your products. You can't control prices, but you must control costs. Between 70 and 80% of a product's costs are determined during the product design phase. Once a product's design is established, it's almost set in stone, and there's very little wiggle room for reducing costs. This means that you must start to manage your product's costs at the very beginning of the development cycle. The Design for Cost, or DFC methodology, can assist in this effort. DFC, also called Design to Cost, is a strategic cost management philosophy that's customer-focused, design-centered, and multifunctional. The focus of DFC is on removing excess cost as early as possible in the design phase. Success with the Design for Cost approach involves the same important characteristics as other Design for X or DFX dimensions you're familiar with. These characteristics include the following: knowledge of customer and industry requirements, information about the development process, and an ability to break down processes into sub-processes and components. Other characteristics are buy-in from managers, marketing, and development teams, an understanding of how all the DFX tools in use can affect each other, and performance metrics for assessing your tools. Consider this scenario. You're a process improvement consultant working on a new line of environmentally friendly office supplies. You're working with the product development and marketing departments of a large office supplies company. The market for these products is very competitive and price sensitive. Your goal is to deliver a high-quality product at a very competitive price and still make a decent profit. The product development department decides to adopt a DFX approach for designing the product and its associated processes. The first step is to form a multifunctional team with members from the product development, marketing, and sales areas. Your various team members share information about the customer and the industry the product is targeted for. Members of the sales department gather and contribute information about the potential customer base, current products on the market, and price ranges. You learn all you can about the proposed product line. The more you know, the better prepared you are to define project parameters and establish a competitive target cost for your product. You also brainstorm with your team on how to structure the processes to best meet your time and cost goals. This helps you identify areas where you can cut down on costs. For instance, involving the sales department at the very beginning of the design phase enables you to decide on the critical product features that must be in the product. This will help you determine costs associated with every step in the development and production processes. Your team members then help break down the entire process, from product conceptualization to delivery, into sub-processes to a granular level. Once this is done, you allocate costs at the detail levels, where you can see and manage them more effectively. For instance, your production team members can identify the sub-processes involved in converting raw materials into finished goods. By understanding each sub-process, including its cost estimates, you can determine costs for all major sub-processes. The support of managers and functional team members is critical, so you aim to get buy-in. Managers can ensure you get the resources you need for your project, as well as clear the obstacles from your path as you proceed. You decide to use DFC and Design for Manufacturability and Producibility (DFMP) tools. The tools complement each other to help you achieve your quality and cost goals. DFMP can be leveraged for cost reduction. For example, by using fewer and standardized components, you not only simplify the manufacturing process, a DFMP goal, but also potentially greatly reduce component costs and defects. You need to use two sets of metrics, one set to assess DFC tools and the other for DFMP tools. Such metrics as return to yield and defect per unit can help you evaluate whether sub-processes and components are meeting your DFC cost projections and whether your processes are creating high-quality and low-defect products. Metrics such as number of components used, cycle time, and ease of operation can be used to assess how well you're meeting your DFMP goals. Using the DFC approach requires you to creatively explore design alternatives that are within guidelines, using rules of thumb focused on cost. The approach also involves breaking down processes to find areas where costs can be cut and money saved. The multifunctional team is integral to your success with DFC. Team members share a deep knowledge of how products are developed. They're able to find the optimal processes, materials, and tools to make purchasing and design decisions that will help contain costs. When you use a design for cost approach, one of the first things you do is calculate the profit margin or target margin for your product. The target margin is the profit you want the product to make. Establishing the target margin is tricky. If you set it too high, you risk pricing your product out of the market. But if you set it too low, you won't get enough return on your investment, and you could risk your organization's future success. As a rule of thumb, the target margin should be set slightly higher than your company's current gross profit margin, say by a factor of 5%. The additional 5% is included to cover any cost increases that occur during development. Once you've established the target margin, you can calculate the product's target cost. The target cost is the total of the funds you can spend on the product for processes, materials, and machinery. You calculate target cost by subtracting your target margin from the projected price of your product. Target cost serves as your team's mandate for the DFC approach. It's also a tool for driving out excess cost from your production mechanisms. For example, in the design phase of a new product, if production costs are worked out to be higher than the target cost, you must adjust your product design and the production process to keep costs down to the target. Often, this effort results in squeezing out excess costs by identifying and adopting the most efficient and effective processes, materials, and machinery. Target cost is also a management tool for evaluating whether the product is worth the organization's ongoing investment of resources. At specified points during the development process, especially during design and project gate reviews, for example, the target cost is updated and evaluated. Based on this evaluation, a go, no-go decision is made to continue the project. Follow along to find out how a target cost evaluation process might work. The first question to ask is, can we achieve the target cost? If the answer is yes, then the evaluation is complete and you continue development. If the answer is no, you drill down to determine what to do next. The next question is, can we increase the projected price to cover the higher target cost? You might be able to identify and refocus on a higher-end segment of the market where customers expect to pay more. Then you could increase the projected price to cover the larger target cost. If you can't increase the projected price based on current functionality, ask, can we add some functionality to the product as a way to justify the higher target cost and increase the projected price? If the answer is yes, you must proceed with caution. By adding functionality, you may also increase the target cost even more. If all of your efforts to justify the target cost fail, the final question is this product so important to the company that it justifies the target cost? When the product is strategic, you may have no choice but to go forward with it, even though the target cost is higher than you would like. The decision whether to continue or cancel a project isn't always clear-cut. If you're dealing with a marginal situation, the decision can be very difficult. Don't commit to continuing a project just because you've sunk sizable resources into it. Instead, focus on the opportunity costs that you can gain by canceling it, including these: the opportunities your designers will have to work on more valuable projects, the opportunity to maximize your organization's finite manufacturing or production capabilities with a better project, and the opportunity to apply limited resources to better use. Price is important in the marketplace as products mature and the competitive playing field levels. It also plays a critical role when affordability is your customer's most important purchasing criterion. Between 70 and 80% of a product's costs are determined during the design phase. Design for cost, DFC, also referred to as design to cost, is a strategic cost management philosophy that is customer-focused, design-centered, and multifunctional. The target margin is the minimum amount of profit a new product must achieve. It's calculated by taking 5% of the company's average gross profit and adding it to the average gross profit. Target cost is equal to the projected price for your product minus the target. When was the last time you bought something that didn't work as well as the company promised it would? Were you able to return the item for a refund or exchange it for something else? Did you have it fixed at the company's expense? Or did you simply throw it away? Regardless of how you handled the problem, you were probably more than a little frustrated or angry. As a customer, you expect durability and reliability in what you buy. As a maker of goods and services, you're on the other end of the spectrum. You are responsible for ensuring that you don't inflict faulty products or services on your customers. Design for X includes two dimensions that can help you: design for testability, DFT, and design for maintainability, DFMaint. Testability measures the ease with which a component or product can be checked for performance to specification throughout the product lifecycle, from concept through design, manufacture, and maintenance. Testability is the ease with which the functionality of any product, component, or service can be determined to a desired degree of accuracy. The DFX discipline, Design for Testability, helps you to design processes, equipment, and facilities capable of producing a product or service that can be tested in a cost-effective and efficient way at various stages of its life cycle. DFT is used most often for situations where products and services need in-process testing, and testing is critical. To implement a design for testability approach, you need to involve engineering or quality assurance personnel very early in the design process. Their early involvement will help to minimize the cost of developing or acquiring new equipment, as well as to minimize the cost of testing the product at each development stage. 3 strategies are recommended with design for testability: automated test equipment, standardized equipment, and easy access to testing. Automated test equipment can be cost-effective in situations of high production volume. For example, a major software development company might use proprietary software simulation programs along with a custom-built kiosk-style PC to test each new software product in the alpha and beta phases. Also, use of standardized equipment can reduce lead time and costs of testing. For example, a software development company might use the same kiosk-style PC that it uses for testing to mass-produce DVRs and promotional CD-ROMs. Finally, easy access to testing should be a priority. Built-in testing is often preferred. For example, various engine parts on your car have built-in testing. If anomalous conditions occur, such as overheating or low oil levels, indicator lights inform you so that you can take immediate action. Testing goes hand in hand with another important DFX dimension, maintainability. Design for maintainability, or DFMaint, refers to the amount of time and cost required to test, calibrate, adjust, or repair a component, part, product, or process to a predetermined condition when using defined procedures and resources. The objective of design for maintainability is to create a product or service that can be maintained for the least amount of time, for the least cost, by the fewest support resources. Maintainability must be considered during the product's design. Trying to re-engineer a product for ease of maintenance later can be cost-prohibitive if it can be done at all. The ability to maintain a product quickly and easily and to keep it in good working order is essential for customer satisfaction. For instance, people who own cars wouldn't be pleased if they had to use a floor jack to remove spark plugs, or drop the engine to access and replace the muffler pipe. These kinds of poor design decisions shake customer confidence and can erode loyalty. The goals of design for maintainability include the following: reduce downtime, reduce user and technician time for maintenance tasks, reduce requirement for parts, and lower maintenance costs. There are specific methods that you can use to increase your product's maintainability. First, you can use modular construction. Creating a product with groups of subassemblies or modules increases maintainability. You can simply replace a malfunctioning module with a functioning one. Then you can repair the module and reuse it in a different product or recycle its components. You can also use throwaway parts. New parts are often inexpensive when compared to the cost of repairing a broken part, plus the production time that's lost when a part breaks or malfunctions. It's preferable to simply replace a worn-out or broken part with a new one and throw the old one away. Third, use built-in testing. Built-in testing makes maintenance easier because it can pinpoint the parts that are not functioning properly. Finally, you can operate parts in constant failure mode. When parts operate in constant failure mode, their rate of failure is predictable. This means that it can be plotted on a curve and understood statistically. If you know how frequently parts will fail, you can schedule them for replacement before failure occurs. For example, each part in your car's engine has a different rate of failure. Manufacturers know precisely how long each part will operate at optimum performance levels. They create maintenance schedules based on these failure rates. When you take your car in for its regular checkups, the mechanic knows which parts to replace and which systems to perform maintenance on based on these schedules. In addition to testability and maintainability, there are 4 other important characteristics that should be measured with a Design for X approach: the environment, user-friendliness or ergonomics, appearance, and packaging. The objective of Design for the Environment, DFE, is to minimize any pollution that results from the manufacture, use, and disposal processes associated with your products and services. DFE is becoming increasingly important as more businesses go green and the government passes more green legislation. There are many ways to incorporate DFE into your design processes, and you need to find the ways that work best for you. Some methods include minimizing waste, conserving energy and materials, reducing chronic risk, adopting accident prevention strategies, attending to recovery and reuse, reducing packaging, and following green disassembly processes. Here's an example of how a company might use a DFE approach. A major pharmaceuticals company maintains its expensive scientific equipment and instruments according to regular calibration and maintenance schedules. The company replaces the equipment when it begins to wear out or break down. The majority of the old equipment still has useful life, so it is reconditioned and sold to other companies, institutes, and schools. Equipment that isn't suitable for resale is disassembled, and the parts are sold if they're still usable. Design for user-friendliness, or ergonomics, has become a very important characteristic in product design. This DFX dimension measures how intuitive your product or service is to use and how easy it is on the body. The main emphasis of the approach is to help you make your products fit their users. There are many proven strategies you can adapt to achieve user-friendliness. For instance, you can simplify the steps for using a product. Instructions that accompany your product, especially when the product is to be assembled by the user, must be clear, concise, and easy to understand. You can also make controls and functions intuitive. When you are traveling, you may have found yourself utterly at a loss when trying to figure out how to turn on the shower in your hotel room. Make your designs fit with users' expectations. Similarly, don't hide the controls on appliances or personal electronic devices, or make them so tiny users can't find or use them. Another strategy is to anticipate human error. People make mistakes. You need to brainstorm how people will use your products and then build in appropriate safeguards so they don't hurt themselves or damage products when they make mistakes in using them. And finally, you can improve component accessibility. If you buy a lamp, you want to be able to change the bulb without taking the lamp apart. You need to make it easy for users to access components. In addition to being user-friendly, designs must be ergonomic. Say your company is designing a new desk chair. There are a multitude of ergonomic factors to consider, including the height of the chair, the size of the seat, the distance of the seat from the ground, the distance of the back support from the seat, whether to include arms and a footrest, how the user will adjust the seat, backrest, arms, and footrest, and last but not least, how to ensure the adjustments are simple for all users to make. Two other Design for X characteristics are Design for Appearance and Design for Packaging. Both characteristics are so specific to an organization's products that it's difficult to provide general guidelines. Appearance is among the most important aspects of a product, especially if you're selling to the consumer market. You want your product to jump off the shelves, and for this to happen, the product must be attractive to buyers. To end up with an aesthetically pleasing product, you need to make appearance a driving force and use it to inform your selections of materials, fittings, and finishes, for example, in the design phase. Packaging is a huge business in itself, with entire institutes dedicated to teaching packaging design and technology. When you use a design for packaging approach, you must consider how to disseminate your product in the most efficient manner. Your design decisions must account for the environment, user-friendliness and ergonomics, aesthetics, and cost. Design for Testability, or DFT, ensures that you make thorough plans for product testing at points where it is most useful. Strategies essential for a DFT approach include automated and standardized test equipment and easy access to testing. Design for Maintainability helps ensure that your products can be serviced for the least amount of time, for the least cost, and by the fewest support personnel. Strategies include using throwaway parts, modular construction, built-in tests, and running parts in constant failure mode. Other important characteristics include design for the environment, user-friendliness or ergonomics, appearance, and packaging. All of these characteristics must be considered early in the design phase. Having to re-engineer a product to include any one of them is the oft-quoted saying about the best-laid plans of mice and men quickly going awry applies to product design as well. Even relatively well-designed products may falter after launch once they encounter the wide range of factors and conditions that can affect performance. Traditional approaches to unwanted variation are reactive. When a problem in manufacturing is identified, measures are taken to identify the source and fix the problem. But even good control of manufacturing processes goes only so far in preventing product failure after launch. The Six Sigma approach is to identify and address the source of problems as early in a product's life cycle as possible. Robust design, also commonly referred to as quality engineering or robust engineering, takes that approach even further by being proactive. It focuses on improving the fundamental function of the product during the development processes. The concept of using a system of robustness for the evaluation and improvement of product development processes originated with engineer and statistician Dr. Genichi Taguchi. Current robust design methods incorporate many of his key quality imperatives. Using the concept of parameter control, robust design improves the basic function of the product or process in the design stage so that it is more resistant to random noise. Noise factors are largely uncontrollable, hence robust design reduces product variation by reducing the sensitivity of the design of the product to these factors. Correcting design defects when a product is already in the manufacturing phase is often costly. Follow along to learn how a navigation system manufacturer found this out the hard way. The manufacturer received 15,000 returns on its latest marine GPS system in the first month after product release. The allegedly watertight system continually shorted out, in some cases leaving boaters lost and stranded. 3 small seals that degraded rapidly in direct sunlight were implicated in the defect. The manufacturer spent time, money, and effort dealing with the problem. It had to reimburse customers, as well as handle the returns through retailers and by mail, and dispose of over 15,000 units. The company then had to identify the problem, redesign the product, and redesign the entire production process before reintroducing the item to the market. All of this lost time, productivity, and profit could have been avoided if the manufacturer had originally employed a design strategy to ensure a more robust product. The basic premise of robust design is that to ensure minimal impact of noise factors on the product or process, you must maximize the product's robustness in the design stage. There are 3 basic stages that comprise robust design. The first stage is concept design. It depends on the abilities and creativity of the designer in the selection of the process or product architecture. Decisions are based on available technology, cost, customer requirements, and any other relevant considerations. Parameter design is the second stage. Once the concept is established, the nominal values of the various dimensions and design parameters need to be set. In any product or process, there's variation that is controllable and also some variation which is beyond control, known as random noise. Parameter design, the focus of this video, is used to make a product or process more robust and less sensitive to the effects of variation in inputs, manufacture, and environment. The final stage is tolerance design. A tolerance is the total amount by which a given dimension may vary. Tolerance design is a more costly next step if parameter design is insufficient. Building on the data developed in parameter design, tolerance design determines which variables have critical tolerances that should be tightened. It balances the cost of tighter tolerances against the benefits to the product and customer. Loose tolerances can result in quality loss and rework, but tight tolerances cost more to design and maintain. Because of its cost, tolerance design is a last resort to improve robustness. In robust design, parameters are analyzed and controlled to create a design that can withstand variation in input conditions and the operating environment. You can choose to design for the lowest investment of time and money, the highest reliability, or an optimized combination of factors. In robust design, you choose the design factor settings, the parameters, and tolerances that will optimize performance. To do this effectively with the minimum number of engineering runs and expenditure of time and money, designers use Design of Experiments, DOE. DOE, also known as Statistical Design of Experiments, SDE, offers a systematic, rigorous approach to selecting and adjusting control factors. But before you can apply DOE, you must be able to recognize the parts the various factors play in the design. 4 elements need to be considered: control factors, signal factors, noise factors, and response. Control factors are parameters that are under the designer's control. An important distinction between different control factors is whether or not changing a particular factor will add cost to the product. Factors that add cost, such as changing materials, changing ingredients, or changes that require retooling, are usually associated with tighter tolerances of components, so they are often called tolerance factors. Factors that don't add any cost are simply referred to as control factors. Control factors must be triggered by a signal factor. The signal factor is the input used to trigger the intended response. The action taken to get a car to go a certain speed, stepping on the accelerator, is the signal. Getting up to the desired speed is the response. Noise factors are parameters that have the ability to produce an error in the desired response and are beyond the designer's control. The designer's job is to select control factors carefully so that the impact of noise factors on the response is minimized. Examples of noise factors in developing an automobile that will go 0 to 60 in 4.3 seconds might include the quality of gasoline, road conditions, and the driver's tendencies. The response is the desired end result, or output. For a motor, it might be hitting the desired RPMs, or for a thermostat, it might be achieving the correct room temperature. Successfully obtaining the response depends on two things: the control factors and the noise factors. The more well-designed the control factors are, the less the noise will affect the desired outcome. Take the case of an engine part such as a fuel injection pump. The signal for the pump is the throttle position sensor that requests a certain amount of fuel be pumped into the system. The response is the amount of fuel released. Control factors include the various component parts of the fuel injector pump and the way they're designed to interact. The measurements and the precise size of each component have a significant effect on performance. If each component is currently being machined to within plus or minus 1 micron of specifications, simply retooling to produce all 8 to tighter tolerances of plus or minus 0.75 microns might seem like a good idea. But this approach can be vastly expensive, and there's no guarantee it will lead to significant improvement in the robustness of the final product. The job of the designer is to determine what the appropriate control factors and settings are for minimizing deviation at the lowest cost. There are 3 basic goals of robust design: to identify the noise and controllable factors and assess their impact on the response, to determine whether controllable factors built into the design can make the design more resistant or insensitive to noise, and to determine how to manufacture the product at the lowest possible cost within the set parameters. One basic goal of robust design is to identify the noise and controllable factors and assess their impact on the response. A system of trials can allow you to analyze change in overall system performance when you subject parts to varying values, stresses, and experimental conditions simulating customer conditions. To determine the optimum combination of factors and levels for new products, you use orthogonal arrays. Orthogonal arrays are matrices in which you record the results of experiments with various controllable factors and noise levels. The optimum combination of factors and levels can be determined from the analysis. Another basic goal of robust design is to determine whether controllable factors built into the design can make the design more resistant to noise. Finding the combination of design variables and parameter settings that maximizes the signal-to-noise S/N ratio will allow the product to withstand any noise. While generally robust design seeks to optimize the S/N ratio, there are cases when a smaller S/N ratio is better. For example, smaller is better when you are dealing with deterioration, wear, or shrinkage. There are also situations when the nominal level is sufficient and a greater or lesser level is undesirable. This is the case for dimensions, clearances, weights, and viscosities, for example. The third basic goal of robust design is to determine how to manufacture the product at the lowest possible cost within the set parameters. If there are multiple ways of achieving a robust product or process, designers should choose the least expensive and the one with the quickest time to market. A classic example provided by Dr. Taguchi involves a tile manufacturing company in Japan. The company was having variation problems with a newly purchased kiln. The dimensions of the tile produced by the kiln were subject to extreme variation. The stacked tiles were baked inside a tunnel kiln. Tiles toward the outside of the stack tended to have a different average dimension and exhibited more variation than those toward the inside of the stack. The cause of variation was clear: temperatures were inconsistent throughout the stack. To correct this by redesigning the $2 million kiln would be a very expensive proposition. Getting a consistent temperature throughout was the obvious goal, but in this case, as the design of the kiln could not affordably be changed, temperature was treated as a noise factor. The designers explored other, more controllable factors to find out if the dimensions of the product could be made insensitive to temperature. The challenge was to make the product robust enough for the existing kiln to produce consistent tile. Those knowledgeable about the process brainstormed 7 major control factors that could affect the tile dimensions. These were the limestone content of the mix, the fineness of the additives, the amalgamate content, the amalgamate type, the raw material quantity, the waste return content, and the type of feldspar used. After testing these factors using an orthogonal design, designers found limestone content was the most significant factor, with other factors having smaller effects. Increasing the iron content of the limestone by a few percentage points and making minor adjustments to the other factors reduced defective tiles from 30% to less than 1%. Treating temperature as a noise factor and adjusting the various controls reduced the impact of inconsistent temperature by making the product more robust. During the analysis, designers also discovered other cost savings through using different combinations of elements. Robust design techniques lead to improved customer satisfaction, reduced costs, shortened development time, reduced rework, and products getting to market quicker and smoother. For these reasons, robust design is one of the more important recent developments in design theory. The robust design methodology uses an organized framework of experimentation and analysis to develop a product or process highly resistant to uncontrollable noise factors. Robust design works at 3 stages: concept design, parameter design, and tolerance design. During these stages, designers identify the effects of various factors on the desired response. Optimizing the parameters, followed in some cases by tightening the tolerances of the control factors, delivers the highest level of response to the signal factors, or maximum robustness. Designers use statistical analysis to get the highest signal-to-noise ratio at the minimum cost and in the shortest time frame. A lumber company cuts its pine strapping to 8-foot lengths, give or take 1/4 of an inch. To attract new customers, the company considers improving quality by cutting to a tighter specification of plus or minus 0.001 inches. The retooling cost to produce the tighter tolerance proves exorbitant, and as it turns out, research shows the tighter tolerance adds no value to the customer. Pine strapping is used for rough construction rather than fine woodwork, so the money spent on the tighter specification is wasted. The lumber company did not apply robust design principles when determining which critical tolerances should be tightened. A tolerance is the acceptable amount or range a product or process is allowed to deviate from its ideal design specifications. Tolerance design is the third important component of robust design and a valuable tool for meeting design requirements. After the parameter design phase, it is possible a design will still not meet requirements. In that case, the next step is to see if reviewing the tolerances of the product or its components is a viable solution. This is done before the product goes into manufacturing. Tolerance design determines the acceptable range of deviation for a design, taking into account the cost of achieving the tolerances. In most cases, producing perfection is costly, if not impossible. Usually, the tighter the specifications a product must meet, the more expensive the process is. The aims of tolerance design incorporate both the point of view of the customer and the point of view of the organization. From the organization's viewpoint, tolerance design aims to find the amount a process or product can deviate from the ideal and still remain within functional limits. Although this goal is framed from an organizational viewpoint, it still emphasizes the customer's point of view by focusing on functional limits. The other aim of tolerance design is to find the limits in which products or processes may be assembled easily and perform their required function with minimum adjustment. Properly designed specifications can reduce defects and save on high costs associated with rework. Such costs are addressed in one of quality pioneer Genichi Taguchi's important contributions. He proposed a new, broader view of the losses associated with poor quality. Instead of simply considering these as losses affecting the organization, he created the idea of quality loss to include the quality costs to society in general. Quality loss incorporates the costs of poor quality, such as rework and retooling, loss of reputation and market share for the company, low durability, and many other factors. The further a process or product is from its target value, the greater the quality loss. Determining quality loss is a vital part of calculating tolerance specifications, which helps balance quality with cost. In Taguchi's thinking, quality loss is a measurable cost for which a dollar amount can be estimated. He put forth a quality loss function, an equation for finding the tolerance level at which the quality loss is acceptable. Quality losses are estimated using the product's functional deviation from its target values and the cost of a malfunction of the product. This approach is described as using economical safety factors to achieve a balance between quality and cost of design. To determine tolerances, you use the tolerance specification formula, which has two components, the functional limit and the safety limit. The final tolerance specifications are equal to the target plus or minus the result of the functional limit divided by the safety limit. Determining the functional limits is a matter of testing. Some analysts find where the values fall 50% of the time, referring to this 50% point as the median. They use the 50% point as a guideline to set the upper and lower limits. By experimentation, a company determines its top-of-the-line mobile phone's optimum performance occurs when the output signal is 1.0 watts. Testing of the functional limits shows there is no discernible change in functionality if the signal drops as low as 0.8 or peaks as high as 1.2 watts. The functional limits are generally expressed as a percentage, so in this case, the limits are 1.0 watts plus or minus 20%. Therefore, values can range between 0.8 and 1.2 without affecting functionality. The other needed value required for determining tolerance specifications using the formula is the safety limit. This factor takes into account the quality loss, which includes the system-wide loss to the customer, the business, and society in general. The equation for the economical safety factor requires you to take the square root of the result of the loss when exceeding the functional limit divided by the loss when exceeding tolerance specifications. You calculate the economical safety factor by determining the average quality loss after shipment. For example, the shipment of a defective item is known to cost $150. The adjustment cost for the product in-house before shipping might be $20. To determine the economical safety factor in this case, you take the square root of 150 divided by 20, or the square root of 7.5. The safety factor for this item is 2.74, rounded to 2 decimal places. The design department for a home accessories company is trying to set the tolerances for the output voltage of a high-end electric fireplace. The fireplace has the functional limits set at plus or minus 20% of the output voltage, meaning values can range from 80 to 120 volts for the 100-volt fireplace. The designers begin by calculating the economical safety factor. The average quality loss after shipment of a bad fireplace is known to be $250. The adjustment cost of a power supply before shipping is $41.50. So the economical safety factor is calculated as the square root of 250 divided by 41.50, or 2.4544034. The tolerance specification for the output voltage of 100 volts is found by dividing the functional limit, which in this case is 20% or 0.20, by the safety factor of 2.4544034. This yields a value of 0.0814861. The resulting tolerance specification for the output voltage of 100 volts is 100 plus or minus 100 multiplied by 0.0814861, which is equal to 100 plus or minus 8.14861 volts. Although the functional limits were established at 100 plus or minus 20%, which is 100 plus or minus 20 volts, The fireplace should have output voltages within 8.14861 volts of the nominal value. So the upper and lower tolerances should be at 91.851 volts and 108.149 volts when rounded to a more convenient 3 decimal places. When setting tolerances for designs that are made up of 2 or more components, it's important to consider the tolerances of each of these component parts, including the various materials used. One way of considering the individual tolerances for a multi-component item is to use worst-case tolerancing. In worst-case tolerancing, the individual tolerances for each of the component parts are added together to establish the total tolerance for the part. This method is called worst-case tolerancing because setting the overall tolerance specifications in this way allows for the possibility of all the component parts hitting their maximum tolerances at the same time. Exceeding tolerances is costly and must be avoided, but companies also incur costs when the tolerances are exaggerated. When compared against real results, worst-case tolerancing tends to overestimate the amount of variation of the output. As a designer working on a modular ultralight fishing rod, you want to achieve an overall length of 48 inches. The rod is made up of 4 interlocking pieces, each with a tolerance of plus or minus 0.5 inches. The tolerance for the assembly using worst-case tolerancing is the sum of these individual tolerances, or plus or minus 2 inches. This specification proves safe when the rod goes into production. The assembled rods vary slightly, but results never exceed plus or minus 0.5 inches. The alternative approach to worst-case tolerancing is called statistical tolerancing. In worst-case tolerancing, the designer aims for 100% interchangeability of parts in the assembly. Notice in the case of the fishing rod design, all 4 parts were treated the same when calculating the overall tolerance. Statistical tolerancing focuses on the tolerances of individual components rather than the sum of tolerances. Designers who use statistical tolerancing embrace a certain, small, economically acceptable risk of failure in exchange for the opportunity to set tighter tolerances. In the worst-case tolerancing of the fishing rod, allowance was made for the chance that all 4 parts might simultaneously hit their individual tolerance limits. Using statistical tolerancing, designers count on the fact that the odds of that happening are exceedingly small. As variation in the components is normally distributed and components are randomly assembled, the worst-case scenario is highly unlikely. Using this approach, designers can set tighter tolerances. Statistical tolerancing uses the square root of the sum of variances to determine the tolerances required for multi-component parts. This is based on the additive law of variances, which states that for independently selected parts, the variance of the assembly is equal to the sum of the squares of the standard deviations of the individual parts. This approach produces tighter tolerances for the assembly than you would get by adding the individual tolerances, as in the worst-case method. Statistical tolerancing uses the square root of the sum of variances to determine the tolerances required. The calculation depends on several factors, including the desired sigma level. Follow along to learn how statistical tolerancing is applied to the fishing rod design. Let's assume that a plus-minus 5 sigma safety level is required for this product. If the components A, B, C, and D of a 48-inch modular fishing rod have standard deviations of 0.11, 0.10, 0.18, and 0.10 inches respectively at 1 sigma. Using the equation, you find that the assembled rod variance squared is 0.0645. To find the variance of the rod, you take the square root of 0.0645. This gives you the statistical tolerance limit at 1 sigma. To calculate the tolerances at 5 sigma, you must multiply by 5 after, which gives you 1.2698425. The actual overall tolerance is the target level plus or minus the statistical tolerance limit, or in this case 48 plus or minus 1.2698425 inches. Compare this to the tolerance of plus or minus 2 inches determined earlier for a similar rod assembly using worst-case tolerancing. The cost differences and reduction in unnecessary scrap generated could be significant using the tighter tolerances. Statistical tolerancing accepts some risk based on the reality that a reasonably capable manufacturing process, well-centered, will produce very few units of extreme size. This method is popular in mass production situations where a small number of failures is a perfectly acceptable risk. Unlike worst-case tolerancing, statistical tolerancing tends to underestimate the output variation, presenting a small risk to quality rather than a risk to cost. A focus on tolerance design should not be misinterpreted to mean that organizations should aim to barely meet the standard. Products that barely meet the standard are not much better than those that fail. Hitting the target is always the objective. Tolerance design is an important component and tool of robust design. It is used to determine the allowable amount of variation that still keeps the product within functional limits from both the organization's and the customer's points of view. The aim of tolerance design is not perfection, but rather finding tolerances that provide the best balance of quality and cost when parameter design proves insufficient. Using the tolerance specification formula requires testing to determine the product or process's functional limits and calculating the economical safety factor, which takes into account the quality losses. There are different approaches to determining tolerances for assembled parts with subcomponents. Worst-case tolerancing adds the tolerances of the individual parts to ensure a low risk level. Statistical tolerancing accepts a small risk of failure using the sum of the individual variances to determine the overall tolerance specifications. This allows for tighter tolerances and less scrap and rework.